Good day, my dear subscribers. I'm happy to present you part 8 of my series called How to Create a Horror Game. Today we will have a cozy atmosphere for our very first time, because we're sitting near a campfire. As always, I'm holding a cup of tea in my hand and a cookie in another one. Of course, I highly advise you to go through the previous 7 parts before you watch this one. Today we are dedicating most of our time to coding. If you know nothing about it, don't worry. Just as usually, I'll ensure that the information stream is smooth, is easy to understand, and, what's most important, is juicy. Granted that you've watched my previous lessons, you'll most certainly enjoy it. Just make sure that you've ticked the annotations to this video. By the time you're watching it, my notes could be added to it. I do know how long you've been waiting for its release. Please forgive me for such a huge delay. But, you know what? I'm most certain the following hours of content will compensate it with usury. Now to slightly worse news. I'm currently going over a very heavy workload in university. 2014 is my final year before I grab bachelor's diploma. I'm also invited to work in a company, so it's quite possible part 9 will never come out. For instance, this lesson took me 40,000 edits to extract everything that you need and bring your coding knowledge from knees to feet. I do appreciate all the support and love you gave me, so I'll do my best to return and release part 9. If this happens, I promise that it will be a hardcore session in Unity editor scripting. We'll be looking at data structures such as red-black balanced binary search trees, persistent data structures, building extensions to Unity editor, and what's most important, the pathfinding extension. In fact, this is what I'm working at the moment in 2014 for my final year project, so you can be confident that if I do come back, I will be capable of recording another kick-ass tutorial for you. Now, when majority of occasional visitors fast rewind into the middle, it's only me and you. Let's get started, friend.
Alright, I would like to begin by asking you a question. Since we're making trees, how would you think we can make a tree an efficient one so that you can use it with ease in games, in multiple copies of this tree? How can you make it to be an efficient model? Of course, use your knowledge from the previous tutorials and come out with an answer. This is a test for you. As you know, objects from the games, the 3D models, are just a bunch of 3-dimensional coordinates in space. And those vertices, basically dots, are combined into what's called a mesh. In other words, the 3-dimensional object that we're talking about. With the help of those dots, the vertices, we can shape out the objects, that way creating the world of the game. However, we cannot model everything with dots. You cannot make little details, scratches and bumps on the surfaces, like for example looking at the skin of your arm. You have tiny hairs, pores, etc. You cannot detailize your model with the help of just vertices and use it in games. You have to do some other hacks like normal mapping. We were talking about this in tutorial number 4. We're talking about computer games, not movies or any kind of scientific experiences where such models are in fact used. There you can, of course, like 3D scans are solemnly made out of dots, and you get, by the end of the scan, a 3-dimensional model comprised completely from dots. And in programs like ZBrush or Mudbox you can do the same thing. You model those bumps and scratches with a huge number of vertices. But at runtime, you cannot use that amount. Well, at least not for a single object. Because of that, trees that are made of hundreds of thousands of branches with leaves and different surfaces of the bark should not be modeled precisely just with dots, the vertices. Instead of that, you use something different. You can create an efficient trunk of the tree and then stick around it planes, the quads. Each one consists of just 4 dots. Those will be the tiny branches that emerge from the big trunk. On those quads you can stick a texture with your leaves or flowers, fruits, whatever you might have there. That is, you don't model every single tiny branch with vertices. You only need to model the trunk of the tree and the foliage object. Here you can see I've modeled a trunk which consists of just 96 faces. Very efficient. One object is not going to be the cause of the overhead at all, even on mobile devices. In fact, 100 of copies of this tree will still play fine without any kind of lags at a frame rate which is higher than an acceptable one. And for the foliage of the trees, we're using something like this. You see we got several of the planes here, the quads, each one of which is made of triangular pieces, and if you want to be really efficient, you can use not quads, but just one triangular piece per surface. And that way you'll have not 728 of vertices, but a quarter less, and you'll have much more efficient foliage. You can still have 182 of faces, the triangles. However, with that amount your foliage will look twice bigger, because each of those planes currently is built of 2 triangles. So if you just use 1 triangle per surface, you're going to be able to model a bigger foliage. Each one of those planes has a square UV layout. Since the plane is already square, just make sure that it samples the right area of the texture and you're good to go. We use the same texture per every single surface, per every quad, and it's still not noticeable. You get very nice results with this. However, there is still one thing. For instance, you can use a picture like this one, something similar to this. I got my tree trunk texture here, branches with leaves on the bottom left, and a branch with the grayed out leaves, like dead ones, on the right. And a couple of external textures like an arrow or a cross, just to make use of the extra space on my texture. And because it's a PNG texture, in 3ds Max we have artifacts here, which are not visible in the final output in Unity, but 3ds Max doesn't recognize alpha channels by default. That's why you see those artifacts. So let's pretend that we're going to be using the JPEG texture for now. This one, for example, the one that has white background instead of alpha channel. That way you can see what's happening there with a greater ease right now. The whole texture is of course 1024 by 1024. You can actually go with 512 and it would be much better. However, you could obviously stick less things into it, or they will be forced to be less detailed, since every single piece will be taking less pixels on the texture. But because I want to have one texture and different variations of the tree, I've stuck everything in here, as well as this vine that is going to be positioned on top of the rocks, the mountains maybe, or big boulders. And because I have everything here in my tiny atlas, well, 1024 is not that big for atlases, but because I have everything here, I can just sample from this texture with ease. And let me show you what the tree trunk looks like with this texture. Here I have it. If we apply an unwrap UVW modifier, just to see what's going on. First of all, let's apply our texture, so that we can see in the background. Not this one, but the one without alpha channels, so that we can see without artifacts in the viewport. Now you can see that everything here is sampling from just this spot. Because I'm using dirty normal maps, which I think were discussed in tutorial number 4, somewhere at the end. Because I'm using them, I don't actually have to provide space to each of my UV patches separately, because we're not baking the normal maps from the higher representation of geometry to the lower one. We're just using the normal map texture that is going to be supplied along with this one, along with this picture, as a second texture. Because of that, my UV patches are overlaying, and you can see that at the top of the tree, such as this one for instance, is simply turned around. Initially it was looking like this, then I flipped it vertically, then position it in the following way. Of course, press F4 to get rid of the wireframe mode. Also uncheck any visibility of the seams like peel seams or map seams, just to see if there are any problems occurring right here and if the texture is actually fitting together. Or you can see the texture joint, which is bad. If that happens, arrange your parts so that it's less visible. But because I'm using dirty normal maps and just a single sampling of the texture, I can afford this tiny piece of texture to be sampled by many polygons. And instead of having a straight piece, which wouldn't fit into this square, would have to be sized down to fit like this altogether. Instead of this, I simply bent it in half and overlay pieces on top of each other. Observe that I didn't move the seams from my UV patches apart. Because of that, I'm not gonna have a seam right here. In the viewport, we're gonna see a reflected texture across the model, since this part is sampling from the same spot as this one right there, which is somewhere right here. That way, there is no clear seam to the viewer, and at such big distances from below, for example, of the tree, you're not gonna be able to recognize it. The only downside to my current UV layout is that I sample with 2 different halves from the same space on the texture. Because of that, you can see the reflection happening here, on left and right, and then a reflection right here. The cause of that is that I didn't provide extra space for every single UV patch, and they are sampling from the same zone on the texture. However, I've saved myself a lot of texture space that way, so no separate UV patches, everything samples from a narrow spot. The same story happens for the trees. Let me Alt-Q to exit the isolate selection mode, select my foliage, and hide everything else. You can see that this is a set of planes, a group of planes, and if you pull this one, for example, to the left, I'll press F2 so that you can see my selection. This one consists of 2 triangles, because quads are always built from triangular pieces. Let's convert this really quickly to an editable mesh. You can see that indeed everything here is made out of triangles. They are like subcomponents of your polygons. And that's what I was talking about just a second ago. You can have not quads for your foliage, not planes, but just triangles. This will allow you to create twice more surfaces, each one of which will contain just one triangle. And you can create either twice more optimized foliage, or have the same number of surfaces, and your foliage will look twice bigger. As well as, of course, reducing the count of vertices. The count will be reduced by 1/4. Let me pull this polygon aside for comparison as well. Of course, if you want to put a texture of branch on this triangle, you're going to be able to put less texture on this surface than if you would be putting it on quad. So quad is much simpler in that sense. But if you're sampling from the spot of a texture, Well, it's not going to be a big problem with a triangle. However, have a look at what happens. They are already unwrapped. So by deleting one half of the polygon, I didn't modify the UV layout of the remaining triangular piece. Let's apply it to our quad. I'll press F2 so that you can see what happens. And apply it also to the triangle. We cannot apply it because we currently have the quad selected. So let's just click in the empty space to deselect everything. Then we can assign material to everything at once, to all the polygons of our foliage. As you can see, this polygon is just a half of the texture right here. That's why you have to think about how you're gonna arrange this. First of all, triangle is by default a half of your plane. That's why if you want to stick the same size of the texture, it's gonna be at least twice bigger, like this. But then if we try to remap and adjust the UV coordinates so that it fits, let's see. Select this polygon, pick our texture. As you can see, you have to arrange your pictures in a different way, since in case you want to stick your whole branch into it, similar to this, you are able to do so, but you're also grabbing other parts of the picture as well. So it's up to you what you want to have. The first option is have less vertices and surfaces, or have more stuff drawn on the texture. It's a very interesting subject because you gotta find the balance. Either you're gonna have triangular branches, or the ones that are gonna fit better in this setup. If you have branches that fit into your triangle completely and don't look awkward, don't grab any other extra texture parts, completely go with this approach. In my case, the branches are suited best to be sampled by quads. And because of this, pictures on my texture are packed tighter than anything else if I would be using triangles. Remember that UV layout is always styled to the left and to the right, so if your triangle is out of bounds, it's gonna work out as if it would be sampling from the opposite side. Here, let me show you really quickly. Let's go into Options, Preferences, and show what happens in reality. So, tiled bitmap ticked on. And there you go, you can see that the triangle is out of bounds of our UV table, therefore sampling from the other side, the one on the right. You can be very sneaky, and you can actually do the following. Have your UV patch of your triangle positioned like this, and let one half of the triangle sample from here, and then have the second half, the left one, of your green branch to be displayed here. So it's kind of working like with tileable textures. Doesn't matter if you offset it out of bounds, it's still going to be sampling from the appropriate half of the picture. For instance, let me show you what I did for my herbs. Let's open Material Editor, pick a different one, and apply a diffuse texture, the one with my herbs. By the way, you don't have to click on this button and go up a level all the time. Go into the required folder. You can simply search for the folder that you visited a second ago in here. This is a big time savior. I absolutely love it. Make sure to use it. That way traveling back and forth between recently visited folders. Let's assign the material to our plane so that it's visible in the viewport. And okay, it's a PNG. We're gonna have slight problems because we'll have little artifacts coming from the alpha channel. But once again, ignore it since in reality the alpha channel will be cut out in Unity. Let's quickly set up the background. My grass, as follows, will be displayed with the triangular pieces. That way I'm planning to have a more efficient grass on the ground. But because of that, I had to arrange my textures in an appropriate way. You can see that the texture is arranged such that we have a part, the triangular piece right here, sampling from 0.5 in X, all the way to 1 in X, and then something like 2/3 of Y, all the way up to 1 in Y. Beside it, we have a different herb, which also awaits for its own triangular piece to sample from it. And we have a reversed triangle right there, the one that's turned upside down, for this herb that sits inside of here. We have a herb right here, and the other one right there. But what happens on the sides, and what I was talking about before, how you can arrange your texture efficiently, if it is stylable, you can split two of your triangles. For instance, the half of this triangle can be here, and then the second part can be on the opposite side, right there. That way, when you sample with your triangle, and it's going to be offset, sampling from out of bounds of your UV rectangle, you're going to be sampling from this half over there. But it's a very rare case. Herbs are shaped that way so that you can fit them into triangles. But that is not the case with branches, and that is why I've chosen a different approach. I've chosen to go with the quads for the foliage of my model, since that way I simplify my sampling, having my branches packed up nicely, avoiding any empty spaces around the branches as much as possible. Of course, the way I did this is I quickly created a plane, quickly unwrapped it to sample the texture of this specific part on the UV, closed it, then collapsed all the stacks, converted this polygon or piece to an editable poly, then quickly duplicated everything, rotated the pieces in such a way that they surround my trunk, which is, well, you can see it here. I just duplicated the pieces so that they surround each of the branches. Because I've unwrapped everything before, every single piece has copied the UV coordinates from the initial first plane. Now when I have the foliage ready as a single piece of geometry, there is one more final step to do. This is a quite special strategy. Some people don't know about it, but if you want to create really nice looking trees, you have to do this one more step. There is a thing in 3ds Max that we didn't talk about before. If you open your maths book, you will find out that every single plane can be specified in 3D World with just two parameters. First one is the pointing space, which contains 3 coordinates x, y, and z, and the direction that the plane is looking at. If I create particle system, let's see which one it is, pf source for example, just for the sake of the arrow gizmo that it has, to illustrate you the example. We have a pointing space where our plane is positioned, but now we need to specify the second parameter, which is the direction. We can do this with a normal vector. Vector is simply a difference between 2 coordinates.
If you subtract coordinate A from coordinate B, you'll get a vector which originates exactly from A and points directly to B.
So it's a difference between coordinates, each one of which has 3 components, x, y, and z, just like normal 3D space point would be. This vector has to be perpendicular to the plane. In other words, to be orthogonal. That is exactly the purpose of the normal vector. If you think about it, there is only one possibility for it to be perpendicular. Having those 2 components and modifying them, you will turn around the plane. A second way to specify a plane is with the 3 dots, the 3 vertices. Perfect example is this triangular piece that I've shown you a couple of minutes ago. There is only one single plane to which those 3 dots that make up the triangle belong to. Because of that, the normal of the triangle is the same as the normal of the plane that those points belong to. That way, when you render it to the screen, the computer knows in which direction the polygon is faced. While in maths, dots are one-dimensional objects and don't have additional directional vectors, it's only a property of planes. In 3ds Max, each vertex has a normal. So here you can see the plane consisting of 4 dots, and each vertex will have a normal. If I go to modify, reduce down the length segments to just 1, 1, press F4 so that you can see the wireframe, and apply a new modifier which you haven't seen before. It's called edit normals. Let's bump up the display length and change color to something like yellow. Observe the sticks, or the normals, that are sticking outside from each of the points. Because they are all facing in the same direction, when we rotate around our plane, it's shaded in the same way across the surface. However, if we select one and then move it aside, thereby modifying the direction that the vertex is looking at, the surrounding area of the polygon, which the vertex controls, is fooled into believing that it's pointing in a different direction than it is in reality. If we change the color to something darker, say like purple, you can see this effect in action. Modifying the different normal, you can see that we're basically shifting the glossy part around. That way you can fake the eye into believing that the plane is actually round, convex, or is bent, but it's not really the case in reality. It's an illusion. I'll pick those 2 and move them aside, then pick the other opposite ones, shifting them to the other side as well. Notice how the specular part has changed. If you look around, you can see that this is a totally fakey surface, and it looks like it has a pimple on the center of it. We're fooling the computer into believing that. What happens there is we're having an effect on the pixel shader of 3ds Max. We will probably discuss them in the further series of my tutorials, but currently they are out of our scope and are unnecessary. We will be learning them probably after we're done with the coding and the pathfinding for the game, the artificial intelligence. For now, just know that every single vertex has a normal, by altering which you can adjust the surroundings that the vertex controls. Because of that, we can create some very nice effects. For instance, when you populate your terrain or ground in your 3D engine with grass, herbs, bushes, or anything like that, every single grass piece is obviously drawn on a plane. And you usually don't draw one grass blade per plane. You draw a pack of grass as a texture and then sample this texture with one plane. So many grass pieces are drawn on one single plane, be it the plane or the triangle. I'm going to be using myself triangular pieces, just like I told you before. Due to that, it's going to be quite efficient, but you're bound to have some problems. Let's say you have a plane, which is your terrain. As I build it, I'll pick a dark color, something like purple, and for my grass blades, let's also make them purple. Press A to make sure that we can snap by 5 degrees while rotating, then bring it to be orthogonal to the plane. Bring it upwards like so, and we could have gone here and adjusted the pivot to be lower, but it's not necessary. All of that was covered in previous tutorials anyway. In this example, if you look above, you can see that the terrain is shaded nicely, but the grass blade is quite dark. That's because the computer sees that the normals of the grass blade are not faced in the direction of the camera, which emits light in the shaded mode of 3ds Max. And this is the case why it's shaded darker, but the plane, the terrain, whose normals are looking exactly towards the camera, are shaded brighter. Let's imagine that we are the sun, since our camera emits light, and that we rotate around the ground. At some point we'll have to go behind the horizon, basically do a sunset. As we approach the horizon, the ground will be lit darker, since the normals are pointing in a direction different to our camera. But the plane, which carries the texture of a pack of grass or herbs, will be lit much more brighter than the ground. At such times, when the sunset occurs, in game engine this creates a very distinct separation of 2 things. It looks like the grass and the terrain are 2 separate things. It looks like the grass is just stuck on top of the plane, it's not actually growing out of it and it's not bound with it, which is very bad. This is the problem that we'll eliminate. In order to fix this, you have to alter two of the vertex normals on the bottom of this plane. By selecting the plane, go into the Modify panel, picking up Edit Normals. Press 1 to be able to select the subcomponents of the modifier, that is the normals of the vertices of the plane. Grab the required ones, and you can move them, or you can even rotate them. So I'll press E, then we'll rotate them by 90 degrees, which you can see at the bottom of the screen. It was occurring here. I will exit Edit Normals, and we'll click in the empty space. As well as that, let's press F4 to get rid of the wireframe. Notice the nice gradient that smooths out into the terrain from the plane now. The grass blade actually looks like it's bound with the ground and grows from it. Of course, in reality, it's a separate piece. Now, when the sun is setting, the grass blade will be shaded in a conjunction with the terrain, since some of the normals are pointing in the same direction as the normals of the terrain do. The terrain's normals are all looking upwards. The blade of the grass is looking up like this as well, faking the effect that those two vertices are being carried by a flat plane. Since those two normals are aligned, we get the same gradient on both parts. The other normals of the other two vertices are looking in a different direction, that's why they are shaded differently. There are several tutorials on YouTube on how to use those options on Edit Normals, but it's nothing complex. It's simply how to manipulate those normals in an efficient way, quickly and precisely. How to align the normals of one point to the normals of another one quickly, etc. Now you can right click and convert this thing to an editable poly, and it will still preserve the direction of the normals of the vertices. Of course, converting to an editable poly is an equivalent of collapsing the stacks. The procedure that we performed a second ago was called explicitly setting up the normals of the vertices. Not many of the game engines do support it, but Unity and Unreal Engine, and I'm pretty sure CryEngine, do support it, which is excellent. When you export your model in an FBX format, make sure that Preserve Edge Orientation is turned on. If you are exporting as an OBJ format, ensure that the normals parameter is ticked on. That way, your altered normals for the object will be exported along with the mesh. But we were talking about the trees, and now we're talking about the grass and the normals. How are those two things related, you might ask? Let me get rid of this first. I will pick those three foliages. We'll go into the realistic mode. We'll press Ctrl L to ensure that I'm shading everything in real time with the lights that I've positioned into my scene along with other objects. Let me pick this light and actually assign a green material to the foliages. Pick up the difference. Observe this foliage right here. That one here as well. And observe this one. Again, back to the previous one. And back to this one. When we rotate this specific foliage object, you can see how the shading is nicely applied across the whole surface. It happens even though all the planes are pointing in different directions. Here, they are also pointing in different directions, and in fact it's the exact copy of the previously shaded model. However, the normals of this object are not set in an appropriate way. They are all pointing in different directions, which creates a hectic representation, very unnatural one of those leaves, like they are really sharp blades. Here it looks like some kind of round foliage, very soft, although it's made in exactly the same way as this bad foliage that I've shown you. Finally, to create beautiful trees, you're gonna have to do this one more final secret step, which is to steal the normals of your mesh from the round object. This is easily done in Autodesk Maya program, transferring the normals of one object to the vertices of another. But in 3ds Max you cannot do it by default. That's why you have to search on the internet for a Max script called Normal Thief. Once you get it, extract it to the folder located at the following path. It is your drive, see for example, Program Files, Autodesk, your current version of 3ds Max program, / macro scripts, which is the folder inside of 3ds Max 2013 in my case. So macro scripts, and drop your script into this folder. Then you can restart your 3ds Max, and when you go into Max script, you can open the script from this directory. Press Ctrl E to execute it, or you could have just run the script from the same directory. This script is quite slow, that is why people have attempted to improve it. That way a slide normal thief script was created, however, which is very buggy. I couldn't start it out, I could not run it, and people who managed to make it run say that the normals are kind of packed in an unnatural way, in the way that they didn't intend them to be. The normal thief that we're using will allow us to steal the normals from one object and copy those normals to the vertices of the other object. Here you can see me having this foliage. Quickly grabbing my foliage and going into the isolate selection mode, I will show you what you have to do in order to make use of this script. First of all, you have to create an object to steal the normals from. In this case, we're going to approximate the shape of the foliage by changing around the vertices of the geosphere. Don't create a sphere, because it has a different construction method. As you can see, the polygons and vertices are shrunken down towards the pole if you have created an ordinary sphere. Yes, it might look more round than the geosphere, but this is a bad approach for our case. We want all the points to be at an equal distance from each other. due to the normal thief script being so slow, we want to reduce the number of segments down to, well, 2 will be too much. Let's have our geosphere consisting of polygons that have 3 segments set as a parameter. Then once we are ready, let's click on the model that we've just finished creating, arranging the polygons, etc. Go into the third panel right here, effect pivot only, center to object, so that the object's pivot is positioned in point in space, which is an average of the coordinates of the vertices that make up this model. And the pivot point of our geosphere is already in the center by default. Then let's click on the geosphere and align it with our object, pivot to pivot in X, Y, and Z. Rotation doesn't matter. We were discussing this whole alignment thing in part 6 when we were rigging our character. Make sure to check it out. It's quite intense. It's 6 hours and it's really interesting and hardcore. I'll press Alt X while having my geosphere selected so that we can see through it. Let's go into the shaded mode because we don't need any fancy lighting. I will scale the object down. And then remember that once you scale anything, you always have to go into this panel right here with a hammer and reset X form. Also, let's reset the X form for our foliage as well. It is actually a necessity. You have to use it before you apply your script. Once we have this done, we can go into the second panel, then right-click, collapse the stacks, or simply right-click and convert it to an editable poly. That's an equivalent of collapsing the stacks. When we have multiple objects, instead of selecting each one and then collapsing the stacks for each object specifically, you can select all of them and just right-click, convert everything to editable poly, and then each one will have its own stacks collapsed. Grab our geosphere, go into the vertex mode, and if you don't have those 2 panels like I had in tutorial number 6 or before, you can grab by this border and drag it to the left, extending your inspector panel to take up more space. You can have 3, 4, 5, any number that you desire. I'm using just the 2. That way you can go down, go into paint deformations, select your push and pull brush, grab original normals, because you want to push away from the surface direction, not along the world axis, Y, X, or Z. So original normals, outwards from the surface. Increase the brush value and the strength, as well as the brush size right here. If you want to, you can actually use the brush modes from the graphite modeling tools, but I prefer to do it in this old-fashioned way. It's much quicker in my opinion. And we want to shape it out, the geosphere, so that it approximates the volume of our foliage made out of polygons. With the left clicking we can extend and extrude the surface outwards. With the Alt left clicking we can push it inwards. And just rotate around the object like normal. Alt middle mouse button. If you have big spikes, you can go into the relax mode, adjust the strength of the brush, and then smooth out those peaks and sharp surfaces. If you are really into this working mode, you can go into brush settings and adjust the fall off, the brush types, to create craters or whatever you want, but I don't advise you, since there are other programs designed specifically for that. It's much easier to work there than in here. So don't do anything too fancy and over the head. So just follow those simple instructions, but know that this option is still there for you to use if there is ever a need. Make sure that none of the vertices are sticking outside of your geosphere. I have done this already, so I'm just gonna get rid of this one, and for the sake of time, I'll pick the one that I have finished working on before. Once this is ready, exit any regime by pressing 6, or simply click on the editing mode that you've been working in and get out. Click on the hammer, reset X form for the object, right click, convert to editable poly. After you're done tweaking your geometry with the brush deformation, last step to do is to go into the vertex mode, Ctrl A, remove isolated vertices. That's very important, otherwise this will freeze your script and will throw out an error at you. I had this problem before and it was really freaking me out, because nobody had an answer to what was going on, so it took me a lot of time to figure out how to solve it. Isolated vertex is something like this. It's isolated, it's not controlling any surfaces, but it's still sitting there, so if you remove isolated vertices, it will disappear. If you want to, you can also remove unused map vertices, but it's not necessary in our case. Repeat the same procedure for your geosphere. Then go into hammer, reset X form, reset selected, and reset X form on your foliage as well. Then before you can use the script, you have to select both of them and convert each one to an editable mesh. That way I've converted all of them at once to an editable mesh. Now we can run our script, grab it from the directory where you should have saved it, the one that I talked previously about, and all of the scripts should be saved in this directory ending with the macro script folder. Any scripts that you download have to be placed in this folder. Once you run it, as you can see, you have to pick a reference object, so left click and carefully click on your geosphere editable mesh. Then select the object to change the normals of, that is our foliage mesh. Then once you click action, it will update for a few seconds and then the update function of 3ds Max will freeze, and you won't see any change on the screen until the script has finished. It will take its time, something like 5 to 10 minutes, so give it some space, and once it's done it will come out nicely. The problem that I had before is that it would work for like 30 or 40%, and then it would say vertex number 99 has got a problem with the normal, so I'm terminating myself and not continuing to steal the normals. So removing the isolated vertices fixed that problem. The way the script is working is it's figuring out for every single vertex of the mesh the closest vertex from the reference mesh from which we're stealing the normals. So we find the closest vertex and then we copy the normal to our working vertex. By the end of the process, we will have foliage whose normals are sticking in the same direction as the normals of our modified geosphere object. That's why the script is so slow. Our foliage is made out of that many vertices, and for every single one we'll scan about 200 vertices, which make our geosphere. So multiply those two numbers, and you'll have the number of procedures that have to be run in order to shape out the normals of the foliage. So let's click Action. Once this is done, you will see message saying done and done in both places. You can close the script now, and actually we can get rid of our geosphere now. It served its purpose. Press F4 to get rid of the wireframe, and as you can see, the script placed edit normals modifier onto the mesh. So you can right click and convert everything to editable poly just to collapse the stacks. And this will preserve the direction of normals as they were set. Altogether, those planes are now suggesting more volume to the eye. They create an illusion of a thicker and a softer foliage. Let's unhide everything else, go into realistic, press Ctrl L to make sure that the light is shining in real time onto your modals, then observe its look. So yes, indeed, very soft transitions between leaves and nothing like it was before. The planes look like they belong to the same group and are joined somehow. That way you can create very soft looking trees. Along with that, if you import it into the 3D engine, it will look just as good. That actually looks both as good as right now, as well as when you have your texture with an alpha channel. The alpha channel gets cut out, and you will have a solid part of the texture, which are leaves, or drawn branches, remaining. Let's quickly export this tree as an FBX format, then teleport ourselves to Unity. If you opened Unity for the first time in your life, don't freak out, because I will explain majority of the stuff to you, just like I normally do, and you'll be quickly familiar with the interface and how it's working. First things first, you have to create a project. Project is an equivalent of saying my game. You're just saying my project. For that, go into File, New Project. Specify the directory where your game should be located. In my case, it's going to be in my computer, my drive called E, and I will set up the one in the folder called Other. We'll create a folder called New Game. If you suddenly remember that you need to adjust the folder, you can browse again. Currently we are in the New Game. We can create another folder and store our game in an even more deep directory. Or simply put / and the name of the folder that you want to store your game into, or if the specified path does not exist, the extra folders will be created. When this is done, we can import extra tools that Unity provides to us, like fancy effects or some extra scripts. Those things will enhance the look of our game, however for now let's leave them unchecked. We are only going to be looking at our tree that we will import in a second. And set up defaults for 3D, because we're not making a 2D game. Then create. Wait until the project is rebuilt. Once it's done, you can see something similar to this layout. If your layout is different, you can click here, then pick the one that you prefer. As for myself, I prefer to work with the default one. However, you can work even in 4-split, like in 3ds Max. This panel is called Hierarchy, as you can see by this tab. Here's the project panel, the console is right here, and we'll talk about console and everything else as this tutorial progresses. The inspector is this panel right here, and finally two panels are Scene and Game. You can switch between them by clicking on them, or if you want to, click on the tab, then reposition it to wherever you want it to be. Obviously you can do the same thing for any other panel, creating your custom layout that way. You can even detach it and have it like a different window on a different monitor or something. Currently in our game view, you can see what we have in our scene by inspecting the hierarchy right here. At the moment we have just one main camera. Cameras are delivering all the required information to the screen. This is what the player will see when he plays your game. It will be rotating around the world, the scene, capturing and visualizing different things of your game from different angles. Later on you can stick different effects to camera to enhance the look, to make it look like the character is drunk, to enhance the colors, to add HDR, whatever you want. We're gonna look at this later on. Just as in 3ds Max, which is really nice, by pressing W, you will call for the handles for movement, and it's exactly the same way as moving in 3ds Max. By grabbing one of the handles, you'll be sliding along the respectful axis. Following the well-established convention, the red one is X, green one is Y, and blue is the Z, the forward axis. In 3ds Max, the Z is looking upwards, and Y is looking forward. Here it's vice versa. As you import your models into Unity, be it FBX or OBJ, this is taken into the account. Have a look at the options of the FBX exporter in 3ds Max, and you will spot this setting. That way your meshes are displayed correctly when transferred between two worlds, the Unity world and 3ds Max. So W for movement, E for rotation, and R for scaling. Scaling along one axis is called non-uniform scaling, just as in 3ds Max, and scaling by grabbing in the center is the uniform scale. Non-uniform scaling is actually bad in Unity. I will discuss why later on. Let's stop learning about the hierarchy panel for a moment and focus on the following panel, which is called Project. Project is displaying the set and the structure of our folders. If we go into my computer, then data E, other, the directory where we've chosen our game to reside. Everything that we'll see in the project panel will be inside of the assets folder. We are not able to access those other three ones because that's where the preferences for our projects are located and other helpful files. However, we can alter the files that are inside of here by working with the Unity's interface. But let's not touch them for now. Let's leave them for later. That is, assets is your folder right here. That's where the things for our game will be located at. And to quickly navigate between places, just as in 3ds Max, you can click over here, then pick the most recent path that you've been working with, the one that you've been visiting often, and that way you can travel back and forth between your folders dedicated to 3ds Max and Unity and copy stuff around back and forth. While working in Unity, you can right-click on the assets folder in the project panel and create another subfolder, for instance, my folder. When writing the names for the folders, we're using the so-called camel case. It was discussed in tutorial number 6 when we were rigging our character, somewhere in the middle of the lesson, when we were doing scripting in 3ds Max. But camel case is simply writing without spaces. If you want to make it clear that the name consists of two words, just start the second word with a capital letter. As you can see, my folder belongs to the assets folder. It is the subfolder of the assets. And if we look over here, there we go. We created my folder inside of the assets one. We could have also done the same thing by not left-clicking on the assets, then right-clicking, create a new subfolder. Instead, we could have right-clicked over here in the empty space in the representation of the assets folder, its view, and could have created the same folder. For example, my second folder. You can change the size of those icons with this slider, having a very packed version somewhere here, or a very big bold one where you see all the names and the icons are big. I will go to the folder where I've exported my tree. It happens to be a different project as well. I will just steal it from there or make a copy. And I have a tree set right here, so I'll press Ctrl C, then of course pick my path from here. And let's import this asset into my folder, the first one. In order to do this, we can either right-click and import new asset, then navigate to the one that we want to import. This will snatch it from there and will create a copy of an asset in my folder. Or we can be smarter and just copy it by hand from one directory into another one by using my computer, selecting my folder and pressing Ctrl V to paste the asset into my folder. As we click into Unity, it will quickly update its assets. As you can see, we got our trees mesh from our 3ds Max FBX file format, the trees object with all the meshes, and the accompanying materials folder. I prefer not to have it, however for those couple of minutes I'll keep onto it, and then later on I'll get rid of it. As you can see, my folder indeed contains materials subfolder with one material. We can left click on this object and drag it into the scene. If I click on the trunk and press F on my keyboard, this will adjust the screen view to focus on the object. I can press Alt left click to rotate around the scene. This is different to navigating in 3ds Max, where you Alt middle mouse click to orbit. As well as that, I can right click and use my WASD keys to move just like in shooter games. The longer you hold your keys for, the more the camera will accelerate. Eventually you'll get very quick speeds, so if you have huge scenes, this is very handy to navigate around. Of course, you can press F to focus back on the object. You can zoom in by Alt right clicking or simply scrolling up and down with your mouse. You can pan across the scene by clicking on middle mouse button and dragging left and right just like in 3ds Max. So the only difference is pretty much Alt left clicking to orbit around. However, you almost never use it and you just go around flying with the right clicking and WASD keys. You can see that by left click and dragging the object into the scene, we instantiated it and now we have a trees object, which if we click on it and move it around, will control other three objects. That is, it has three sub-objects, each one of which has a child object as well, called foliage. If we click on the trunk, we're going to be controlling the trunk and its child. And then if we click on the trunk of a different tree, we're going to be controlling the trunk and its specific foliage. However, if we want to control all of them at once, we're gonna click on the trees object, the main parent, the one that inbounds those three objects, and alter it like this. You can put the axis to be located at the pivot point of the trunk, the position of which we've set up in 3ds Max. You can have the axis positioned at the pivot, or in the center of an object. You can scale, move, rotate globally along the axis of the world, or if you changed your object like this, you can move it locally along the axis of the pivot point. You can switch easily between pivot point or center option by using the shortcut Z, and Ctrl Z to roll back your actions. Ctrl Y to forward roll, that is to redo something, just like in 3ds Max. Notice that there is one slight problem with our trees. Back in 3ds Max, the planes were visualized as two-sided. However, it is not the case with Unity. Unity culls, or in other words hides, everything that has turned its back onto the camera. For instance, have a look at this plane. When we move behind it, it will disappear. This is exactly why half of our leaves are not visible on this tree. This can be easily fixed, so don't worry about this for now. Since I want to have a bigger scene view window, I will drag this game window behind the scene by grabbing its tab and docking it near the scene tab. That way, they are effectively under each other, so we have now more space for the scene view. It's time to get rid of our materials folder that has accompanied this object since we imported it into Unity. So let's press delete on it, or right click and delete. Unity will tell you that you cannot undo this, so make sure that you don't accidentally delete something important. Better to double check what's inside of it before you do so. That way we'll get rid of the material which accompanies our trees, and because of that they will not know on how to color themselves. Due to that, they will become pink, signifying that they are lacking material. That's okay, because in my folder, nearby to our trees, we can right-click and create a new material, just like in 3ds Max when we pressed M and created our materials. Let's call this one tree material, or tree capital M-A-T, so tree mat with a camel case notation. Now we can left-click and drag it onto the meshes of each of our objects in our scene view. Do so for the foliage and the tree trunks as well. By default, it's the simple diffuse material. That means that any information that will be processed is only concerned about colors, the emission color. It might come either from the texture or the main multiplicative color. We can instantiate many copies by left-click and dragging it into the scene. But then we'll have to reassign the material once again to our models. This is quite a tedious task. However, once we get rid of our materials folder that accompanies our FBX file, it will have this problem. If we don't want to be bothered by reassigning material every time we instantiate it, we can actually leave aside this prefab and let's call it something like double_trees. So that we show that it's obsolete, but it's still necessary. And then let's create a container which is called prefabs in Unity. Let's call it trees. I'll get rid of the newer version of trees just to have the older ones in my scene view. And as you can see, we got our trees object with 3 sub-objects, each one of which has one child object. Let's close our trees, then left click and drag it into our newly created trees prefab container to store it inside of it. Now, because we stored information about our material into our trees object while it was in the scene, this reference about the material has went inside of the container along with our trees object and its sub-objects. Now, when we spread new copies and instantiate those objects from this new prefab, they will have their material along with it already assigned. However, we cannot get rid of the obsolete trees prefab, since it's the root one which contains the information about the meshes. You cannot copy them or paste them into here, so you just gotta have them sitting there beside the trees. From now on, we're going to be working with the new trees prefab. If you change something within the model, for example, alter the hierarchy between the children, you can pick one of the objects and click revert. With this, you copy the state from the prefab from which the object was instantiated, effectively reverting everything that you've done to the instantiated copy. Notice that when we change the hierarchy, Unity will give us a message saying losing prefab connection, do you want to proceed? If you press continue, your objects in the hierarchy panel will not be highlighted with blue anymore, meaning that they have a different state inside of them to the prefab that they belong to. By clicking on the prefab, you can change the default scale and other default parameters that will be attached later on via the Add Component button. However, because those objects have now lost the connection to their prefab, we can no longer affect the scale of those models all at once. That's why let's click on the trees or any other sub-object, then go to revert. Now the objects are again connected to the prefab. If we press Ctrl+C and Ctrl+V to duplicate it, now we have the second trees object, and Ctrl+V again. If we change the scale of those trees, it's going to be changing the scale only for this object. However, because it's connected to the prefab, we can select the prefab, and then for all of the objects which are deriving from this prefab, we can change the scale all at once. By that much, for instance. Because I was scaling each one individually by different amounts, this is called non-uniform scaling, which is bad in Unity. So if you do scale something, try to do it by an equal amount, or pre-scale your mesh in 3ds Max before you export it into Unity. But it's not really a killer if you do scale it ununiformly. Otherwise, this option wouldn't even exist. So let's do like 1.5. Now, any objects that are instantiated from this prefab will be bigger by half. We can rewrite this prefab. So for instance, if we put all of those 3 objects under the tree object, now we can click this main tree object and drag it on top of the prefab right there. This has rewritten the prefab. Now, if we get rid of the trees object from our scene, we're going to be able to instantiate 6 trees at once every single time we instantiate this prefab into our scene. By now, I've ensured that you are at least a little bit familiar with Unity's interface. Let's see which preferences we can change inside of Unity. We will have a look at Edit, Preferences. There are several settings which you shouldn't touch, except for maybe this one. You can have different themes of Unity. The default one is dark, the legacy one, the one that Unity has been using before, is white. we are particularly interested in external tools. For our scripting, we're going to be using a built-in editor called MonoDevelop. Because it's buggy in Unity's version 4.6, we're not going to be using the default built-in one, but we will pick the correct version on our own. Select Browse, click on my computer, and find the executable file for MonoDevelop. In my case, it will be in my C disk, Programs 86, Unity, MonoDevelop, and you can pick the MonoDevelop shortcut, or go into bin, and then click directly on the executable file for the MonoDevelop. With this, now we're going to be able to edit scripts with our MonoDevelop editor. You can have different editors, but we're using MonoDevelop. If we double click on any of the images inside of our projects folder, we will open it in the application specified in the image editor option right there. You can browse for the shortcut of Photoshop or GIMP if you're using that one. Obviously, 3ds Max is not going to work for that, and we're done with this page. Inside of colors, you can specify which colors the wireframes should be of different states. We have this trees object selected, and because of that, it's outlined with a bluish blue wireframe. We can change this color by making it something like bright red, then observe the changes in the viewport. If you want to get rid of wireframes completely, just set the alpha to black. That way you'll get rid of any colors, or set it to be really white, so the alpha component has the maximum value to make it really prominent. If you press W, you can see that the axes are highlighted with different colors, so you can change their color. But I wouldn't really advise you because red, green and blue are well-known colors for their specific axes coming from Maya and 3ds Max, so it's quite common to use those three colors. Don't touch them. So in this part of the window you can play around with the colors, thereby changing the view and the mood of the scene. Inside of the keys, you can set up several of the shortcuts, not all of them, but some of them. For instance, to toggle between 2D and 3D mode, which you don't need in a 3D game, you can press 2, and this will put you into the appropriate 2D mode. I have disabled this shortcut, and now it's Alt Quote for me, the combination which I'll probably never use. But if you want to reassign it, left click, and then press a key that you want to store. For example, number 2, like it was by default. Then once I press 2 on my keyboard, I'm switching between 2D and 3D representation of the scene. Let's make it as it was before, so Alt Quote, or simply a quote and then tag the required combination, be it Alt, Control or Shift. Move is W, and everything else you can inspect on your own. That's it for now. Let's close the Unity preferences. Once again, they are accessible via the Edit and then Preferences. And let's have a look at this view cube right there. It kind of reminds us of the one from the 3ds Max, but it has one difference. You cannot click on it and drag it to rotate the scene. But if you click on its center, this will put you into the orthographic mode, which doesn't have perspective, useful for 2D games once again. And if you click on the axis, this will align your view directly, perpendicular to this axis. That way you can look from exact size, the top, the bottom, and all around. Remember that F is to focus on the selected object. The project panel is displaying your hierarchy of folders, basically this one, everything inside of the assets folder. Beside it, because of my current layout, you have a console panel. This is where you'll be displaying messages from your scripts most of the time, to be able to track if your scripts are working properly, or to catch down any mistakes that occur. We will make extensive use of this panel as we start to code. Those options will be considered as well, so don't worry for now. Since we have several objects in our hierarchy by now, there is one thing that you can do. That is, you can press Ctrl F and search by name. So for instance, main camera. As you can see, there is just one object containing this word combination. Everything else is grayed out. That is, you can press Ctrl F to search, or click into here, or over here. You can always add extra panel into your layout. For this, click on this extension which is present on any of the panels, and click Add Tab, for example, Animation. You can then click on the animation and dock it somewhere else, and of course get rid of it by left-clicking, close the tab. That is, if you get rid of the hierarchy by mistake, don't panic and restore it via this option. You can also press Ctrl 4, or go into Window and Hierarchy. Observe that the shortcut is displayed on the right from the Hierarchy option. Pay attention to them, using them extensively. Just as in 3ds Max, there are several of the debugging representations of the scene view. You can have textured models with the textures applied to them and sampled by the meshes. You can have wireframe to see how the vertices are connected via the segments. Different viewing modes, for instance RGB or alpha. That is, if there is anything on the way of the camera, it will be displayed as white. Otherwise, if the space is completely empty, it will be black. Just as I've shown you before, with the shortcut that we've reassigned, you can get into 2D mode by not using the shortcut, but by simply clicking on this icon right there, and get back into 3D by doing the same thing. We can view the scene with the lighting turned on or off, have the sounds enabled or disabled, and then enable any additional effects. One of them is, for example, the fog, where objects and things get hidden as they get further away from the camera and tinted with a gradient, resembling the fog. Another one is the skybox, which is made out of 6 textures positioned in a cube, the sides of which are located at an infinite distance from the camera around the scene. When those 6 textures are combined together, it will create an illusion of surroundings, such as, for example, open space or beautiful sky, and flares, which are artifacts in the physical real world. They are adding extra realism to our game, and you can have them turned on or off in the scene view. That is, while you're editing your game, you might want to temporarily turn them off or have them on. This animated material currently is turned off, so if you want to have it on, just click on it. You can toggle the view of any parameters or components that you want to have visible or hidden. For instance, you can disable the gizmo of terrain, and you can hide the grid so it's not distracting your eyes. The gizmos for colliders or the lights can be hidden. You only have to uncheck them here. Sounds, flare, cameras, they all can be hidden or turned on by clicking on here and having a grayed out icon. Your project will have to carry different scenes. Currently we're in scene 1, however we didn't save it yet. Press Ctrl S and save your scene for the first time. For the name of the scene you can put anything, something for example like my first scene. Set it to the type file Unity and press save. As you can see, your scene has been saved to the top assets folder. If you desire, you can reposition it and have it reside in different folders. For example, a folder called scenes or any other custom folders. That is, you can store all the scene files just in one folder to avoid a mess. Although scene files are made from the same things and objects which are located inside of the project panel, each one has a different number of things and different positions of them in its own world. This is reflected in the hierarchy. So, for example, if we create another scene and save it in the same folder as the first scene was saved to, that is my second folder, and save it under the name my second scene, this one now, as you can see, has a different hierarchy. My assets, all of other resources are just as they were before with the previous scene. However, the hierarchy is different. The objects in the scene are different, but the access to the assets and the project files is just as with any other scene. Let's get back into the first one and get rid of the first scene. Be very careful when deleting scenes, since that implies destroying your whole hierarchy within the scene. Unity will warn you that you cannot undo this action. However, that's not really true, because if you accidentally deleted something, remember that deleting anything inside of Unity's assets folder, be it a scene, other folder, or any of the files, it's simply an equivalent of simply getting rid of the file inside of my computer. That means that it's going nowhere but directly into your trash can. Open up your trash can and there you go, you can restore it. Once you go into here, into my second folder, the deleted file will still be there. Don't freak out, chill out, and drink green tea along with me. But right now we really need to get rid of it, so damn go away. And let's create another object which is not going to be born via the prefab or any other file that we've imported. It will be just an object native to Unity. Let's go into gameObject light. It's going to be an object of type light and it will be point light. That means that all the light is shining from one point in space. Observe that once we created it, everything else in our scene went dark. This points out all of the areas to which the light does not reach. That's why let's get our light closer to the objects, and if I press F to focus on it, you can see where it's currently located at. We can increase its range via altering the component called light that is attached to this game object. Let's increase the brightness along with it as well. It can cast shadows or be without shadows. They can be soft or hard. Those are the parameters specific to this light component that sits on top of this game object. The game object's name is point light, as seen in the hierarchy. We can rename it in the hierarchy by having it selected and then pressing F2 or right-clicking, picking rename. So I'll type a new name, something like LOL light. I'm not going to go over those settings because they're quite evident. In fact, there are a couple of ones which we should focus on. And if we create for this example the game object, 3D objects plane, then position it underneath of our light and the trees as well, so it serves like a ground. We can scale it up uniformly, and if in the light component of our light game object, if we have shadows enabled, we can alter them with those settings, but the one that I wanted to discuss is currently not available in this rendering mode. But what is a rendering mode, you might ask? Let's discuss it first before we continue this example. Some time ago, legacy Unity was using a rendering path called forward rendering, which was causing big overhead if you had many lights. Since for each single light, because it casts shadows, you had to do a separate drawing pass, effectively painting on top of the scene over and over again for every single light that you have. There were several optimizations taken into the account, and in general you couldn't have shadows coming from more than 2 lights, because additional lights were optimized. However, deferred rendering allows you to have many lights, which are much less expensive. The downside to that is that deferred rendering is not available, I think, on mobile devices, or not on all of them, and it's only available to currently personal computers and Macs. And since our shadows wouldn't work with the forward rendering mode, the older one, to change into deferred rendering mode we have to go into Edit, Project Settings, Player, which we will visit a couple of times in this tutorial later on, and change it from forward to deferred lighting. After this, let's pick our light and observe that the shadows are falling from the light through the trees down on the ground. Notice that the borders of the shadows are not perfect. Their resolution is quite low. This is the setting which you can alter in another options panel, also from edit. We will have a look at it in the next example. For now, let's change our lighting type, so click on the light, from point to directional. This way, the light is considered to be at an infinite distance from our world, for example like a sun or a distant star, and it does not have a position. It only changes the direction as the Earth rotates. As for the shadows, they should be soft or maybe hard. It doesn't really matter for this example. Shadows are a very expensive effect because it's effectively projecting the vertices of the objects onto the surfaces of another object. This kind of effect is quite expensive, but an even more expensive effect would be a real-time reflection. There are some approximations and hacks that has been done to fake the reflection, such as cube map textures, for example, which we'll talk about later, that are quite similar to the skyboxes, for example, and just project the texture onto the surface of the model, faking the reflected light coming from all around. However, real-time reflection does not use a cube map, and you have to find ways around this. But we're talking about the shadows at the moment. So once again, the shadows are achieved by projecting the geometry onto the surface of another geometry. And this happens along with the ordinary projection of points and polygons into the camera, the viewport that you see right here. So besides of ordinary projection and visualization, you have to also do different sorts of projections to fake and simulate the shadows. Of course, this increases the render time. And the problem of forward rendering was that if you have many lights, you have to do this kind of projection for every single light. This makes shadows an expensive effect, and if there happens to be shadows from directional light, Unity will try to hide them after the certain distance. If we come closer to the objects, you can see what I'm talking about. The shadow appears after the certain range has been breached. At this distance you can see them, but if you fly away, the shadows are erased and are not calculated to improve the performance. If you want to change the settings, you can do this by going into Project Settings, Quality, and change your shadow distance to some greater amount. For example, 150. Obviously, the shadows will start to disappear only after 150 meters away from the camera. We can allow for the shadows of only type hard, or we can allow for hard and soft shadows, which are slightly more expensive because you have to blur out the shadow borders. Cascades allow us to have more crisp borders of the shadows that are closer to us than the borders of the shadows that are further away from the camera. It can be the same single shadow, but at different distances, different cascades will be applied. Another interesting thing is that if you have your shadows set to the distance of something like 20 meters, then pick no cascades at all, observe that the borders of the shadow are quite crisp all the way along. The closer part can be even more crisp if we have two cascades. Two cascades work nicely because first cascade, which is applied to the part of the shadow which is closest to the camera, that first cascade grabs the part of the shadow texture which is much bigger than the second cascade. We don't have to talk about the shadow textures at the moment because you're not familiar with this. However, what shadow is the result of projection of vertices which is stored in a texture file. That's why the zigzag borders of the shadow that you've seen before are occurring. Those are the pixels of the shadow texture. And that is because the second cascade is getting less of the texture than the first one. In theory, the shadow borders that are further away from the camera than the first cascade was, those borders will be less crisp. But because at such distance, those shadows on the screen take less space in terms of pixels, you will not see this drop in quality. Anyways, the point that I was trying to bring across was that if you have shadows with no cascades, but a short distance, this will produce quite crisp shadows. However, with the 4 cascades, which makes the first quarter of our shadow quite crisp, grabbing the biggest portion of the texture compared to other cascades, the second cascade is grabbing less texture, and so on until the 4th cascade gets the least of the shadow texture. Because of that, 4 cascades will produce a very nice gradual crisp border of the shadow, but if the shadow distance is ridiculous, for example something like 1000, you can see that the 4 cascades are not helping too much. They're still doing their job, but the point is you take your distance and you divide it by 4. Or 2, depends on which number of cascades you have. The shadow texture has the fixed size. Huge distance of texture will degrade your quality of the shadow, so tend to use appropriate distances. If you use ridiculous distances, shadow cascades will not save your ass. It is up to you, you gotta figure out what you want. Shadow resolution is exactly the resolution of the texture that gets projected along onto the surfaces. After this it will be fixed. It's a fixed amount which you set and then use across the game. You can have medium, high or very high resolution, but medium usually suffices. You can disable vertical synchronization right here. And finally, level of detail, LOD, is a concept specific to Unity and some other game engines. In few words, every object that you import into Unity, you can set it up to have different levels of details. For example, if you have a very detailed rock with 500 vertices, you can have this amount of vertices set to be as level of detail 1. Then the second one will have 200 vertices. And level of detail number 3 will use a third copy of this object, which only has 50 vertices. Obviously, substitute those different representations of the object, those levels of details, as things get further away from the camera. Since if the rock is taking a couple of millimeters on your screen, you're not going to be able to see or really care about its detailization. And the LOD bias allows you to extend this default distance at which the LOD levels get switched to have a higher quality of rendering in the inspector view. We might cover levels of details later on, if we'll need them. However, right now it's out of our focus. Final thing is that you can produce games for different platforms. Current Pro version of Unity allows you to create games as a standalone, so it's an executable file with its own folder, designated to work on Macs or personal computers, just like any of your games, Diablo, Crysis, Unreal Tournament, World of Warcraft. I'm listing my favorite games right here. This kind of build is called standalone. And as well as that, the standard version of Unity Pro can create games for web, where you can see the globe being drawn. That's the build for the web. This version can be downloaded by the websites and distributed across the web. By default, there are 7 different settings of quality. By clicking on the fastest, for instance, you can adjust the settings specific to this category of quality. The fast, simple, and good can all be different. If you don't want to have this quality option available on the targeted build, you can remove the tick. So for example, if I take those, the last 3 options will not be available to the web player. You can only play on simple, fast, or fastest graphics. But for standalone, the environment which is not bound by your internet speed, you can have good, beautiful, and fantastic graphics settings. Obviously, depending on your choice, good isn't going to be necessarily better than fastest, depending on which settings you'll plug into each quality category. When working on games, if you have everything laid out nicely, you'll simplify your work a lot. By clicking on them, you can set up the default one that is used in the editor while you're developing your game. So Fantastic will allow us to have the shadow distance of 150, the one that we've adjusted, and it will have, let's say, no cascades, just for the simplicity and the performance of the viewport. If you want to, you can have just 3 of them, and get rid of the remaining ones by clicking on the trash can on the right. On the contrary, you can add a quality level by clicking on this button. The quality choice by default, as you run the game for the first time, will be corresponding to the appropriate tick on the table of the appropriate build. You can change it by clicking on this black arrow and picking the one that you prefer, like fastest, for example. This is web, standalone, iPhone, Android, BlackBerry, and other application types, such as Windows Mobile. The last 5 ones are portable mobile devices, and those builds are not available with the standard Pro Unity version. Currently, you have to buy an extension in order to be able to build for this specific chosen mobile version. Of course, building for such platform requires a deep understanding of coding, paying a special attention to the performance on the targeted devices. Mobile phones and portable devices, as a rule of thumb, have CPU power, RAM, and their graphics processing unit. Those things are not as strong as the ones on your computer. So ensure that you've mastered building your projects as standalones before you begin to develop applications for portable devices. So those were the quality settings accessible in Edit Project Settings, followed by Quality. There's also Input, Tags and Layers, Time, Player, Physics, and Script Execution Order. Those are the ones that we'll consider in this tutorial. But having created our light with shadows, we still have a couple of things remaining to cover. Once again, those are the parameters from the light component of our gameObject, and specifically, the current parameter that we'll be discussing is the shadow bias. Adjusting the value of the bias property allows us to get rid of the shadow artifacts that will occur on the objects that are casting shadows. We do this by sacrificing the precision at which the shadows are drawn from our object. If we make the bias larger, you can observe that the shadow becomes more distant from the object. However, we get rid of the shadow artifact, those black dots, on the object that's occurring if the bias would be too small. But watch out, because if the bias is too big, you get a quite nasty effect where you have an illusion of object hovering above the surface because the shadow is so far away from the object. As always, find the right balance. Light mapping. Yes, we've mentioned it in a couple of my previous tutorials, and in this one we'll be going over it, but slightly later, so hold on for now. Culling mask. Once you'll get familiar with layers, you can mark an object to be a different layer. For instance, an object can be the layer of terrain, water, your own custom layer, like, I don't know, trees. Once you have them set up, you'll be able to choose them from this list. Currently there are 6 default ones, and you can specify which one this light is affecting. If you want to draw a halo around your light, which is not really fancy by default in Unity, without any kind of extra imported assets, but if you want to do so, you can draw it by ticking this box. When you zoom out, you can see that there is a halo drawn around the object. As you change the color of the light, the halo changes with it. So you can have red apocalyptic sun, or green sun if you're high on drugs or something. You know, pink elephants. Our light that we created is a game object. Our trees that are also in the hierarchy are game objects as well. You can see that when we were creating trees, those 6 objects were belonging to the trees object. That is, they are the children of the trees. this gameObject is empty and it only has two components, transform and light. Because it has a light component attached to it, we can refer to it as light. This gameObject is empty. We can create similar empty gameObjects by, of course, going into gameObject and, you guessed it, create empty. We can rename it to something like myEmptyGameObject or just GO for gameObject. And then our trees that already existed in the hierarchy of the current scene, they can become children of the newly created empty gameObject. All we have to do is click on the trees and drag it on top of the gameObject. Remember that we can always rewrite our prefab by dragging any of the gameObjects from the hierarchy on top of the prefab. If we do it with the newly created gameObject, when we decide to instantiate this object across the scene later on, we will have this gameObject controlling 6 other gameObjects. Fuck, so many gameObjects. Each one of which has a child. That is the tree with their foliage. Yes, so many gameObjects, guys, I know. And what's really cool about them is that those things can contain components. One of such components was light, that you've observed a second ago, and they are basically the modifications that the gameObjects are taking upon themselves. Currently, our empty gameObject that controls other 6 gameObjects has only one component, an absolutely necessary one, which every single gameObject in your scene will have. It is called transform. Transform is a component which contains parameters position, rotation, and scale. Each one of those parameters, I'm talking about position, rotation, or scale, are of type vector 3. This means that they have 3 slots for values, x, y, and z. When speaking about the position parameter, it's storing the precise location relative to the world space. If this position parameter wouldn't have 3 properties, x, y, or z, let's say it has only x and y, then it would be of type vector 2, since it could only store the position of point in 2 dimensions. Rotation is also of type vector 3, and so is scale. That's the standard representation of transform component. And once again, this component is absolutely necessary, so you'll see it on every single gameObject or anything that's positioned within your scene. For example, the foliage and the stamp of the tree that I've selected, each one has its specific transform component. Let's mention the fact that if anything is linked to some certain gameObject and does not exist in the world on its own, so it's linked to something and is a child of something, then the transform component will be relative to its parent, not to the 0th coordinate of the world. Therefore, the stamp and the foliage of the tree that I've selected will have different values that belong to their own transform components. For now, let's get rid of everything except for the camera from our hierarchy view and find out where the 0 of our world is located by picking our camera, then clicking on one of the fields that belong to the position within our transform component and typing in 0. Then press tab to travel to another field. Don't manually click by hand because it takes time. Then type 0 again, tab to go into the Z, and input the value of 0 as well. As follows, this is the absolute 0 of the world, since our camera is not linked to anything. If we create another gameObject, not empty one, but this time having the mesh of a cube, in other words, we're creating a cube, it has some other components, and it has the cube mesh. We've discussed what meshes are in my previous tutorials, including this one as well in the beginning, so that's not a problem for you. Mesh is just a set of vertices that you've imported from 3ds Max into here. But this cube has a component of type transform, it is currently zeroed out in our world, it has no rotation, and its scale is 1, 1, 1, so it's a normal cube. If we drag it outside via those axes, you can see that the parameters change. And we can change them by hand by either typing in numbers directly, or clicking on X, Y, or Z, and dragging left and right. If we position it here at 888, with the help of my marker, I can show you that the world axes are as follows. X is this one, Z is here, and the Y is here. And they are all passing through the point, coordinates of which are X equals 0, Y equals 0, Z equals 0. This cube is positioned in the following way. We count 8 meters along the X, then we count 8 meters along the Y, which points upwards. So now we've went 8 towards here and then 8 upwards. The last coordinate we have is Z. It has a positive value of 8. Therefore, we'll count along the axis 8 meters. So along the Z axis, 1, 2, 3, 4, 5, 6, 7, 8. We could have skipped this jiggly way of counting and could have just drawn a vector from 0, 0, 0 directly to the point in space 8, 8, 8. This jiggly way of representing this is simply to show which kind of mathematical components the vector contains. Its mathematical x component is 8, and so is y and z. The order at which I was showing you does not matter. You can count first y, then z, and then x if you want to. Obviously, this purple vector is the vector 3, and it signifies the position of our cube relative to the world space, that is, to the 0 of the world. Meshes are made out of vertices, and the vertices are nothing but a bunch of coordinates in space. So in theory, vertices can be represented by 3-component vectors if you only need to store the position of the point. However, in reality, each of the vertices carries extra information, such as vertex color, which is also a mathematical component carrying 3 variables, RGB. Vertices also carry information about UV coordinates, so that they know where they should sample the texture from, if they will be given any, and the normal's information. Normal is another vector, and it's usually normalized. That is, it has a length of 1. Vertices also will carry information about animation, the position in space relative to time, how they are affected by different matrices of space, such as modifier skin, the one that we've been discussing in part 6. Skin modifier is nothing but a set of matrices that are mathematical objects, which have an abbreviation of bones. So each vertex has to know all of that information in order to be able to precisely deliver the information of where in the space it should be and in which state. That is, simple position would not be sufficient to represent the vertices of the mesh in their full glory. That is the first component, transform, that belongs to our cube gameObject. As you see, there are other components that are default to this gameObject, cube. There are other extra components which are available. Specifically, there are box collider and mesh renderer. There is a cube mesh filter. This is the component that contains information about all the vertices, etc. Box collider, which helps us to detect collisions in the space of the world. The box collider component is using the box collider object as one of its variables. You can edit this box collider component to be something different. For example, you can have it a sphere collider, capsule collider. If you have a complex mesh, which is for example concave, that is bent inwards, you might require something more expensive, which is the mesh collider. Because our current game object is a cube, box collider is most appropriate to it. And finally, the mesh renderer will be carrying information about materials. Is the object to which this component applied going to be casting shadows? Is it going to receive shadows from other objects? And is it using something called light probes? Light probes contribute greatly to the efficient simulation of lighting and can be used to achieve such effects as color bleeding, for example, in real time. Currently, on our game object, we have 4 components. Default material diffuse is not a component. It's simply a link to the variable which is sitting inside of the mesh renderer component. So mesh renderer is a component, and material is just a value inside of the variable called material, the variable which belongs to the mesh renderer component. I can show to you that indeed rendering is a component, and material is not listed there. You can stick those components on any game object. Those components can be applied to any of the game objects that are to be made. So you can stick mesh filter, mesh renderer, which has information about materials. Mesh filter keeps information about the vertices and the mesh which is supplied into the current game object. You can have different effects like a particle system, a halo, lens flare if you want to cast lens flare from your object. It does not necessarily have to have a light component attached to it for the flare to be working. You can have different components that belong to the physics group, such as rigid body. If you have this component attached to the game object, you then can supply information about mass, the inertia, how it should react to the collisions of other game objects colliders, etc. You can add any kind of collider components to your game object. Even sounds can be attached to the given game object. Parts from the UI category can be also used, for example the graphics user interface, or in other words, heads-up display. Those are components. If we want to add them onto the selected game object, we can simply go into component, then pick the required one. I'm gonna pick halo. Now when we have this component attached to the game object, you can see it drawn around our cube. Let's change its color and the size as well. If we want to disable this component, we just need to untick it. It is still present on our game object, but it's not working temporarily. You cannot disable some of the components. The best example for this is transform, since it's very necessary. And you cannot disable mesh filter. However, you can get rid of it, just as you can get rid of mesh renderer. If you get rid of the mesh filter component, your game object will assume that it's carrying no information about vertices, because it will not have information about them. That way the information about your model will not be able to be delivered onto the screen, and the object will not be rendered. And if you get rid of the renderer, which grabs the points, assigns material to them, and modifies their visible properties, if you get rid of this component, you will have the points, but they will not be processed, and you once again will not see the geometry of the object on your screen. And finally, every single object can be tagged with an appropriate tag. So if we have several cameras in our scene, and don't be surprised by that, because you can overlay them. For instance, one camera can render the above of the scene, and output everything that it sees into the top right corner of your screen, while the main camera that is located in line with the head of the character will be showing the major stuff that happens around your character inside of the world. So you can have different cameras, along with the several of the game objects. Like let's say we have cubes. Now we can group them up together, not actually linking them between each other, but selecting them and tagging them with an appropriate tag. If there is no tag in here that we would like to use, we have to create it. We can have arbitrary number of tags. Currently we have one tag in here. We can specify that we want to have like 4, but it doesn't matter. Every time you add a new one, you'll have an extra slot to write your new tag into. Currently we can say that, okay, geometry, or my geometry, whatever you want to have, and then, for instance, my cameras. From now on, those 2 tags will be available to us, as well as the default ones that you saw earlier, like a player or camera, for example. We can select our cubes, and currently they are untagged. Let's tag them with geometry. As for our cameras, let's tag them with the tag myCamera. Those tags can be very handy when working with scripts, since you can refer to the objects by filtering them by tag, and checking if the object actually belongs to the specified group, like are they belonging to cameras or do they belong to geometry group. And the final thing is that you can have layers. Layers are fixed in number, you cannot have more than a set amount. Currently, there are 5 reserved ones, which you cannot touch. The first one that you can alter is the number 8. Those layers, and you can currently think of them as masks, although it's not 100% true, those layers are tied directly to the number of bytes that you are using. Byte operations are very cheap, and because of that, Unity makes use of them and incorporates them directly into layers. Let's call the layer 8, for example, custom terrain. And then if we create a gameObject, 3D object like plane, we can assign it a layer of a custom terrain. And then if we cast rays and test for collisions, we can have different colliders that will be reacting to our clicking, belonging to different gameObjects that are all around this plane. But if our plane has its own collider and it has a layer of terrain, when we do collisions, we can filter and just say that we only want to click on the terrain and ignore everything else. So anything else, filter it out. You can make everything like this happen via the script. Our plane is currently marked with the layer custom terrain. Its tag is the geometry, and it's an easy way to determine which group this object belongs to, but layers are a super efficient way of filtering out data. Just as with each of my tutorials, I'd like to show you a couple of things that I found interesting. It is always helpful to know something like this. Each one of them belongs to a different subject, but if you know them, you'll be one step higher. The first trick is that, as you know, from lesson number 4, for example, or number 5, because character was using normals that were pre-baked from a higher representation of the character to the retopologized one, because of that, his UV patches had to be laid out separately from each other, and each UV patch was sampling from a separate spot on the texture. But, in the case of environment, you can make similar object sample from the same area on the texture. I call this kind of texturing homogeneous texturing. If that's the case with you and you decided to take this approach, along with homogeneous textures, you might pick homogeneous normal maps as well. In other words, dirty normal maps, which we've been talking about in the end of tutorial number 4. The benefit of such homogeneous textures is that you can texture as many objects as you want to with this texture, and they don't even have to sample from the same area of the texture. Let's say you have a single texture, the homogeneous one. For it, in order to be homogeneous, it has to be tileable. That way, when you force different objects to sample from it, their UV patches can be as big as you want to. Even if some of the patches do stick out from outside the borders and are out of UV boundaries, that is the 0 to 1 range, even if this happens, you'll be sampling from the opposite side of the texture, and because it's tileable, you'll not notice this transition. Just as we've been discussing in tutorial number 4 somewhere at the end, when we were talking about tileable textures and dirty normal maps. Along with this texture, I have a dirty normal map, which accompanies it usually. I have cracked concrete N, and I'm using the notation of -N just to show that this texture has a normal map tied with it. And there we go. This is the normals for this homogeneous texture. I've shown you how to produce those dirty normal maps that you see in front of you, also in tutorial number 4. But the matter of fact is, if you have some kind of crate, his sides can sample from here. If you have different stones, the stones can be sampling from here, a second patch of a second rock can sample from here, and so on. The only problem with such homogeneous textures is, although they are very easy to use, you have to watch out for seams, because in this case, if the rock is unwrapped like so, you'll see a seam where the texture doesn't line up on this side, for example, with this one for this UV patch. When working with homogeneous textures, hide your UV seams on the models which will be sampling from them. This is especially the case when working with secondary textures like normal maps, because if you have a seam on diffuse, it might not be as prominent and might not jump into the eye as much as the seam from the normal map will be. Sometimes that's not really avoidable and there is no way to hide your UV seam. In such case, put it on the back side of the object, the one that probably will not be facing camera in the game at any time. Another subject, aside from the homogeneous textures, are texture atlases. We'll be mentioning them quite a lot. It is a single texture, which in itself combines several other smaller ones. You can see that I have 4 homogeneous textures here, the tileable ones, and judging by their look, you can assume which kind of surfaces they can be used to texture. For instance, the one on the bottom right can be used to texture the floor, the ceiling, or even rocks from the mountain. On the other side, 3 other ones are more like man-made, and so they will be used for pillars, walls, in other words, parts for the buildings. What really fascinates me about game development is that it's a constant fight for resources. On one side, the textures that you're using shouldn't be too big, otherwise it will take a lot of time to load them, and they will be consuming a lot of memory. However, if you have too many of them, you'll have a huge drawback, because this will put a strain on your GPU, the graphics card. So many textures is a bad idea. It is better to have several big ones than many small ones. For instance, it's a great idea to combine those 1024 textures into a single 2K one.
The problem in this case is that you lose the ability to tile the textures.
But this is not really a 100% case, because there is still something that you can do about it. We will return back and talk about this texture atlas in a moment, because for now there is another example which is more applicable at the current state of tutorial. That is, have a look at which objects I have here. Because you already know from the atlases, I can say that each one of them samples from a specific portion of an atlas. Speaking of which, I can show you by pressing M and opening my material editor. We can click here or go into maps, click on diffuse, and the atlas is right here. It's a 2K texture, once again, but observe how many slots it has. I can texture so many objects with the help of those textures.
Each of those squares is 512 by 512.
And because of the way I use them, my objects are still pretty damn detailed. Let me quickly apply this material onto, let's say, this jar and a couple of other objects. Notice that as I'm applying this material to separate objects, they are of course colored differently. Each object has its own UV layout on the space of the UV table, which is different from other objects' UV layouts. And to be fair, it's such a pleasure to just be able to drag this texture and seeing how it nicely wraps around the object. But of course, I had to spend time before that and unwrap all the objects. The example that we're working towards is the following one. Let me quickly select this jar and isolate the selection, then open up the UV editor, and for that we have to stick a new one on top of it. If we open it up, you will see that the part is sampling actually away from the table, but it's an equivalent of it sampling from somewhere here. The UV table tiles by default. And just for the simplicity, let's press on here, the absolute transform mode. We've been doing this a lot in tutorial number 4. And press 1 to offset it 1 unit to the right. Let's then quickly pick the texture. I'm using Atlas number 3, or you can browse for the required texture if you want to. Then, as you can see, I got my different parts, sampling different pieces of the texture. I've just cut out a piece of the video in order to cut down on time of me selecting those parts, because as I collapsed the stack, I lost the ability to expand towards the seams, because the seams got written into the model, so I cannot use this button. I had to select my pieces manually in the viewport, but here it is. I have 2 similar UV patches, which are lying on top of each other, and are sampling pretty much from the same space on the texture. If I press F2, just to show you what's happening at the background on the texture, without the red selection, and then untick map seams and peel seams as well. It looks faceted because we didn't stick it on top of editable poly. So to quickly fix it and to have a smooth representation of surface, I'll quickly apply editable poly and we'll drag it downwards underneath the unwrap UVW. I will then collapse 2 and press yes. In editable poly, I'll press F4, then we'll press Ctrl A, go downwards, and then those polygons that are selected, I'll assign a group of 1 to them. I'll press 6, or we'll click here to deselect my polygon selection, and it seems like it didn't fix the problem. So perhaps if we go into the vertex mode, press Ctrl A, those vertices are probably not welded together for some reason. So let's just press weld, and yes, it did fix the problem. Now I can press 6 to exit any editing regime, go into unwrap UVW, opening the UV editor, and then quickly selecting parts once again. There we go. We got 2 different patches, which are sampling from the same space on the texture. They are using the homogeneous tileable texture, and because of that, I'm positioning the UV patches on top of each other. Where they join, over here, if I press 2 and select those 2 edges, you can see that it actually happens here. I was talking about the seams before and that you should watch out for them. Here, you can see that although the 2 UV patches are split, you don't see the seam right here if they're lying like so. The explanation of this is that those polygons, this one and that one, are sampling from the exact area. This is how we avoid revealing our border. If we would position our UV patch somewhere else, like here for example, just a couple of notches to the left, you'll start to see that there is a seam right here, which would become even more prominent when we apply a normal map. But if their borders are aligned, like so, then there won't be any problems. Because this is just one half, you also have to care about the other side. And you see that I follow the exact same strategy right here, and also aligned the vertices to the best ability. Sometimes it can be hard, for example if the circumference of the object is not made of even number of polygons. In this case you have to watch out and stretch your parts reasonably. the main idea is to hide the seams, but don't overdo it. Try to position this seam, the edge, somewhere where it will not reveal a reflection, since storing those UV patches like so is basically an equivalent of mirroring one side to the left. So with bad luck, you'll have a mirroring effect like this one, for example, right here. Try to position your whole group somewhere where the seams are not as visible. In my opinion, this place was pretty good. We don't really care about the inside. Nonetheless, if you want to, you can pay attention to it as well. I would also like to show you in real time how to unwrap something as simple as this log, for example. The thing is, our texture atlas provides stylable textures, but they are quite small if you think about it. 256 pixels by 256 isn't a very big amount, so we have to use it wisely. But you might say that the log is quite long. How are we going to be able to stick this whole thing into it? It's all about the same trick as with the jar that I've shown you before. Let's quickly isolate the selection, and if we apply our texture atlas, as expected, you can see that it's applied incorrectly because the model doesn't have UVs supplied to it yet. Let's apply a plain white material to it for now. Press F4 just so that we can see the wireframe. Make sure that the show seams, in fact peel seams, is what we need. They should be turned on. Let's press 1 in order to travel into the vertex mode right here. I will expand this for my ease of working, and then we are interested in this option right here, point-to-point seam. Remember that if we are using such homogeneous textures, try to put the seam somewhere at the part which most likely will not be facing the camera during the gameplay. But in the case of a log, it's pretty round, so you cannot really predict which part will be hidden, because you can turn it around. And then let's quickly lay a circumference for this part right here, and the same thing right here. If we press 3, I'll press F2 to show you the selection, and click expand towards seams. We can do quickly pelting, start pelt, and then go into settings and relax by the face angles to have a more gradual relaxation. And there we go. We can press commit. I'll leave this for later. And then if we pick for our background our atlas texture, it's a bitmap. I will use the quick link. Here it is. Now I want our log to sample from a wooden texture somewhere from here. But the thing is, if you scale it down too much, just that it fits completely, you'll have a very crappy resolution of the texture. So have a look at this. Yes, like so we've stick our part inside of the texture, but if we press F2 and apply our material to it, the atlas one, notice that the texture looks really crappy. This is exactly why when modeling this log, I connected the circumference with a segment. If it's not there, you can quickly go into the editable poly, press 2, and then connect those segments with another one. I'm using shortcuts, and I've been talking about how to establish shortcuts in tutorial number 5. They are really handy when working in editable poly, so make sure to check this tutorial out. That way we've divided those polygons into 2 parts now. But be careful, don't subdivide it too much, because you gotta pay attention to the polygon count. In this case, it wouldn't be wise to go above 30 polygons, because the building in the center of my map will be using quite a lot of logs, not necessarily for walls, but for pillars, for different borders and fences. That's why I'll try to keep it reasonable. But 3 stripes of polygons is fine. That way, if we go into Unwrap UVW, open the UV editor, we now have our UV patch subdivided into 3 parts. Let's select everything. I'll press 3 to be able to select within the polygon mode, and then scale it up. We want to have it as big as we can, but you can see that we won't be able to scale it up more because you'll start to pop out from the top borders. So I'll scale it down to this amount. Now we can select those polygons, and before we do anything, let's press 1, grab the borders along which we'll be mirroring our parts, and then click Align Vertical, and align vertically those ones as well. Now we can return back, and right-click, Flip Horizontal. We can then detach it, and position it somewhere here. Because we've aligned our vertices vertically, it's very easy to position them precisely on top of each other. If you want, you can press Ctrl S, or if this shortcut is unbound in your case, just click here and then snap towards pixels or vertices. Then repeat the procedure for this part as well. Press Shift to slide along the axis. If I press F4 in my viewport, you can see what I was talking about. Now our texture looks much more detailed than previously, but because that's where we have our seam, we cannot really see it, but we get a mirrored effect. So try to find a better spot for your texture by dragging it around. Excellent, this one is best, I think. You can see that we have a problem here, and that's because I dragged it way too high. We get a seam right there, but because I'm using a tileable texture, it will disappear as soon as I will scale up my UV patches, just so that the borders, upper and lower ones, are touching the appropriate parts of the texture, the upper and lower one as well.
In fact,
this specific little texture is not tileable. There is no point in scaling it so that the upper parts touch the upper part of the texture and the lower segments of the UV patches touch the lower one, because the texture itself is not tileable. But in this case, we can repeat our strategy once again by grabbing those 3 vertices, aligning them horizontally, grabbing the 3 polygons above them, flipping vertically, and then dragging them downwards like so. This is what I was talking about before. Since the circumference of this log is not consisting of an even amount of polygons, when we try to flip them and fold them vertically, you can see that this patch consists of 3 polygons and this one consists of 4. So what can we do about it? There is one thing. We can select this tool, grab it by the bottom left corner, press shift and drag it downwards, but not all the way, because if we do so, we'll stretch one half too much.
instead we want to scale it up a little bit
And then grab the other half.
and scale it down slightly.
I'll press F2, we'll select the other part. It consists of 4 polygons, and then just as planned before, I will grab it by the bottom right corner and we'll scale it upwards like so, just so that those seams are meeting here. They are also meeting here, and because it flipped it over like a cake, those 3 parts are all sampling from here. Notice that there is no seam here at all, and it's not the case for the upper part as well. Yes, we get mirrored parts. Because of that, let's find a more appropriate place for it to sample from the texture. Don't forget that you can always rotate your UV patches, but in this case, it's not going to be really applicable, since the bark of the tree doesn't follow it that way, it's only one directional. This seems to be the best bet. It's just a matter of fixing those end parts, which are actually, I don't know how it's possible, but I think they arranged themselves from the first catch. Yes, we got them sampling from here. Anyways, it would be just a matter of selecting them and doing a planar projection, then going to Pelt, opening up settings for relax mode, closing the Pelt map, and then just relaxing our polygon. Then we can scale it down and position it somewhere to sample from one of those endings. So it's a different texture, but because it's a wooden texture, we can combine them and you won't really see the difference. In fact, it was better before I touched it, so I'll position it back. And there we go. We got a log without any kind of seams, and we are making the full use of our 256 texture. If we want to utilize this range even better, we can open it up and then scale up our part by even a bigger amount, so that it grabs a bigger resolution of the texture. I'll deselect my snap mode and we'll scale it up to my best ability. In fact, I'll grab those vertices and we'll just drag them to the left like so. Watch out so that it doesn't go out of bounds, because if this happens, obviously you'll be sampling from this part of the texture. And there we go. Very crisp and very sharp texture, just from 256 one. And it's a homogeneous texture, so we can force anything to sample from the same area as this log was. In addition to the previous set of tips, in which we've discovered atlases and discussed, as I call them, homogeneous textures, this example shows you what you can achieve with the textures that are tileable, but which are gathered in an atlas. As you can see, this is just a set of bricks, which is used around the corners to add extra detailization to them. Just as jars from previous example, they are sampling from some spot on the atlas, and the way I made them is that I just constructed one efficient block, quickly unwrapped it, then collapsed all the stacks, then quickly distributed it as other few bricks. Because of that, each one has exactly the same layout of UVs as the first brick, and they're all sampling from the same spot on the texture, the homogeneous one. That texture has also normal maps, also homogeneous ones, which accompanies that diffuse texture. When I was happy about their position and rotation altogether, I've attached them to one editable poly, quickly went back and culled all the faces which are not going to be seen. This helped me to reduce the polygon count, and as well as that, I tried to delete some of the vertices. The vertex count was also improved that way. But to extend on the previous example, when we were talking about jars, atlases and tileable textures, here is the wall. If we're going to modify and apply unwrap UVW, just as always, open the UV editor, you will see that I have 6 squares, all sampling from one specific spot on the texture. This texture is an atlas one. It looks like this. Because it's now an atlas, we cannot grab our parts and just scale them up indefinitely, since if we decide to go with atlas for performance, we are losing the ability to tile. Now your parts have to stay exactly within the range of this texture, with the specific spot on this texture, and if they go outside just a tiny bit, they'll be starting to grab another part of the texture. That's why it's all about the balance. If you want your wall to sample texture 3 times in a row, that is have 3 tiles, you have to subdivide it into appropriate number of polygons. This results in a bigger mesh, and if before that you would only have a box with 6 sides, 6 polygons, now you have 12 plus 4 due to the polygons on the sides, and plus 6 above and below, resulting in 22 polygons. But This way we will help greatly our GPU because it won't have to spend its time switching between textures. They are all packed up nicely, and each square is sampling its own piece of the texture over and over again from this spot. You have to be careful and position your edges so that they are lined up with the edges of the texture piece. That way you'll have no seams across the wall as your tiles are repeated. If there is no possible way to fit your UV patches into the UV layout as it is, the square one, let's say your parts are rectangular or circular, then follow the previous strategy with the jars, where you mirror your UV patch along a seam like we did with the log, and make sure that the objects are joined within those seams across which you mirrored. Just like in the case with log. We will be talking about atlases and productivity slightly later in this tutorial, but this is a very important subject and it's best to start learning now than during some other time. Have a look at my parts. You can see and recognize all the textures that I've been showing you a second ago with the atlas. They're all quite repetitive, but the way the objects are shaped and the scale of the texture, the way they are sampling it, they are all adding something different to the object, and they don't look the same. Yes, they do look like they belong to a similar family and that they are made from the same material, but each one is special in its own way. Those are the parts that will be used to build the underground catacombs in my game. You'll see them later on in this tutorial. Of course, this implies that I can texture every single model that you see in here with just one texture, excluding maybe those tunnels inside of the earth. But those meshes can be textured with just this material. Tip number 2 is, have you ever wondered why as you bake your normal maps from a high representation to the retopologized version, why do the resulting normal maps don't seem to line up together where the seams are? Like for example, if you have a look at this monk, on his belt you can see a clear division from the normal map, right there. That's where the seam lies, and as we unfold the belt, it's pretty much a rectangular piece. And to be fair, in the game engine, you won't notice this seam. But why does it occur, you might ask? It happens for one simple reason. I will not be messing around with this character because I've already finished modeling him and texturing, and animating as well. However, I can show you how the principle works in another scene. Right here, I want to bake the normals to this cylinder from the deformed one. And I've already got everything set up. I've got 2 copies, and the thing is, after we bake normal maps for this cylinder, there won't be any difference in normal mapping. You will not see the normal map seam. Observe the following. Let's save it on the desktop under the name normal map no seam as a JPEG image. Then render. And for the second cylinder, let's repeat the procedure, but this time save it under the different name, normal map with seam. If we go back to the desktop and compare the results, you can see that they are looking pretty much the same. But as you can see, the second cylinder has a different UV layout to the first one. And if we have a look at the first cylinder, we can assign to it a material, and for the diffuse color we'll pick our baked normal map color. As you can see, there is no seam. This is however not the case for the second cylinder. To it we need to assign a different material with its own diffuse texture in order to show you the example and the difference between 2 textures. This texture will fit specifically to the UV layout of this cylinder. Clearly there is a seam right here. In this case, with the first cylinder, there was no seam, or a very minor one, like really tiny. But here it's really prominent. As you might have guessed, 3D normal map is representing bumps, uneven surfaces, with 3 colors, RGB, which stand for 3 axes. As computer renders triangles, points, and outputs them to your screen, before he does it, he calculates which color the triangles should be. And for that he samples the texture, the normal map one, and judging by the color, he modifies the angle at which the ray coming from the light falls at a given pixel. Depending on red, green and blue, it figures out that this surface has got its normal pointing in a different direction. Faking the look of objects that way is much cheaper than faking them with specifying different coordinates in 3 dimensions with vertices. Because when working with normal maps, all you have to do to figure out which direction the pixel is looking at is just to sample the appropriate area on the normal map texture. But if you have vertices, you don't have to sample a texture, but there will be so many of them, each one of which carries all sorts of information like position, color, animations, how it's affected by matrices, etc. It has so much info that your game wouldn't be able to run at a rate at which it runs when it uses normal map. But the lesson here is normal map seams will occur in the places where the UV seams are not lined up, because the coordinate system, the axis of the normal texture, are fixed. When baking normal maps, computer does not know that this patch is joined with the previous one, and that it's exactly the same one but slightly tilted. It just maps normal map top to bottom. However, just like I said before, this seam is not visible in games. But if you ever wondered why it occurs in 3ds Max after the bake, this is the cause. Following the idea of the 4th tutorial, speaking about buildings, there is one strategy to follow when exporting your building parts to Unity. Remember that in Unity you cannot mirror objects. You can achieve this effect in there by setting the scale to the negative number, but when applying normal maps to such models, they will look inverted. This problem will cause you to search for scripts which will uninvert the normal maps. But it's much easier to pre-mirror the objects in 3ds Max and then export them as two separate FBX files. That is, grab all of your parts and mirror them as a copy. It does not really matter in which direction, but in my case I prefer to do it in Y. Once you've mirrored it in any of the directions, you can achieve any other position that you desired before by simply rotating the object. That's because in this world there are two states, mirrored object and not mirrored object. It does not matter in which axis you'll mirror your left glove, as soon as you mirror it along Y, X or Z, it will become the right glove, etc. Having your parts duplicated, you can offset them to the required position, and it would be actually a wise idea to rename such objects, each one to have _m at the end of their name, to signify mirrored part. But you cannot do this one by one because it will take so much time. Following the principle of the tutorial number 6, you can select all of them, go into Tools, and rename objects. You can unclick base name because you don't want to modify it, and then for the suffix, put _m and rename your parts. It is very important to name all of your parts appropriately, because this will simplify your life when you quickly need to sift through the objects and find the required one in Unity. Because I've already done this process before, I have now _m, but you got the idea. Grab your parts and then export them. In fact, in Unity, sometimes you can see a strange anomaly happening, and I have no idea why this occurs. But if after you've exported your models into your game engine, if the model looks flipped inside out, you have to go into 3ds Max, press 5 to select the element, and as you can see, this selection says that the polygons are flipped inside out. To fix this, press flip, and they should be okay. However, the problem might still occur in Unity, and there are two factors to watch out for. They are both related. First one is to have a look at if the model is flipped inside out. Judging by that, a second problem might not be there if the object, let's say, was not flipped. But if it was flipped, most likely the scale of the object was flipped as well, and now its scale in Unity will be negative. If you attempt to change the scale to be positive in Unity, you'll simply mirror your objects backwards, just like they were on here. This can only be fixed if this problem occurs. It's quite rare, but if it does occur, you can select your parts and export them in the object, for example FTL. After that, you can import your FTL object back into 3ds Max, then export it into Unity as an FBX or OBJ format, and then the scale will be okay inside of Unity. Think of this FTL format as some kind of waypoint. Once again, you only need to do this if your object was flipped inside out inside of Unity, forcing you to come back into 3ds Max. To finalize this example, export your building parts in two states, if you need to access their mirrored copy later on during the building process in Unity. If you don't require mirrored parts and can survive with just rotating and repositioning your objects without the mirrored copy, then don't export this second mirrored version of the objects. Watch out for flipped versions of mirrored objects when you import them into Unity, and FTL format will help you if you encounter this problem. Beware though, since after you export your models in an FTL format, it will put headers and will apply some kind of nasty renaming of the objects. So try to name your objects after you've tested that they work fine in Unity. Always check that your parts are working inside of Unity, the mirrored ones, before finalizing them and renaming them appropriately, because FTL can screw up their names. In this example, I've made a box, which I've converted to become an editable poly, and then I just mirrored it along the x-axis or y-axis with some offset. This action produced that box right here, with a 002 ending. With those parts that I showed you a second ago, when I tried to export the mirrored parts into Unity, mirrored parts became flipped. You might say, okay Igor, just stick a normals modifier, and then simply unify normals and flip them if you need to. This solves the problem, but only in one way. Your faces will no longer be flipped. However, inside of Unity, I had the problem where the scale was -1. So I had to come back here and go through the FTL routine. But in this case, I have this object, which is mirrored. If anything bad happens to it, it's only this object which will be affected. Since the third one, which is a copy of this one, I grabbed it and did reset xform on it. But once again, reset xform didn't help me with the building parts. But still, this object has reset xform, and that's why it's called box03 mResetted. If we export them into Unity as an FBX format, if I quickly jump into Unity, you can see that I've already brought them into Engine. Don't worry about Unity's interface because you'll learn a lot in just a few minutes. The moral of the story here is that we have our box, the initial one, then the mirrored one, and the reset xform box as well. The normal box has a positive scale, and so is the mirrored one. Reset xform one has also the positive scale, and this shows that mirroring objects in 3ds Max, pre-mirroring them that is, gets rid of the problem where you get negative scale, such as for example in Y in this case, when you try to mirror it in Unity. Never mirror in Unity, pre-mirror in 3ds Max, and I think in my case when working with those building parts, that was only the problem because they come from 3ds Max 2014. And as you know, I'm not a very big fan of that version. It has so many bugs. That's my guess on why this problem was occurring with them as I try to mirror them. If you are new to game development, you might be asking yourself a naive question. Why can't we make a whole game inside of 3ds Max? 3ds Max is just a toolkit for creating meshes, objects. However, it's not relying on establishing any kind of connections between objects. Yes, it does support parameter wiring and reaction manager, but those things are only altering the parameters that were given by default by the Autodesk to you, like transform, color of the material, etc. If you do something to one object, if it was parameter wired to the other one, the second one will be affected by the change in the first one. So indeed in 3ds Max there are relations between things, but 3ds Max's scripting and parameter wiring is a system which is not even close to being as flexible as the coding provided by game engines. As well as that, 3ds Max is not able to produce a standalone application which will contain those relations between objects that were described by you as a programmer, thereby making a game. 3ds Max is an excellent tool for shaping out the look of your world, but the relations between things inside of your world, the gameplay, it all depends on Unity. Now my plan is to explain to you how coding fits into Unity's interface and how can we utilize it to be able to control things inside of our scenes. Your code, or how we used to call it script, is a file containing commands. You can code in different languages, each one of which has its own syntax, like for example Russian and English. However, every single language that you pick will be working from the same principles. For instance, languages such as C#, C++, Java, Unity Script, Boo, F# and Python, they are all centered about concepts such as functions, properties, numbers and classes. So the words are pretty much the same, it's just the way of how you arrange them. So far, Unity provides you 3 languages to work in. It's Unity Script, sometimes people refer to it as JavaScript, C#, which we will be building our tutorial upon, and Boo. Personally speaking, when I started learning to script inside of Unity, I began doing this in Unity Script. And looking back there, it was a mistake for me. It was important for me to kickstart, and everybody said that for beginners, all languages are pretty much equal. Back then I didn't take programming seriously, but soon enough I realized that I love it, and that I need more flexibility than Unity Script provides. That's why I started learning C# and quickly found relations between those 2 languages, but it still took me some time. So it's best to begin learning straight the C#. As well as that, it's closely related towards C++, that advanced programmers are using for coding in most of the games at the moment. And it's also believed that the file sizes are smaller than if you'd be writing in Unity Script. The language itself is more demanding than Unity Script in terms of syntax, but because of that, most of the time it's more optimized. So what are the scripts? They are like a spirit inside of your object. Their purpose is to make something with the object, to access its components, to access the components of other objects, and to tweak parameters inside of those components. Because I'm making tutorial for everybody, I'm not going to jump straight away into hardcore coding, but I will start out slowly, explaining to you basic concepts, and then as we proceed further, you'll begin to see the relations between things. It's very much like learning a language. That's why we say that we code in language. It's pretty much the same as the normal language, in terms that you start to learn and you don't know enough words, enough combinations of words to express your thoughts, but as you gain more knowledge and your own personal vocabulary grows, you begin to understand how to express your thoughts and tell the engine what it is that you want from it. As you can see, this is a more complex scene than the one where we were working on the trees. We'll be looking at it in more detail closer to the end of this tutorial, and currently we are just gonna stay in this zone. We're not gonna be manipulating the objects yet, because we still need to figure out how coding works. So it's just gonna be a decoration for your eyes. Speaking of my scene, my hierarchy is filled up with many objects. Different buildings, characters, lights and cameras. And my layout inside of assets is as follows. I'm keeping different parts of my scene inside of specific folders. Some of those folders play a particular role in specific areas of coding, such as editor and resources, but we'll be looking at them later on. If you name your folders for casual storing of objects, make sure not to call them editor or resources.
because those are the folders reserved by Unity. Just to keep things tidy, I keep my materials inside of materials. For many of the objects, shaders written by me inside of shaders. The standard assets contain different things that are supplied by Unity, and other folders also containing different objects. Let's create another folder, so I'll right click on the assets and let's name it tutorial 8 scripts. If we double click into it, you can see that we are positioned right here inside of our newly created folder, and this is what the folder contains. Nothing so far. To create something inside of it, let's right click and we'll be making a C# script. We can also make Boo script, just like explained before, and JavaScript, the one that I decided to learn first. It wasn't the best decision, so let's go with C# script. We can call it first script. Notice the capital letters and their notation. When coding inside of C# or Unity script, it's important to refer to the names of the objects just like they are written. That is, first script starting with a little f and first script starting with a big F are two different names. It is very important to pay attention to the upper and lowercase letters. We would like to double click on it and open it in the Unity's editor for coding called MonoDevelop. But if it doesn't work for you, you have to go into Edit, Preferences, External Tools, and that's the one that we've been looking a couple of minutes ago. Here you go. This is the one that we're going to be using to write our code inside. Usually it's MonoDevelop built in by default, but if it has bugs, you can browse for a specific shortcut for MonoDevelop. As we double click on it, we get this very familiar window that majority of us saw a million of times probably already. And notice that the script is called firstscript.c#, which is an extension of the script. And the whole script will be happening in a class firstScript. It is very important that this name corresponds to the name of the script. Otherwise, you'll get an error thrown at you by Unity. Because I'm explaining to you everything from beginning, I'm assuming that you don't know anything about classes. But don't worry, you will soon be familiar with them. Let's minimize this window for a second and click on our gameObject with the component light. As you can see, this gameObject has a name pointLight with a space in between. It has a component transform with a couple of parameters, each one of which has 3 values. And it also has got a different component, light. It also has got different parameters, and every single one of them has some sort of a value assigned to it. The component is currently enabled because of this tick, and we cannot enable or disable transform, since it's very necessary. It has to be always on by default. We can attach our own component, and to be specific, the script that we've created a second ago. To do this, just click and drag it on top of here, or you could have done the equivalent thing by going into Add Component, going into Scripts, finding your script by typing in name in here to quick search, or just glancing on the list and picking up the correct one. Notice that for simplicity and the ease of viewing, the name of the script has been split into 2 words because Unity understands camel case. This is not very handy because you might have somehow 2 scripts, one with the first letter F being the capital and one with the lowercase, and then you would have 2 scripts right here with exactly the same name. But it's what we gotta work with, so just left click on it and you got your component attached into here. Let's jump back into MonoDevelop and see what else we can do with this component. Let's get rid of this piece of code for now and talk about variables. Just as back in Unity you could have seen that the light component has got things like draw halo where you can put a tick. It has got different sliders and different fields for inputting your numbers into. Field is just this kind of rectangle, the input box. We can add similar things to our script, to our component, so let's do this now. Because we're going to be making variables, we have to decide which type each one will be. A variable is like a little sack or a container for storing something. For example, you can have a container which is a box, a sack, a bowl, or even a teapot. Each one of them is used for storing different things, but each single one of them can be represented as a variable, or a parameter in other words. In coding, there are different types of variables, the most important ones of which are bool, that is boolean, int, which is an integer, float, which is a floating point type, string, char, vector3, and other things. All of our code, for now, will be happening just inside of this class, and class itself is also some sort of description of a type of container, but we'll be talking about this later on. For now, the class begins from this bracket and its influence ends over here. So anything that we write has to be inside. Let's press enter a couple of times to extend our range of working and declare our first variable. We first have to declare a type of the variable, and for now let's write bool, that is, we want a container of type boolean, then put my variable, or my var, for instance. Just as in the case with Unity, with the folders with reserved ones, in C# you cannot use a couple of keywords for names. That is, you cannot say, okay, I want to have a type boolean, and I want to refer to my variable as vector3. This is incorrect. you would want to put boolean and then your name, which is my name, something that's not reserved by the language itself. After each statement like this, we have to put a semicolon. That is, if we want to declare a second variable, we have to put a semicolon and then declare another variable. Pressing enter here and going to the new line is just for our simplicity and the ease of perception of our code. Computer will not care if you write it like this, but it's much easier to perceive and to visualize your code. It's much easier to work inside when everything is laid out nicely. We have to register the script for Unity by saving it, pressing Ctrl S. And if your shortcut doesn't work, you can do it manually by going to File, Save, and also inside of Tools, you can go into Options, go into Key Bindings, and check for different controls and for different shortcuts. So currently we have two variables here. This one has name myvar and it's of type boolean. This one has a name someInt and it is used for storing integers. Boolean is the type which is used for storing variable which can only have two states. It's either true or false. If we save the script and go back into Unity, Unity will be thinking for a little bit right here, executing our script, and you didn't see anything in here. Nothing changed. That's because your variables have to be public. This means that Unity's inspector can actually see them and perform direct changes to them. For my more advanced viewers, yes, we'll be talking about getters and setters later on, but for now I would like to explain simple things just as they are. So having it like this, with a public in front, this will allow us to unhide this variable so that Unity can see it, and other scripts can see it as well. They can directly access it and directly modify it, which isn't a safe code. However, if we want to have it seen inside of Unity, we have to do it. So our variable is not hidden, it is used for storing true or false value, and it's called myvar, and so on. Once again, Unity is thinking, and then once it's done, you'll see two variables in here. And if we want to, we can tick myvar and untick it. This means that the variable has a value of true, and this means that it has a value of false. Some integer is currently 0, and it can be -100, for example, press enter, or you can even click on the empty space and drag it left and right to increase it by 1 every single time. However, there is a limit to how big it can be, or how small it can be. Integer is a 32-bit value. This means that the integer can have a value not greater than this amount. This is the absolute maximum which an integer can have. It can be both negative and positive, but its absolute value, that is its amount, shouldn't exceed this number. I was talking about bits just a second ago. You might not know what it is. A bit is an entity which can be either 0 or 1. In computer terms, it means that the wire will have current running through it, or it will have no current running through it. So I'll put 2 forward slashes, so I can write anything inside of here, and the editor will not throw any kind of errors at me for not following the syntaxes. And now I can write freely to you. A bit is 0 or 1. Byte is an array of 8 bits. An array just stands for sequence or some sort of a list, but not really. It's a collection of some sort. So byte contains 8 bits, and an example of a byte is as follows. As you can see, we got 8 bits in here, and this is equal to 0. By convention, people who made computers established a rule that the first byte, if it's turned on, will imply that the whole number is bigger by 1. This one, the second one, represents a value of 2. The third one represents a value of 4. This one, 8. And then every single time, it's basically multiplying by 2. 16, 32, 64, and 128. As you can see, I can express a value of 65 by writing 0, 1, that is, I want to have 64. Then I put 0, 0, that is, neither 32 nor 16 are desired by me. And then I can write 0, so no 8, no 4, no 2, and then I want 1. This is an absolutely excellent way of expressing your numbers, because if you think about it, there is only one combination for each single number. For example, 9 is 1 and then 8. 3 is 1 and 2. 36 is 32 and then a 4. And 35 is 32, 2 and 1, etc. As follows, byte, if you turn on all the zeros, can express a value between 0 all the way to 255. That is, it can express 256 values inside of it. But it's only the case if the byte is unsigned. That is, you want to express a positive value from 0 to 255. If you want to have your byte to be signed, then you have to divide it in half and provide one half to be negative and the other half to be positive. So this is an unsigned byte. That is ubyte, unsigned byte. But a signed byte is from negative 127 to 0 and then to positive 127. Integer is a 32-bit value, that is, it has that many zeros times 4. That amount of zeros allows us to express a value of that size. This is a signed int. An unsigned int can be twice bigger because it doesn't have to carry information about minus. And it's very handy to remember. Those are basically the powers of 2. For example, 2 to the power of 0 equals 1 because any number to the power of 0 is 1. 2 to the power of 1 is 2. 4 is 2 times 2, that is 2 to the power of 2. 8 is 2 to the power of 3 because we multiply 2 by 2 by 2, and so on. That's why 1024, it's also a power of 2, that is 2 to the power of 10. And 2048, that is the sizes of the texture that we've been using, are also falling into this category. This is because bit operations are very fast, and this is exactly what a computer is doing behind the curtains. We are going to be writing in an arbitrary language, the simplifications, so that we can express our thoughts in the way that we understand them, and then they all will be recompiled and recoded into the machinery language, the low-level language. That is, our commands will be broken down into simple instructions, and then output as a sequence of zeros and ones. That is, the current should pass through the wire or not. On YouTube there is an excellent video, and I probably will put a link into the description of the video, or also into the annotations to this video, which you'll see now. It is talking about the architecture of CPU. It's very interesting, check it out. Just to add to this, kilobyte is 1024 bytes, megabyte is 1024 kilobytes, so quite a lot of those little bits. Gigabyte is 1024 megabytes, terabyte is 1024 of gigabytes. After terabytes there are petabytes, exabytes, zettabytes and yottabytes, which are quite big for our current time. In comparison to that, our current script is only weighing 209 bytes, so less than a quarter of kilobyte. That was some background about bits, and keep in mind the terms unsigned and signed. But we were creating our variables, and because of that, we told Unity that we want to have a variable which can be either true or false in the inspector because it's public, and the script is attached as a component to one of our game objects. And we also want to have an integer, which is exposed to inspector just as the myvar was, because it's public, and because of that, we can change this default value by typing in our own preferred one. This will not change it inside of the script as we type it inside of the inspector, and we'll be talking about serialization later on. But anything that you do in here in the inspector will not have an effect on the script for now. By default, booleans, if not specified, they will be always false. You can specifically and explicitly specify that you want to have a boolean to be true by default by typing in equals true. And if you type something like 1.0 or 1.9, this will be considered a mistake because boolean is a type which is incompatible and cannot carry this value. It can only be true or false. If you don't put semicolon at the end, you'll get an error saying that the beginning of this line does not match the ending of this line. Remember that this is equivalent for the computer as if we would be saying that true and then spacebar public. Those two things do not relate between each other. That's why computer wants us to have a semicolon here. It doesn't care if our code contains enter in between or not. C# is the language which requires correct syntaxes. That is, you have to put semicolons at the end of each statement. I think it's not necessary to say. However, just like in 3ds Max, of course, our script is running from top to bottom. That is, computer will execute this piece of code first, then this one, and so on. Sometimes our code is presented in chunks, which computer recognizes, and then jumps between them back and forth. It is much more complex than just advancing from top to bottom because of those things, but in general, that is how things work. You start your code on top, and then it proceeds to the end, to the bottom of your script. Because our class extends from MonoBehavior, that is the class provided by Unity, and we'll be talking about extending, inheritance, etc. later on. But because of that, because it extends this class, it can use functions, variables, and different parameters which are provided by MonoBehavior. We're also using a couple of other libraries, such as the ones located inside of system, inside of collections, and also the one provided by Unity Engine. Those two are necessary ones. You'll see them almost always in everybody's scripts. Sometimes you'll have more extensions and more additions, and sometimes your scripts will be deriving from different classes. Once again, we'll be talking about inheritance and deriving later on. Because we're using this class, we're extending from it, we can make use of supplied function, which is called start. For now, we'll type in void, and you'll understand what it is in a second, and start. The function is like a machine with Coca-Cola. You throw in a coin, and you get some kind of result, usually a can of Coca-Cola. but it depends on how you coded your function and what you expect it to give out as it's finished. This one is void. That means it returns nothing. If you throw your coin inside of the function, something will happen, but you won't get a result of this function. You'll receive nothing. However, it will have some kind of impact on the system. By convention, MonoBehavior stated that this function, which it controls and provides to us, start, it will be always executed first as soon as you start the game. You start the game by going into Unity and clicking on this button. This puts you into the play mode. As you can see, we're currently running the game, and we'll be talking about different statistics that we can see in here also later on. We are doing everything part by part. However, I'm outlining which things we'll be doing later on, so that you don't freak out and don't start to think that, oh my god, I missed something. We'll be talking about this later on, but this button allows you to enter the gameplay mode. As we click it, this is the moment when the start function is being executed. We can declare something inside of our function, something that we want to happen during that moment when the start is called. Let's type in debug.log. Inside of this function, let's put in a string saying something like hello world, of course. And then don't forget that you have to put semicolon at the end. String is a type, but in our case, it's a value which is contained between those double quotation marks. If at any stage of your code you type in double quotation mark, that means that you want to supply a value of type string. And in this case, we want to supply into the debug log a string saying hello world. This function, log, will print out a message into the Unity's console because Unity is familiar with it and said that, okay, if user calls log, then I'm going to be typing everything out into the console. That is, you'll see a message right here, or if you are switched away from the console in some other tab, you'll see displayed here. The latest message will be popped into here. So, as we click start in Unity's interface, this function will kick in, and this function will be performed inside of the start one, displaying the message. As you can see, we get hello world message. It's not a warning, it's just a message, the debug one. You can figure out that it's not a warning because it has a comic cloud sign next to it. This is a message, that's a warning if you have a yellow triangle. And then the error would be a red sign stating that there was compilation error when the script tried to execute. You'll get a compilation error, for example, if you miss a semicolon. For example, if we save our script to apply the changes without our semicolon, if we go back into the editor, you'll see that you get an error saying that first script inside of our tutorial A scripts folder, which sits inside of assets folder. This script, which is of language C#, has an error at line 9, column 12. If we go back into our script, we can see that yes, indeed, 9 is our line, and then all the way at 12 we get an error because, well, we didn't put a semicolon before this statement. That's why it's thinking that everything up to those brackets, starting from public int, it thinks that all of that is one statement. And it doesn't like it because it cannot figure out what we want. Void does not usually follow the name. There has to be a semicolon. That's why Unity is suggesting to us, if I roll back our actions, that's why Unity is suggesting to us that void was not expected in this case. Since we were declaring either class, struct, or interface member, indeed we were declaring an integer, and void is not expected in this case to follow it. There has to be something in between, and that is semicolon. If you go back into here after saving your script, the error will disappear. Currently, those variables are sitting idle. They exist throughout the life of our script, and they carry a value of some sort. This one is carrying true, and by default this one is null, because it hasn't been given a value yet. So it's not initialized. We can change it to something like -10 during our start function. For that, we can put an enter, and before our debug put another statement, which will state that our sum int will become equal to 10. And just like I've explained to you in 3ds Max, this sign is nothing like mathematical equality. Here it means that the left side becomes equal to whatever is on the right. It's not double equality or anything like this. And so, by default, sum int is -5. Then when the start function is executed, it becomes 10, which then is followed by our message produced by the result of function log. In it we say that we want to display hello world message. If along with this string we want to display a value of our int, just so that we can track and confirm that indeed it became 10, we can put plus and put some int. Because this is a string, we're not actually adding anything in here, we're concatenating. This means that some int will be converted to string, and then those two strings will be glued together. In fact, before this quotation mark that is string ends, let's put a space bar so that there will be some space between this message and 10, which will be popped in as a value of some int. Let's save our script, exit gameplay mode, and enter it once again. Notice that we get one message stating hello world 10. Since this is a name of the variable, by the rules of C#, we want to express its value. If we want to type a string saying some int and not the value, we would have to concatenate to this string a string stating some int, and that's it. This would be considered a word, but if we're stating some int without quotation marks, that is, it's not treated as a string, it's an equivalent of stating 10, because at this instance, some int is 10. So we can change some int to something like 11, for example, print hello world, spacebar, string ends, and then we concatenate value of this variable at the current state of time, and then we want to concatenate something else. Let's put oh yes. Make sure to end the string, because if you don't close the quotation mark, everything else will be considered as the continuation of string. Finish your double quotation marks because they begin here and end here. Make sure that you have semicolon, and if you have everything correct, you can press Ctrl S, you won't get any errors here. Exit the gameplay mode and enter it once again, and now you'll have hello world 11, and then it will state oh yes. Notice that there is no space in here. That is because it's effectively stating hello world, space, the string ends, then we stick a value of this variable, then we concatenate a second string which doesn't have a space in here. The string directly starts with the capital letter O. So we put spacebar in here, press Ctrl S to apply the changes, and re-enter our gameplay mode. Everything now is correct. Now I would like to create another function, my custom one. There are a couple of reserved functions by Unity, such as start, which belongs to MonoBehavior, awake, update. Those are the ones that we'll be talking about later. However, if you decide that you want to have a function, then you suddenly by some chance decide to call it update, and if your class inherits from MonoBehavior, that is extends. If it does so, you won't be able to use update and code it as your own custom function, because it's already belonging to the parent class from which you are extending. We'll be talking about this later on, but make sure not to use for your custom functions the names start, update, awake, and onGUI, for example. In my case, I'm going to say that my function will not give us any result, like no Coca-Cola, after we throw in something into it. And I want to say my update. This is the name that is not reserved by MonoBehavior. And we can open and close the brackets. We're not specifying anything inside of the brackets. That is, the function is not expecting any kind of coin. If you think about it as a Coca-Cola vending machine, it's not expecting any kind of coin from you. That's why this area is empty inside of those brackets. And we'll execute something. Okay, we want to use debug. And we want to put another string into the debug to be displayed by the console. Let's say we are making use of my update. Make sure to end the string so that it doesn't eat the following bracket and semicolon. Press Ctrl S. Now we've stated that this is our function. We have it in our possession. Make sure that your function is inside of the whole class. That is your first script. It has to be inside of it in order to work. But we've specified our myUpdate function, and this is the set of instructions which will occur if we call for the function. But currently, when the start begins, it will end and nothing will happen because myUpdate is just a set of instructions. In order to make use of myUpdate, inside of the start, for example, we have to call for this function that we've just created a second ago. We have to say myUpdate, put empty brackets, and don't put inside of them anything because we're not giving any kind of coins to our vending machine. Put semicolon, Ctrl S to save, and now when we start our game, the start function will kick in because of the MonoBehavior's rules. It will change some int which we've specified to be by default -5. It will change it to 11, then start will continue executing your code. It will call for a function log which takes as an argument as a coin. It takes in the string, the value of some int, that is, it's going to be 11, and then it concatenates a second string stating oh yes. This will be displayed to the console inside of Unity, and then after this is done, we want to call for myUpdate. At this stage, when we do so, the code will jump to executing starting from this part. It will see that the function does not return anything, so no Coca-Cola will fall out from the machine. It's called myUpdate, so indeed that's the right one to look at the moment, and it doesn't take any arguments. It doesn't take any kind of coins into it. The function starts here because the curly brackets, the opening ones, are right there, and it ends by this curly bracket at line 17. Inside of it, it has just one instruction. It says that we want to put the message onto the console stating that we are making use of myUpdate. And because it's finished, we have to return back to the place where we called it from. By now, myUpdate will be finished, and after this, the start finishes. And we don't have anything else to output, but this will conclude this example. Let's re-enter our gameplay mode, and as you can see, we get one message stating hello world 11, oh yes, and I'll put this for comparison right here. So the first message comes from this line, and the second one comes from here. Let's say inside of start function, we can say that we don't want to stop after myUpdate, and we want to give another debug log stating Okay, end of start. Notice that this is not calling for function since it's enclosed inside of the double quotation marks. That is, it's not being regarded to as any kind of call or variable since it's treated as a string, like a verbal or written message. Once again, we changed my int to 11. We debug a message with the int value and with another string. We call for my update, which will be busy working on its code. In fact, this code is just one instruction stating that we want to output one message onto the console. Then my update finishes, and then we throw another debug log from our start function stating that, okay, this is the end of start. And then the start finishes. Save your script and re-enter the game mode. Now we get 3 messages, just like as planned. In this example, we became familiar with the gameplay mode. We touched very briefly on extending from classes, like MonoBehavior grants us the ability to make use of its start function. We touched on how to output our messages and the values of our variables at current state to the console via the debug.log. And we also touched very briefly on our functions, on our custom ones, how we should name them. Do we expect anything to fall out as a result from this function? Or does it do something to the system, just like this debug log does? It will become clear later on how do we return something else except for emptiness from the function from the next stage. In previous experiment we worked with myUpdate function, which is a custom function of ours, and we called it after the first debug log command. It was a simple function which didn't do anything except for stating that it wants to output a command onto the console of Unity with a string inside of it. It was called after the first debug log and terminated there. MyUpdate didn't return any kind of value as a result of its work. It is a void function. Now we can have a look at how we can make our own functions produce something as the result of their work. For that, let's move myUpdate above the first debug command and then get rid of the string just so that we got myUpdate function, an empty one, being empty. Previously we assigned a value which was 11 all the time to some int. So every time we initiate this function start by entering the gameplay mode, some int would always become equal to 11. Some int is a variable of type int, and because of that 11 fits into it. If you would on the other hand attempt to put something like 10.5 or anything with a decimal, it would throw you an error. Those would be incompatible types. You cannot stick a number with a decimal as a value into the variable which is of type integer and takes only whole numbers. But let's say we don't want to give 11 every single time to some int. Let's say we want to assign it a value that is going to be produced by the work of myUpdate function. Currently, if I put it like this, it's not going to be correct because, first of all, myUpdate is empty and it does not work on anything. It cannot produce anything. And secondly, its return type is void. That means that myUpdate will not give anything in any case. Our Coca-Cola machine will not throw any kind of Coca-Cola bottles at us by the time it's done executing. That's why, first of all, let's change its return type to integer, stating that when it's done, as a result, we will have some kind of value of type integer. And before we start specifying what we want to do inside of it, let's also talk about arguments. The round brackets that are following the function's signature are currently empty. They are used for passing in parameters and setting up the requirements for the types of objects that have to be passed into the function. Let's say the vending machine does not always take coins. Maybe it wants tokens or banknotes. Those are different types of objects, and to specify which one we want to, if any, we have to specify them after the function's signature inside of round brackets. Let's say that we want to have an input type to be always integer, and then we will put some kind of arbitrary name, for example, myArgument. That means when we call myUpdate to be executed, we can put any number inside of its brackets, like 5, 4, anything that's of type int that will fit into this statement right here. Then the function will be able to operate correctly. As a result, it will produce an integer value, which will then be assigned to some int. If myUpdate will throw something like 5, then this statement will be equivalent to saying some int becomes equal to 5. If, as myUpdate finishes, by the end of it will have a value of 11, then some int will become equal to 11, and so on. Once again, it's very important to understand. Integer is a return type of myUpdate, and because of that, we can put it on this line along with some int, because the return type of myUpdate fits the type of some integer. Some integer will be able to acquire the value of myUpdate, because it's going to be an integer value. So we can put into myUpdate an argument of like 5, 6, or 11, anything that we want, negative or positive, that is integer. But it's not going to be really interesting. Instead, let's pass a value of some int as an argument. That is, as the start initiates, some integer will become equal to the result of myUpdate that will be working on some integer at the current state. be it multiplication inside of the update, division, subtraction, or addition, anything that you want. And then some int will be rewritten. Remember that inside of my update, anything that's passed as an argument, we don't really care what it is. My update sees this argument only as the name my argument. It does not care if you pass it some int, some float, whatever. As long as it's int and it fits into the argument statement, from now on until my update works, it will be referenced as my argument. In this case, we're gonna say my argument plus equals to 1. This notation is a new one, and it states that whatever my argument currently is, incremented by 1. So plus equals, and you cannot change them in place, plus before equals always. This is a shorthand notation for incrementing numbers quickly, without writing too much code. You can also put plus equals 10, 11, and even plus equals negative number if you want to. But it's not really correct, because it's better to put minus equals 2. You can also do multiply equals 2, which is a star. Above your 8, if you press shift and press 8, you'll get a star. So multiply equals 2, divide equals 2, subtract equals 2, and add equals 2. That's going to be enough for you for now. Plus, minus, divide, multiply, those are called operators. Let's make it as it was before. So we increment it by 1. Then, since this function is not of type void, that is, it has to return something, otherwise it's going to be an error. It has to return something of type integer. Let's put enter, and then on a new line write return, which is a keyword, then put my argument. Remember to put semicolon at the end. Now, as we press the play button, start will initiate, and then the previously declared variable SumInt will be assigned a value that is going to be a result of my update, which will be working with an argument SumInt at its current state. As soon as this line of code is called, immediately the code will jump into here and will start executing until it hits the return keyword and then returns the result of the function back into here. But while my update is working, it's working with an argument which is passed into it. From now on, in this place, my update forgets about the real name of the variable and just works with the value that this variable passed as an argument had at this state of time. In here, we're going to be referencing it as my argument, and we're just incrementing my argument by 1 and then throwing it out as a result. My argument is of type int, therefore, indeed it can be returned, since we are waiting for an integer return type, as specified in the function's signature. As follows, when my update is done, its return value is assigned to some int, because it was requested like this at the first place, with an equal sign. Then we can produce our 2 debug messages, and that's the end of the start function. In the first debug, we will see the value of some int, and if by default it's -5, by the time when this function is run, some int will have a value of -4, because it will be incremented via my update. We should be able to see -4 in the first debug log, because it's grabbing the first string and concatenating the value of some int at this state of time, which should have -4 as a value by now, and then concatenating a second string as a second message nearby. Let's press Ctrl S to save it, or save it in here. Go back into Unity, make sure that we don't have any kind of errors. If there are errors, you can just double click on them, just like on any messages here, and see where they're coming from. For instance, I double clicked on this message, and it's saying that it's on the next line, that is this one. Okay, end of start. This is where this message came from. Let's click on play. We get a value of 159, which is not -4, and a couple of other messages. If we come back into the inspector by exiting the play mode, this script was attached to our gameObject, which stands for light. If we can see, we changed the default value to be some int. It is 158 by default, and when the script is run, this value is already reassigned a value of 158. So when it's run, it's going to be incremented by 1. If we want to, we can set it up to be 200, for example, and then press enter, and as soon as we hitting the play mode, look, there is 201 now. As you exit the play mode, the values get returned to their original state. That is, values will get remembered if you change them before the gameplay, but if you enter the gameplay, select your object with your script component and type in something like 300, then exit the game regime, it will be restored back to the value of 200. This is directly tied with serialization. We'll be talking about this later on. You can also restore your script to its original values by left-clicking on this cogwheel in the top right corner and clicking reset. Now some int is back at -5, just like it was stated inside of your script. And my var has a value of true, just as you wanted inside of the script, with a tick being placed in here. Remember that now first script is a component, pretty much the same as the light component or the transform component. It has different parameters of different types, such as boolean or integer, each one of which has its own specific value. In our script, we've specified inside of our class a function which should return integer. When it's done executing, we called it myUpdate. It's taking an argument which should always be an integer, and we'll be referencing inside of this function with the name myArgument. As it's being called in here, it simply snatches the value of some int or anything that's passed into it, and this value gets plugged into myArgument variable right here. The only requirement is that the value that gets snatched has to be an integer. And then the result of this function is an int, because it's stated with the return type near the function. This value of integer will be assigned to the variable, which accepts integer. If your function is anything but void, ensure that you are returning a correct type. That is, if you specify a Boolean variable here, only local to this function, it only exists while this function works. So a local variable of type Boolean a1, for example, equals true. If you try to return a1 variable, which is of type Boolean, first of all, there is a mismatch since you are returning a variable of type Boolean, but your function stated initially that it will return only integer as a return. That's an error. And secondly, even if it would return a Boolean, and it would work somehow,
you cannot assign a Boolean value to the variable which expects an integer type.
The next stage of our learning is making sure that you understand what conditions and loops are, which type the loops can be, as well as how we can express the conditions. Inside of myUpdate function, we can add to its instructions the check, which will see if the supplied argument is bigger than a set amount, and if so, it will produce a message, or produce one output. But if it checks the argument and the condition is not met, you get nothing. It just continues doing what it was doing. This type of condition is called if statement. All we have to do is to write on a new line if, and inside of brackets we can put the condition that we want to check upon. Here we're going to be checking if my argument is exactly equal to, let's say, 10. Make sure that you put a double equal sign, not a single one, because double equal sign means checking, and a single equal sign is an operator for assigning things from the right side to the left one. So double equal sign, and this means that we're checking if my argument has the value of whatever the right side has. You can also write in Yoda expressions and say it in an opposite way, as if Yoda from Star Wars would be saying, if 10 equals my argument. And if so, you'll be able to perform something which is stated after the if statement. This is a Yoda expression. Most of the people write it the normal way. But after we've specified what we're going to be checking upon, we can open the curly brackets, or the braces as they're called, then specify what should be done in case the statement was true. In this case, let's make my argument equals to 0. That is, my argument becomes equal to 0. Make sure to put the semicolon after this line of code inside the if statement. You almost never put semicolon after the braces, following the convention and the rules of writing, with a few exceptions such as enums, for example, but we'll be talking about them slightly later. You don't put semicolons after braces, but you do put semicolons on the consecutive lines inside of the braces. Let's get rid of this line, and as we throw a variable's value into myUpdate function during start, this block of code will start to execute. It will see that the value was passed as an argument, to which we refer as myArgument inside of this function, and we check if it was equal to 10, and if its value was indeed 10, it becomes 0 now. Then we will fall out from this part of code because the braces end here, and there is nothing else to do except for return a value of our integer type variable. When this function has returned something, the value to some int will be reassigned as the result of return of this function, and we'll throw out a debug log saying hello world, telling which value this variable has at this current state of time, and a couple of other messages. Let's save our script. Make sure that we select our light to which this component is attached. Make sure that it's enabled, because if it's disabled, you won't get anything running. Let's change it to 10. And because it's now 10, the condition will be met, and inside of myUpdate function, which is called by the start one, inside of myUpdate, the argument that we passed to it will trigger a block of code which compares if it was equal to 10. Then it will be set to 0 due to that, and will be thrown out from the function and assigned to some int. So if we run the game and look in the console, we can see that indeed some int became equal to 0. It's very important once again that you write the names of functions such as start or the names of your variable, that you keep writing them as they are. That is, pay attention to the upper and lowercase letters, make sure that there are no spaces inside of the names, etc. In addition to the if comparison is the else statement. In the case if this condition was not met, we can say else, open the brackets and close them, and in here we can specify which kind of instructions we would like to be performed in case if my argument's value was not exactly 10. In this case, let's not change anything and leave it as it is, but let's produce a message. Oh no, passed argument's value was not exactly 10. It gets thrown into the function right here. because we're gonna set it not equal to 10 later on, it's not gonna trigger this condition. That's why else will have to be executed. And then after it's done, notice that we didn't change the value of my argument. It gets spit out from the function just like it was passed into it. So some int does not get changed after we attempt to modify it. Of course, if its value initially was not equal to 10. Let's save our script, click on the light, and change some int value to be a different one, not 10 this time, so 12 for example, or 9. Press enter to confirm the change. Let's clear our console and run the game. The start kicked in, some integer is becoming equal to the result of my update, who received a value of some integer at this current state, which was 12 in my case. Because it was equal to 12, this condition was not met, and we had to do else. That's why the first debug is this one, and we see it here. Oh no, passed argument's value was not exactly 10. Then we return my argument, since it entered the function with a value of 12, and we didn't modify it in here, it returns out as a value of 12 without alternations. Then the result of this function gets assigned to some int. It was 12 and it got assigned 12 again. And we debug hello world, the value of some int 12, and then the start ends with the second debug log. That's why we see 3 messages here. You will get an error if you get rid of the initial if conditional statement and just leave else. That's why it gets underlined, because it's expecting to have if before it. If we want to check if multiple conditions are met, we have to do it after putting space and then putting double end sign. So end, then typing in my var is exactly equal to true. That is, the instructions inside of this condition will only be run if my argument is exactly equal to 10, and my var, which is a bool and can be either true or false, it has to be true as well. If their values meet the requirements, only then will my argument become modified and will get a value of 0. Then this value will be returned at the end of my update function. So let's change inside of Unity my argument to 10 and my var to true so that it works. There you go, 10 and my var is true. If condition this time will be triggered and some int will become equal to 0. We didn't exit the gameplay mode, that's why when we did it, some int got reset back to 12, just like I've explained before. Let's redo it and enter the gameplay mode. Now some int will become 0, since the first half of condition was met and the second one as well. We can check for things in a different way. Let's get rid of this chunk of code. Then add a local variable, create one that exists only during the runtime of this function. The second variable, let's also make it a type of int, and type in my second variable. Immediately let's make it equal to 1 by default. The cool thing is that we can perform a check on one line with the return statement. For instance, we want to return whatever the result of the following statement will be. We will say, is the value of my argument exactly equals to 10? We put question mark, and if yes, if my argument indeed is 10, the right part of code will give as a result my second var. Otherwise, and that's stated with putting a colon, otherwise we'll return my argument. Once again we will return whatever the result of right side will be. If my argument is exactly equal to 10, we will return first half. If my argument's value is anything but 10, we will return the second part of the half. That is, the condition was not met. And that's the notation. You cannot switch them around. The first one is always true, and the second part is always for the case when the condition was not met. So this will spit out a value of second var, and this will spit out the value of whatever my argument at this current state is. And because it's produced, we will return it. And my update will finish with this result. As my update is done executing, my second var will get killed, and so will my argument get killed as well, because they are local variables. We can only use them while this function hasn't finished executing. For instance, further on, right here inside of start, it is as if they were not declared. Let's make my argument equal to 10, and that way make the result of the function be an integer of 1, which gets assigned to some int later on. Select our light, find our first script component, then change some int to 10 so that the condition is triggered. I had many friends of mine who could not understand the variables and the values and how they get passed and erased from the memory, so please forgive me if I'm going too slow for you. That is, some int becomes equal to 10. When the start function begins, it will want its value to be rewritten by the result of my update, inside of which we pass a value of 10 through some int. This value of 10 gets copied into my update, and because it's 10, it fits into this socket which requires integer numbers. From now on, this value, whatever it is, in our case 10, will be referred to as my argument variable. And we also create a second local variable to be able to return one or the other in case the statement was true or false. Then once it's returned, we get this value and we paste it as the result, and it now represents the right side of this statement. It can then get assigned to some int, and we'll see the information about some int. So now some int is 10, and it should trigger the change, therefore returning the local variable, which is equal to always 1 in our case, this one. Its value gets returned and plugged into some int. You might have thought that why do we need this kind of local variable inside of my update? Can't we just grab my argument and state that, okay, in the first case if it's true, then my argument becomes equal to 1, otherwise it's just as it is. And you would be absolutely right. You can totally do it. But then in this case you wouldn't be able to learn about local variables and then picking their values as one result or the other one. Here we check for if the condition is true. If it was true, my argument will become equal to 1. Otherwise, it will stay as it is. So my argument will be returned its value without any modifications. Press save, go into console, trigger the event by making some int equal to 10, enter the gameplay mode and observe how you get the value of 1. That is, some int receives the value of 1 because inside of my update function, the condition was met. And so we returned the value of my argument. In fact, you can even put 1 in here. If it's true, then you return 1. Otherwise, you return whatever my argument is. There you go. You cannot return 1.5 once again or anything with a decimal because the return type of the function is integer. It has to be integer. If we try to return 1.5, for example, notice which kind of error we'll get and try to remember it. Cannot implicitly convert type double to integer. We'll talk about distinction between double and float later on, but float is less precise than double. That means with double you can have twice more numbers after the decimal, after the point, than with float. To make it a float, we just type in f, so that would signify that the number contains less precision and takes up less memory. But the lesson here is that you cannot convert this type, which is float, to be returned as an integer implicitly. It requires a so-called cast. We will also discuss it later on. But if you see this error, now you know what might be the cause of it. When we've discussed those two conditions, there is another one. In this case, let's get back our local variable, which was integer my second arg or something like that. It was equal to 1 by default. Or actually we cannot initialize it and just state that it's there. It will get its value later on. And then inside of my update, we can perform a check, a very quick one. I'm going to show you a sequence of if-else checks and how we can improve upon that to get very quick speeds. The slow way of doing something is, for example, if my argument is exactly equals to 1, then we do one bit of code. Else, if my argument exactly equals to 2, then we do a second bit of code. Else, if the previous statement was not met, we will do something else. In the worst case scenario, we will have to perform 2 checks in here. And if we have a long chain of if-else statements, then it might take quite a lot of time to execute. If we are comparing our numbers directly, that is, without greater or equals to, less or equals to, but directly checking if it's exactly equal to some kind of value, we can do a much quicker check, which is called switch. Here we can say we are doing a switch. We are going to pass which value we're going to be tracking. That is, we're checking with my argument. We have to open up and close the braces to enclose the instructions for our switch and put inside of it several cases. Let's say the case where my argument is equal to 1. Then we put a colon. Then state what will happen in this case. We can say my argument gets incremented by the value of 1, then it gets incremented by the value of 2. In order to end the case, we have to put a break keyword. If my argument was equal to 2, then we will increment it also by 1. And instead of writing plus equals to 1, if it's just a simple incrementation by 1, we can put plus plus for saving time, having easier code to read. After we're done describing this case, we have to put break once again with a semicolon. And for the case where the variable whose value we're tracking, if it has a value of 3, then my argument will get its value subtracted, reduced by 100. Make sure to put break at the end of each case. You can also put comments everywhere by putting /, then typing in, for example, the end of our switch. Here it's the start of our switch. In the case when you're working with a team, and you know that your code will be accessed many times by other people, you have to put descriptive comments so that they don't get lost and understand the purpose of each block of code that you're writing. As we're passing in the argument for the switch quickly glances at the type of my argument, which is integer, and now the values of the cases have to be of type integer as well. If it's something like decimal, we will get an error where we cannot implicitly cast from float or double, which is a decimal number, to the integer. Just as if we try to mention the case where the value of my argument is a character, for example, like A, C, B. Notice that I'm using single quotation marks for the character and double ones for the string, that is the array of characters. But if I type in something like the value is equal to the character w, we'll get a cast type error because my argument is integer and so should be its values. But if it's w, we'll get an error. However, we will also get 1 because we didn't return anything from this function. Since its return type is integer, not void, we must produce something by the end of the function, as well as the fact that some integer actually expects a value to come out from it. So we must return, and it would be wise to return my argument, which we've been altering in here. So we are returning the value of my argument. However, because our case is w, we should get an error. Make sure that your cases describe values whose type is the same as the argument which you check upon. Otherwise, you'll never be able to trigger the case. That is, our switch will only be triggered if the value passed into the function was either 1, 2, or 3. If it's anything else, then it's just going to be returned without any alterations, because the switch will not meet any cases to work upon. Let's click on our light, locate our script component, then change some int to something like 1 to trigger the first case. In the first case, the local variable will be incremented by 3, then the case breaks, signifying that we fall out of the switch which we've been working upon, then not checking for any of other cases. Then the value gets returned. So if it's 1, after being incremented by 3, some int will get its value. It's going to become 4, just like here. Let's see if it's 2, so that it gets incremented just by 1. There we go. Now it's 2 plus 1 equals 3. And if it's 3, we're going to subtract 100 because it's a third case. It's going to be negative 97 this time. Negative 97 is a whole number. That's why everything here works, since our types match. In case if you forget to put break statement, you'll get the following error. Try to remember it. Control cannot fall through from one case label to another. That means you have case here, couple of instructions, and then the second case with its own instructions. There is no break in between of them, and there should be if your cases are specifying code. You can, however, get rid of the code between the cases. That's gonna act as if you're checking, is my argument 2 or 3? Do the following code. But there shouldn't be any code in between of them. This type of statement is completely valid, and it's an OR statement. If my argument has any of those values, we'll perform this instruction and then break. As you can see, we got rid of the error. We get this warning that my second argument is declared, but is never used. That's because, yes indeed, it's local variable, it got declared inside of our function, and it will be killed after my update finishes running. But we didn't make use of it anywhere in here, so it's not necessary. It's just taking up space. Let's get rid of it. Notice that we can also enclose our return statements inside of the conditions. For instance, after we performed this kind of switch, we can check if my argument is greater than 0, and if it's true, then we will finish our function by returning my argument and terminating the function right there. Else, if my argument is exactly equal to 0, we will return another variable. And to be able to return a new variable, it has to be first declared. If we didn't make use of this kind of variable in our code before it was declared, we can declare it anywhere in the function as long as it was not worked with in the previous code of the function. So for example, we can declare an integer, my second arg. We will initialize it by assigning it a value of 1 by default. And now we check if my argument is 0, then we will terminate the function by returning the value of my argument. Otherwise, if my argument is exactly equal to 0, we will return my second argument. Notice that we didn't make use of my second argument here. That's why it's possible to declare it after this chunk of code. In theory, we can actually grab it and declare it inside of our else statement, inside of this part. But remember that you cannot stick it into here, since else should always follow the if statement. In fact, you cannot put anything in here, because else has to follow the if statement. So if my argument is equal to 0, inside of this chunk of code, declare my second argument, which is equal to 1, which will get killed as well once this if statement is done executing. And then straight away return its value and terminate the whole function. Observe the fact that because our case 2 and case 3 are acting like a single thing, we can change the passed argument in two ways. Incremented by 3 if its value initially was equal to 1, and decremented by 100 in case if it was 2 or 3. That's why currently this piece of code will never be executed, since it doesn't matter if you pass -3, 20, 16, any number that's not 1, 2 or 3, this chunk of code will not do anything. In fact, unless you pass my argument equals to 0 by default, then this chunk will not be triggered. We will check if my argument is greater than 0, and it's 0, so it's not greater than 0. Then this piece of code will be triggered. So it's only one possibility of triggering it. If you would supply my argument as 100 in anticipation that it's going to get decremented by 100, it will not work because of case 3, where the value of my argument is equal to 3. It has to be 3 in order to trigger this change. That's why let's bypass this check by making my argument something greater than 3, such as 4 and more, triggering this statement. Let's save our code, put in something like 5, for instance. and running the game. Before that, let's clear our console. And here we get an error, because if this condition is not met, nor is this one, then there is no return of the function. But we stated that it will return an integer, so we have to provide at least something. For instance, return 0, or for example, my argument just like it is. So keep in mind this error, and when it happens, you will know what to do. In this case, we are passing some int to be 5, a value of 5 by default, triggering the first check and bypassing the switch alteration. And as you can see, we return it straight away as a 5 with the first statement. Let's pass in like 100, for instance. There you go. The switch was bypassed. Then, since the first if statement is triggered because the value is greater than 0, we return it as it is. Then it gets assigned to some int inside of start function and debugged as it was passed. This time let's give it minus 120. Because it's a negative number, it will be passed as minus 120 into my update, which is a whole number, so it's okay. It will not trigger any of the cases for this switch, since it's a negative number and there are no cases described for this matter. That's why we bypass it. And now we do the first check. Is my argument greater than 0? No, it's not. We bypass this chunk of code. And if it's not true, we immediately check if my argument is exactly equal to 0. And no, once again, it's not equal to 0. It's minus 120. So we bypass this chunk of code. And then we return this minus 120 because this is the last thing that we have remaining. So we passed minus 120 into here. We got out of it also minus 120, which gets reassigned to some int and printed out onto the console. There you go, minus 120 as expected. This time, let's change the value to something like 0. As you remember, this is the only case when the second else if statement will be triggered. We pass in value of 0 into my update. 0 is a whole number, so it fits into the socket. We bypass any of the cases of switch because they do not describe anything for 0. We check for the first statement, is it greater than 0 or not. 0 is not bigger than 0, it's exactly equal to 0. And we do the second check, where we check if the value of our argument is exactly equal to 0. And in fact it is, so we will declare a new variable and initialize it to equal to 1, then immediately return it. So if it's 0, we will always get 1 as the result of the function. You might be wondering, why aren't we changing anything within the world? Why do we bother with the console, debug log and everything? But I want to make sure that you have a solid picture in your head of what's happening and you're not jumping from place to place. There might be things that you already know, but with this kind of learning where we have a look at our coding step by step, I ensure that everything that you learn lies nice and flat in your head. Currently, we are extending our vocabulary so that we know which tools we can use in order to efficiently manipulate objects within our scenes and perform different actions quickly. Once we've looked at conditions such as if-else, and at conditions with a question mark, once we've learned about the statements with cases, we can begin to learn about loops. There are several types of loops. The first one, and the easiest one, is while loop. Inside of our function, which takes my argument integer, inside of it let's declare a loop, while, and then we pass into while's brackets something to check against every single incrementation of while. And while it's true, we will perform this action. As soon as this condition inside of those round brackets will not be met, the chunk of code that belongs to while will not be executed, and we will fall out from the while loop. In this case, let's state that while my argument is less than 20, perform the following thing. My argument minus minus, which is a decrementation by 1, as discussed before. So every single iteration of this while loop, my argument will be decreased by 1, then we come back and check again. If my argument is less than 20, the while loop will keep on going. However, in this case, in order to kickstart it, we have to supply a value into the function of 19 or less, because a value of 20, belonging to my argument, will fall out from the while loop immediately. So by default, let's supply a value to some int to be 19. Keep in mind that as the start function begins, some int passes its value into my update in anticipation of receiving the result from my update later on and reassigning it to its value. But 19 falls into my update. From now on it's going to be referenced via the name myArgument, which exists for as long as my update is working. And while it's less than 20, it will be reduced to become even smaller. Because of that, it's going to become 18, 17, all the way to 0, and will become negative, meaning that this loop will keep on running, freezing our program. Watch out, because such traps can occur. They can be fatal, since it will keep on going and crash your program eventually once it runs out of memory. That's why, in this case, inside of the while loop, we will perform a check. Let's check if my argument has got its value decreased to exactly 10, and if so, we will write break, forcing us to get out of the loop which we are currently in. We can also make my argument equals to something that's not less than 20, for example, exactly 20, or something bigger. That way, as we return back to the while loop, my argument equals to 20, it's not less than 20, the condition no longer holds true, and the code will not execute. Remember that as the while finishes, we have to provide a return statement, which will give an integer type value as the result of the function's work. We can return something like my argument plus 1, and this is very important to understand because let's say if we passed in 19, we triggered the loop, it went all the way down to 10, then it became 20, it's no longer triggering the loop, we fall out from the while loop with the value of my argument being 20, and we return 21. This does not mean that we want to increment the value of argument by 1, but we want to grab its value and then add 1 to its value mathematically. If we wouldn't terminate the function with return statement, later on my argument would still equal to 20, even though there was a 1 written here. Remember that in order to change my argument by 1, we have to write either this plus plus, or my argument plus equals to 1, or my argument becomes equal to the value of my argument plus 1. Only then will it work and rewrite the value of my argument. This statement just says, okay, the value of this plus the value of this should be what I produce. Here we are producing something to be returned. That's why we'll always return 21 if initially we passed a value which triggered the while loop. Let's save our script, go back into the game, select our object with the script attached to it, then make it 19, for example, some int. So when its value is passed into the function, it will trigger the while loop, hit 10 and then become 20, forcing the internal variable to become 20, which will be returned with 1 added on top of its value. Then this thing gets assigned to some int, and there you go, it became 21 here and here. Watch out, because if some int is less than 10 by default, let's say it's 9, some int feeds itself into my update in anticipation of receiving a result from my update later on, but it feeds its value of -9. Update kicks in, it grabs this -9 and will be referencing it as my argument. So my argument is now -9. It's less than 20, we decrease it by 1. Now it's -8, and this check will no longer be hit, so watch out for this, because now your while loop will run indefinitely and will never stop. Watch out for this, and it's best to put not exactly equals to in this case, but an operator saying less than 10 or equal to 10. If you want to put greater or equal to, then you put greater followed by an equals sign. Do not change them in place. In this case, less than or equal to 10. This kind of error is not a syntax error, but it's a logical error. Logical errors are very hard to spot, and if you make a syntax mistake, it will be easy to fix, since Unity will point it out inside of its console. But if you make a logical mistake like this, sometimes it can take quite a lot of time, forcing you to write lots of debug statements to see if one loop worked or not. It can be quite time consuming to trace this mistake and to catch it. This was the first type of loop, the while, very simple one. And in fact, if you want to see how it operated, for every single tick of while we can debug a message. We can put a string into it, such as my argument's value is, let's put a space, close our string, and then concatenate the value of my argument, whatever it is at the current state. Its value will be transformed into string by default and will be concatenated to the first string inside of debug.log. Let's make sure that we trigger the while loop, so some int has to feed the value into the function that is less than 20. Clear our console, maybe let's extend it upwards to see more messages at once. Then hit the game. Notice all the stages through which my argument's value went. It became 18, then 17, 16, all the way down to 10, and after the 10 there was a check to figure out if we reached the required borderline, and if so, make it 20 and return a value of 20 plus 1. This value was then grabbed by some int, which was anticipating it since the very beginning of start, and when it has it, we are producing the message where we put a value of some int. The second type of loop is a for loop. We can say for, and we need some sort of a counter which will be counting. We can declare a counter before the for loop or inside of it, and for that we just write int or any type of counter that we want to have and declare its name, such as my count or whatever. We have to initialize it to be equal to, for example, 0 or whatever we want. Put a semicolon, then put a condition, which is equivalent of saying until my count, for example, is less than 40 or some other predefined variable. So if my count is less than 40, increment my count by 1, for example, or divide it by 2. But be careful, because sometimes you cannot divide integer and it will become a float. We need to be safe, so we'll increment it by 1. And then once it's done, we can perform an instruction, such as, for example, decrement my argument by 1, and then straight away debug a log into the console. If in the case with while there was a possibility of not terminating our loop and leaving it run indefinitely, here, as long as this condition is written correctly, the for loop will only run for 40 iterations. when my count becomes equal to 40, 40 is no longer less than 40. That's why this chunk of code will be omitted. It's much safer in this sense, you just gotta watch out for this conditional statement in the middle. In order to trigger it, we don't have to do anything literally. My argument can be passed as any value. It will be forced to go through this for loop 40 times, and by the end of it, my argument will be reduced by 40. Then we will return, as a result of function, the value of my argument with 1 stuck on top of it. Let's save our script, clear our console, pick our light with our script component, then make it something like 85. There you go, so many messages, each one of which is an iteration of the for loop, where we debugged the value, which belonged at this stage to my argument, the local variable inside of my update function. It was 85, then it became 45, less than 85 by 40, and then since our function returned its value plus 1, some int became not 45, but 46. So this statement right here became an equivalent of 46. Because some int is of type integer and my update returns integer, their types matched and we didn't get any kind of error. What's really cool about for loops, and what many people forget about usually, is that you can declare several variables inside of it. For that, after assigning the value to the variable, you can put a column and then put other names which are of the same type. For instance, my second count, which will be equal to 1 by default. Put semicolon to signify that this is the end of this part. With that, we've declared 2 variables of type int. The first one was equal to 0, comma. Then the second one, with the name mySecondCount, also of type integer, became equal to 1. Semicolon to end this part, and then the part with comparison begins, then incrementations and alterations to our counter kick in. You can put comma, and also decrement or increase mySecondCount in the way that you want. Notice that here I was not very careful, and so the second count contains capital C and capital O. I have to make sure that I type in the same name as it was initialized to avoid any mistakes. So after we increment my count by 1, we put comma, and we also want to decrement my second count by 2, for instance. Not having made use of my second count anywhere in here, but working with my count variable
to determine if we reach the borderline and if we should stop iterating through the for loop.
Not having used my second count, let's make use of it to change the value of my argument by my second count. So we'll plus equals to my second count, or the value of my second count. For every single tick of for loop until my count is less than 40, my second count starting from 1 will be decreased by 2 every single time, and then the value of my second count, whatever it is at the moment, will be added to the value of my argument. So my argument will become smaller and even more smaller with the bigger gaps, since every time we're going to be adding the greater negative value of my second count. Clear the console and actually decrease the number of iterations to something like 15, for instance. If we run the game, we'll get plenty of messages. As you can see, my argument value is 86, then the value of my second count is -1. It gets added to my argument, now it's 85, then my second argument gets subtracted 2, so it's now -3, we get this value, then it's -5, so we subtract -5, -7, -9, and the bigger gaps occur, until my argument's value is -110. Remember that we return at the end its value plus 1 on top of it. So some int gets the value of -109. The third type of loop is called for each loop. Currently we are gonna omit for each. Its purpose is to go through an array of elements, doing something for every single element within this array or sequence of variables. So keep in mind that there is also a for each loop, but we will be covering it later on. You are already familiar with variable types and with functions and their return types. Let's also create different variables that belong to our script, that is to its class. Notice that we have a couple of public variables and one private. This means that inspector will not be able to see it, and only the class can use it. Nothing else outside of this code will be able to access and change this variable, because it's hidden with a private keyword. The first variable here we have a public myString variable, which is of type string, and it's used to store an array of characters. We can initialize it straight away here or wait for later. For example, we can put double quotation mark to specify the beginning of the string and put some text into here. Then close the double quotation marks to end the string, and there you go, we have a public string. The next one is the character. To specify a character, you have to use single quotation mark. For example, put v. You cannot put multiple characters, since this will be considered a string, and then a mismatch of types will occur, because char cannot contain string. Then for public float decimal number, let's put something like -1.05. For public unsigned int,
we can use only the positive number because plus or minus is not used in here. Because of that, the potential size limit of unsigned integer is twice bigger than of normal integer that can go both ways, negatively and positively. Here we can use something like, let's say, 5002. For our private hidden boolean variable, let's make it false by default. Then we got public boolean, my var, and public int, some int from before. Those variables are local to this class, the first script class, that is deriving from MonoBehavior. It makes use of a couple of functions, the void start function, which is provided by the other class from which this class derives. The MonoBehavior explains how the start works. So we make use of it, changing some of the values for our variables, invoking different functions, etc. We also specified our own custom function that is local to this class. It is a private function, which it will always be unless stated explicitly. If you make it public, this function will be able to be invoked by any other external class, external script on some other different game object. Sometimes this can be useful, in other times not really. Most of the time the arsenal for the class is hidden away from the eyes of other classes, just so that they don't mess anything up by accident. However, there are some functions that are public and visible from the class. By the end of its work, function can return different things. In this case, our custom public myUpdate function was returning an integer as it's finished executing, and it was taking one argument which had to be an integer. For instance, public function with return type of string, the function that is called minor function. It takes no arguments and returns a string at its end. We can also declare inside of it a local variable, of course. If we want to, we can initialize it straight away, but we can also do so after some actions has been taken on a new line. For example, like this. So it becomes equal to string of text such as this lol. After that you can say my local variable plus equals to other text. You can do this because you can concatenate the string value to the value of the current variable, which is of type string, and you won't have any errors. You can then return either this value or return the value of a variable, my local variable. Of course, you have to invoke somehow this function, just like we did invoke myUpdate in the start function with this notation. So far, this is just a description of the function. We can make use of it in the start one by saying my string becomes equal to the result of the function minor function. Remember that minor function does not take any arguments, and you shouldn't pass anything inside of it. So whatever the result of minor function will become the new value of my string. Because this function is not void, it returns something. Having written it this way, it will produce this kind of error, because you cannot call a function which returns something without assigning the value somewhere else. In such case, the function has to be void. Also, as you declare a public float decimal number, make sure to put an f at the end, signifying that it's a float number, because if you don't put f and just leave it as a decimal point, computer will take safety measures and will assume that it's a more capacious type, the double, which allows you to have more numbers after the dot was placed. So put f to say that it's indeed a float and is a valid value to be assigned to the float type decimal number. If you want to have a double type, put in something like public my double. Then you can put minus 1.05 without an f. Although you can have your functions as public most of the time, it's usually considered a bad practice to leave your variables exposed like that for your classes. You would want to create getters and setters for each variable like this. Hold on a little bit more and we'll be talking about them. Notice that if we try to assign to our float type decimal number a value which is of type double, so it's without f, and save our script, we'll get an error which will state that once again computer cannot implicitly convert type double to float. Add suffix f to create a literal of this type. It requires an f here in order to be considered as a float value. By now you're already familiar that functions can have different return types and can be used to work on different things. Let's talk about classes now. Notice the name of our script. It's called first script, and notice the name of the class that is explained in our script. They are the same, and therefore we don't get any errors. If we do want to change the name of the first script class in our script, we have to do it here as well as in here. This class is deriving from MonoBehavior. In other words, it inherits from MonoBehavior and everything that was described in the MonoBehavior class. We can create our own custom class and derive from it if we want to. For instance, after we finished explaining the whole class, its functions and variables in here of the first script, we can declare our own class, the class that does not derive or inherit from anything and is just on its own. Class is like a set of rules. It contains explanations to different variables, functions, and contains instructions that have to be carried out in different cases. Let's create a variable, a private one, which belongs to my class. Once again, private keyword is not necessary, but I still wrote it only to emphasize this once again. Here comes the very important concept. Since my class is a set of rules, they do not matter unless they are physically formed into something. That is, if object is created from the class, only then will those variables and functions come to life and become available to use. Before that, it's just a set of instructions. To instantiate class, we have to create a constructor function. Constructor functions are always public, and they are always named exactly the same as the class is. They can take any number of arguments, and they can be without arguments. In this case, let's supply an argument integer a, for example. This function will create an instance of my class when called, because it's recognized as a creator function. It will create an instance of this class, an object out of this class, and will set my var equal to whatever the argument passed into this creator function was. In order to clear things up a bit, think of our script as a white piece of paper, contains different descriptions of how objects look like. Those descriptions are called classes. Currently we have the first description, the first class, and the second one as well. Notice that our second class is a custom one, and it does not derive from anything. It does not inherit from anything, unlike the first script does. Because it's not deriving from a MonoBehavior, it has a constructor function, this one right here, which allows it to be replicated and instantiated many times. But so far, everything in here is just a piece of paper. It does not have a representation in physical world. But as we execute some other pieces of code, we might want to create an object based on this class. Therefore, we feed this description to the compiler. Let's say it's a guy who makes stuff. Then he looks at it and then creates an object based on the description provided in the blueprint. This object is now an instance of the class. It follows all the rules that were described in it, and it contains physical representations of the variables that were described in its description. Observe that because our first class derives from MonoBehavior, it does not have to be instantiated. We make copies of it by simply dragging our script onto different game objects. But you cannot really do this, because if you have at least one class inside of your script which derives from MonoBehavior, you cannot put any kind of other classes nearby of it. We will press Ctrl X to cut out the code specifying our second class and leave it as it is on its own. But we create objects from the classes which derive from MonoBehavior by simply dragging them and instantiating on different game objects. For example, this slide. Now we can create a separate C# script. I'll call it our cust classes, so custom classes. We'll double click on it to open it in the MonoDevelop editor. We have two tabs. This is the previous script and that's our new one. Here we can get rid of everything, excluding those two lines because they are important, as explained in the very beginning. Then declare our class, my class. It has one private variable and a public constructor, so that we can create objects based on this description. Because this class is not inheriting from MonoBehavior, we cannot redistribute the script on other game objects. For example, if we drag it onto our light object, you'll see that you cannot add the script because it doesn't exist in terms of Unity. You can only instantiate classes like this, create objects out of them, if they derive from MonoBehavior. But, because this one has a constructor, back in our first script, we can make use of this class. Let's create a variable of type myClass. This type, once again, was specified in here. And prepare a variable called instantiated class. Notice that instantiated class is first of all private, that is, it's not visible in the inspector of Unity, and within another external scripts you'll not be able to access this variable because it's private. It will only accept values of type myClass, that is, it will only accept instances created from this class. When our start function kicks in, that is when we enter our gameplay mode, we can say that we want to initialize instantiated class by making it equal to new myClass. By saying new, we mean that we want to invoke a public constructor function that was specified inside of the class, right here. Keep in mind that this constructor function will take an argument of type integer in order to be able to initialize its private variable that sits inside of this class. That's why in here we have to supply any value or a variable of type integer, for example 2. Then put a semicolon. And there you go, we've created an object from myClass who now has its private variable of type integer with a value of 2, and we've established a reference to this object. Now whenever we want to make a change to this object, we just need to call this variable. Let's add a new functionality to myClass and specify a new public function so that it can be called from outside of this class. Public one which is void, that is, it doesn't return anything, stating print message. Here we'll put debug.log and supply my variable. We can also add a string before it just to make it clearer of what we are typing out. When we invoke this method belonging to the object of this class, it will produce a message, the value of my variable, the private one, is as follows, and we pop a value into here. Remember that as soon as we create an instance of this class, that is, make an object out of it, variable myVar is going to be private. It's only this object who will be able to work with its variable. It can access it and plug it into its functions local to this object, but other classes cannot directly see or modify the value of this variable because it's private. Back in our first script, on the new line during the start function, we can say that we want to invoke the function which belongs to this particular object of type myClass. And here's the function which was described in the rules of this object before. Remember that it's void and it takes no arguments. We can also create another object based on this class, a separate one from the first one. Let's declare another variable, also of the type myClass, then initialize it after. Now we can create an instance of myClass and plug it into the second instance. My second instance will get a reference to the newly created object of type myClass. And remember that the constructor of the class demands a value so that I can set its private variable that belongs to the class to this value. This time, let's make it 10. Also put a semicolon at the end for proper syntaxes. I'll draw a couple of diagrams to simplify things and to explain it from the other side. Once again, we had a blueprint that was explained in our script, our first classes, where we've described a class called myClass. It had a constructor function that modified the private variable declared at the top of the class. Therefore, this constructor function was taking an argument required for that. Here we've declared that we want to create a variable of type myClass that is therefore going to be capable of holding an instance of myClass. And also the second instance that is also capable of holding myClass object. When we say that we want instantiated class grab the reference to the newly created object of this class, we've passed a value which immediately was fed into the constructor function, which altered the private variable that belongs to the object of this class with this value. And now we have an object on this side which is now going to be always referenced by us as we call this name, instantiated class. And that's why on the next line I say that I want to do the following thing with this object. I specify which object, and I'm stating which kind of action I want to take upon it. That's why I put a dot signifying that I want to go inside of the object and access one of its variables that are public or any of its public functions. Here you can see that I've placed dot and stated that I want to execute the function that was described by the class and is available to this particular instance, to this object. The function is void, it returns nothing, it takes no arguments, but it will print out a message onto the console. And we are done here with this object for now. Then we make use of our second variable, which we neatly prepared at the beginning of this script, our first script class. And we are creating a new object based on myClass, feeding a value of 10, so that the private variable of this newborn object will become equal to 10 because of this constructor function. And then this object is now going to be accessed with our variable called second instance. Anytime we say second instance, we really mean this object now. We can state as second instance, we put a dot, signifying that we want to access one of its components, the public ones, and we have print message function available to us that we've specified a second ago. It takes no arguments and it's void, but it prints out a message onto the screen. Here you go, we've specified it before, as you remember in here. Because as we created an instance of that class back in the first script, in first time we passed an argument to the constructor function as a 2, and in the second object it was 10. That's why in the first object the constructor modifies myVar to become 2 initially, and in the second case the constructor modifies myVar to become 10. Then for the first object, as we make use of its public function described in here, it will print out this message and also the value of its private variable, myVar. That's why in the first case it will be 2 and in the second case it will be 10. Let's get rid of those debug logs and remember that we will only create an instance of the class for the first time and the second one only after the start function begins. That is, we have to save our script, ensure that it's applied to some of the gameObject, and run our game to call the start function. As you can see, an instance of my class is talking. My variable myVar has a value of 2, then the second one has a value of 10. Excellent. Notice that if we create an instance of the class, that is the object of this class, we can access the function printMessage because it was specified as public. We cannot access the variable myVar that belongs to this object because it's marked as private. Only this object is able to work on it internally. Nobody else is able to see myVar or do any changes to it. If we set myVar to public, which is a bad practice, but still, if it is so, then as we create an instance of my class, we can do something else. Let's not print the message, but say, okay, our reference to the variable, dot, and you can see that we have myVar suddenly here, available to us. You can see its type, and if it's hidden or not on the right, on the tooltip, its name is myVar. So we can say, this object, it's my variable, becomes equal to 1000, for example. Then if we call the print message function that we've specified for this class, for this particular object instance, the void function, which takes no arguments, it should print out 1000 because my var was modified. Because even though initially my var was constructed to have a value of 2 due to the constructor function, since we have a public keyword in front of my var, we also managed to modify it after the instance of the class was made. There you go, 1000. If you don't press clear on play, you'll have your older messages remaining. For example, if I click play once again, you'll see that we have new messages added on top of here. So you have 2, now 3 messages, etc. If you click collapse, this will unfold them and no longer store them in a compact way. So if you want to have a clear set of messages every single time you start the game, and start from the empty list of paper if you'd like to, you can press clear on play or clear to get rid of the messages manually. Clear on play, and as we start the game they will be erased in order to be able to give space for our new messages. You can click on this icon to hide away the messages and not to show any, and you can do the same thing for the errors or warnings. So watch out for that. If you're wondering why your things are not working and nothing is showing up here, probably you've hidden them with this icon. But as said before, my var should not really be public. It should not be exposed. Let's leave it as it was, the private one, and instead let's provide an extra flexibility for it. If we type in public, the same type as our hidden variable, so integer, and say something like underscore exposed, for example, doesn't really matter, then open up and close the curly braces. Here you can specify 2 instructions. The first one is get, close and open the curly brackets, and set. In get you can type in return the value of the private variable, that is my var. And in set you can state that you want the private variable to become equal to the value. We'll talk about the value in a second, so hold on for now. But now, because my variable is private, if we go back into the script, you can see that it highlights with red saying that it's an error because it's not accessible. For this particular instance of the object, we can press dot, and as you can see, my var is no longer shown, but exposed is available. If you choose it, then want to modify it, you can set it equal to 1000. This will automatically call this instruction and set my var equals to value. If, on the other hand, you want to read the value of my var, once again you can do it via the exposed. For example, we want to debug.log the value of my var belonging to this particular instance of the class. If we do it like this, and not assigning a value to it, that will automatically call for get and will return the value of my var. That's why in this case, as we set it to be equal to 2 by default with the constructor function of this object, here when we try to access it, we cannot do it directly, but we can do it with the help of this function, which provides getter and setter. On the other hand, if we want to make it a read-only variable, my var that is, we can get rid of set and only leave get. That means that we'll still be able to retrieve the value from my var, but we'll no longer be able to alter it externally like this, via changing it for the instance of the class. So this will work, but this will not, because you cannot make use of set instruction, since we removed it a second ago. That way, exposed is not really a variable, it's just a link to my var. Remember that before you close the brackets, in either get or set, you have to finish the line with a semicolon like this. Let's see if indeed we can get the value of my var through this one, and the getter that it provides. If all good, it should be 2. There you go, very nice. Here we debugged its value, which was 2, without any additional strings nearby. Having discussed classes, there is also one thing to mention, that beside classes, the sets of instructions, the so-called blueprints if you will, there are also different kinds of blueprints, slightly simpler one, and they're called structs. Here, in my class, which does not inherit from MonoBehavior and is just a simple class, whose name is by the way different to the name of the script, this one contains a constructor function, which kicks in as soon as we type in the new keyword, such as here, and decide to create an object out of this class. The constructor function requires an argument in our case. It wants an integer as an argument. That's why back there we've placed a 2 in the first case and then a 10 when we created a second object from this class. It got manipulated and the internal variable of this object has got its value changed appropriately. A struct is declared the same way as the class, with one exception that you don't put class keyword before the name of your class, but a struct, just like this. As I said before, struct does not make use of the constructor function, so it wouldn't be necessary. However, inside of struct, you can specify the functions just as you would in class. Struct can also describe variables inside, however it's considered to be less flexible than class. That's why most likely we're not going to be making use of structures in my tutorials. because the structure is pretty similar to class, it acts just the same way as class does. So it's also can be considered by you as some kind of blueprint. You create objects based on the structures just like that. For the type of the variable that's going to hold the reference to this object created from the struct, for its type you have to type in the name of the structure, a value of object of which will be used by this variable, just as we did here. And then you would create your instance of structure just in the same way as we do here. Of course, without any kind of argument, because structures do not use constructors. It's a good time to talk about inheritance now. We can create a second class, which will also have a creator function. In this case, it will take no arguments. It will just create an object out of this class if required to do so. Remember that in order for the function to be considered as a constructor function, it has to have the same name as the class does. Inside of this class, let's specify a method, which will be public, named importantMessage, which will take no arguments and will return nothing. That is, it will be of type void. In there, you guessed it, let's put debug.log. At the top of our class, let's also declare a variable of type character, so char, name it importantCharacter. We will leave it as it is, so when the object is instantiated, it will have no value initially. If we would like to assign a value to it at the same moment as we create the object based on this class, we can say that importantChar becomes equal to some value, such as C, for example, or anything that fits the character type. But I'm just going to leave it as it is for now. Notice that because I didn't put a public keyword here, this variable is considered private. It can only be modified within this class. We can write getter and setter for the public variable that will be exposed. And by altering this public variable, we can assign and get the values to and from the private importantCharacter. But this will be done internally within the class. However, this time let's make it not private nor public, but protected. This is a new keyword. You will get its meaning in just a little bit of time. By now we have two classes, one right here and the other one here. We got our class, myClass, which has its set of values, its set of instructions, and objects can be made based on its description. The same can happen for this class as well. Both of them have constructor functions, therefore can be instantiated in the form of objects. But if we would like to increase the range of possibilities of myClass, we can put a colon after its name, meaning that we would like to inherit from some other class. And in this case, let's inherit from our more important class. Via inheritance, we are basically saying that whatever is described here, all the functions, all the variables, they are going to be available to my class as if they were described inside of my class. However, there is one obligation. Even though we are inheriting from more important class, we cannot access any variables specified in more important class that are private. That is, if this char wouldn't have this keyword here, if it would have a keyword of private or none, so it's private by default, so not public, in this case we wouldn't be able to make use of this variable in my class. However, because it's protected, it means that any class that derives from this one can consider this kind of variable as if it was specified in the same class, for instance here. That's why let's get rid of description of my variable and its getter and setter to free up some space. We will leave the constructor function for my class because it's necessary. We will also get rid of the custom function printMessage, the function custom to my class. Back in our first script, in the start function, as we create an instance of my class, let's get rid of the second object that we are creating in this function and just have one reference to the object created from our my class. Its constructor is expecting an integer because it's specified to be so in the constructor of this class. But the constructor wants to change my var, and my var was not declared anywhere, so it's gonna throw an error. Instead, let's leave the argument for the constructor as it is, so required, but get rid of anything that the constructor used to do before. So it's just an empty constructor with an argument. In this case, we'll create an object based on this class. We'll just pass in a 2 or whatever, just to fill in the gap, the required gap for an argument. And now we can reference this newly created object with this name. Because this object inherits from a more important class, we can say instantiated class dot and make use of one of the functions that more important class provides, such as an importantMessage. It only matters that this function is public. If this function is public or protected, then we're going to be able to access it from the class which inherits it. Let's put dot, then call for an importantMessage, which takes no arguments, it's just a normal function. And if everything goes well, the newly created object will pop a message into the console, because the class derives from more important class, and therefore it has an access to the public or protected, to any kind of variable, or in this case, it has an access to the more importantMessage function. We're getting an error here, which is quite interesting because it says a more important class, the function that has the same name as the more important class, that is, the constructor function, is inaccessible due to its protection level. That means that as we try to instantiate an object in here of type myClass, which inherits from more important class's constructor function is not available to be accessed, and so we cannot create an object out of it. It has to be public. Now if we go back into our first script and save it, we'll get rid of this error. Because we have the script applied to one of our game objects in the scenes, the start function will be executed as we run the game. There you go, an important message is coming through. Now it's possible for you to understand that the name of this class, which makes use of the start function, creates objects based on our classes. This class derives from MonoBehavior. That is why it can make use of start function, a couple of other ones such as update, about which we'll talk later on GUI, and other functions which MonoBehavior specifies. You can read specifically about the MonoBehavior class, its functions and variables that you can make use of inside of your class, which will derive from it. You can do this on this page, at Unity's documentation, currently at this address, which might change later on. Just type in MonoBehavior reference into Google, you'll soon find it. As you can see, MonoBehavior is just one of the classes available for your exploration. There is so much to read for you, but we've covered so much stuff already. That's why there is a big chance that this stuff might be familiar to you. MonoBehavior provides one variable for you to use if your class is inheriting from MonoBehavior, a couple of functions, different messages, members that are inherited from other classes that are more general than MonoBehavior, etc. MonoBehavior is the class which allows you to create an instance of the class which derives from it as a component once it's dragged onto one of the game objects in the scene or in the hierarchy. You cannot do this with an ordinary class or sets of classes which are specified in separate script, the custom ones which do not derive from MonoBehavior. They cannot be instantiated like this onto the object in terms of component, but they can still be created on the fly, virtually, and be used as objects or different types. It's important to mention that you cannot derive from several classes at once. It's prohibited. But you can have class A derived from class B, and have class B derived from class C derived from class D, and so on. If in your code you decide to create an instance not of myClass, which inherits from more important class, but to create straight away an instance of more important class, then you'll have no accessibility to this part of the code, myClass. Remember about protected keyword, the inheritance, the rules that you can inherit from the parent, but the parent does not know about the existence of the child. And also don't forget that there are also things called structs. They can also be instantiated, just like we get objects from classes, and stored in the reference variable, for the type of which we just type in the name of the struct, just as if we would be typing the name of the class right here. In this example, you will see how you can use different variables recorded in a specific class to store different values. It's a slightly more complex example than the previous one, so let's get started. In our custom classes script, which contains descriptions for our custom classes, none of which derives from MonoBehavior, that's why we can specify many of them. In this script, let's specify another class. Let's call it storage. As always, our custom class that doesn't derive from MonoBehavior has to have a constructor, which is to be called with the keyword new, as we will attempt to create objects later on based on this class. Constructor function, of course, contains the same name as the one of the class, and in this case, for now, we'll leave it without arguments. It will be an empty function for now, just like this. Functions are also sometimes referred to as methods, but it's basically the same thing. Inside of our storage, let's declare a couple of integers and maybe a string type variable. Let's not initialize them with anything for now, but still declare that they will exist. We now have three variables, first int, second int, and the key text string type variable. As we will be creating objects from other scripts and classes, only then would I like to set up the values for the variables declared in this class. That's why my constructor function will take three arguments. First one will be int, and we'll refer to it within this constructor function as a variable with the name a. The second one will be also an integer type variable, or argument in this case, int b. The third one, you guessed it, will be string c. If we would like to create an instance of this class, we would have to supply three values. First one has to be integer, second one integer as well, and then the third one has to be a string of text. Then we will assign inside of our constructor function the value of the first argument to our first int. Similarly, we'll do the same thing to the second int and assign it a value of b. Then our key text will receive a value of c. Remember that those variables a, b, and c are local variables who will only exist during the execution of this function. Once it's over, a, b, c will be erased forever along with their values. But because first int, second int, and key text were declared outside of the function, once they copy the values and the function is over, they'll keep on existing. That's why if you still haven't figured it out, constructor function is used to set up default values for the variables that were declared in the beginning of the class, and set up different parameters via the methods of the class. Let's also throw a fourth variable. It will be of type float. That means that it can contain a value with a decimal. We'll call it precious number. Notice that our variables are private, and our constructor function is also private, which is incorrect. Constructor function for the class always has to be public, so that it can be accessed outside of this script. And it's very important because it allows us to instantiate class. Let's also mention that the constructor functions never specify their return type. It's neither void, nor it's integer or any other type. It's just a public function with the same name as the class. Now let's add another custom method, which will be public, that is the one visible to other classes. It will be of return type float, and we will call it insert combination. Currently this method will take no arguments. Having written space for it, let's come back into storage and also initialize our precious number to make it have some kind of value. However, as you can see, our first three variables received the values directly from the arguments. In this case, let's make precious number receive a random value from the range, which is based on the arguments. In this case, we'll have to access a sealed class random, and the function of it, that is, we put dot and then access whatever it provides, called the range. We can use this class, the random one, and everything that's inside of it because of those two lines of code. Having stated that we want to use those namespaces, we can then get an access to the whole bunch of classes that they will provide to us inside of this script. In this case, we can access a random class and everything that it supplies. Without those two lines of code above, you would get an error, since the compiler would not know what you're referring to. But range is a function which takes two arguments. If I open up the first bracket, you can see that it has an return type of integer, and it takes an integer for the minimum clamp value and the maximum. If while having this tooltip you press a down arrow on your keyboard, you'll have a second option where you can return a float value. It will also require the first argument and the second one to be of type float. In this case, we would like to return a float, and for the first argument we'll put first int to describe the smallest possible value. For the second one, we'll put the value of second int. There are two things to consider here. Because they have a type of integer, the function will automatically assume that it has to return an integer type, since its arguments were supplied as integers. But we require a second option. Since our precious number is float, we want to have float output, but then we have our arguments as integers. And there is no such option where you can mix integers and floats for this function. Because of that, we can use something called as casting. If you initialize your first int to be equal to 5 immediately, always, and then somewhere within your class, such as in this function, you would want to state that first integer becomes equal to 5.1, for example, it would give you an error, since this is a double, or if we put f, it's going to be considered as a float type, less precision, but still allows us to use decimal. However, this is not correct. We cannot assign a float value to the variable of type integer. If we would like to do so, before the number, before the value, which we are about to assign, we'll have to put in the brackets the type to which we are going to be casting. So it's, for example, an integer. That way, the first int will receive a number 5 and will not include any kind of decimals after the dot. So we are giving up on precision, but we are able to match the type and be able to fit this value into the first int. In this case, since we're using constructor to set up the default values, let's not initialize the first int and leave it for the constructor in here. But in this case, having int and int here, but requiring the function to return as float, we have to convert those to floats as well. Since the second option of the function does provide a float return type, but it requires float min and float maximum. In this case, we can cast our integers to floats, like this. You can press escape to get rid of the tooltip. That way we are supplying an integer value which is then converted to float, so it fits into the first socket of the method, and so do we do it with the second one as well. That way, the function will understand that it should return a float value, which will be then quickly applied to the value of our float type precious number. One thing to consider here is that because this has to be minimum and that has to be maximum, minimum is always less than maximum. That's why we have to ensure that the first int will never be bigger than the second int. And so if a, the argument supplied into our constructor, has a value which is greater than b, we would like to reverse it. Let's imagine that, for example, A was supplied to B as 5 and B had a value of 2. Because of that, first int will be bigger than the second int, and we have to fix this. In this case, we will inbound this piece of code inside of an if statement. Let's say that if everything goes well and B is greater than A, then allow it to perform this instruction. But if it's not the case, we will instead assign the smaller of the values to the first int and the greater one to the second int. Like this, there will not be any errors when we will try to initialize our precious number float type variable with a value. Our range will produce a correct output based on the minimum float value supplied and the maximum float value supplied. After this, our constructor function finishes and we have each one of our variables contain a value. We will return back to our insert combination custom function for this class, and in the first script, let's instantiate an object of type storage. For that, let's get rid of everything inside of start function, which we can use because our class derives from MonoBehavior. And before anything, let's declare a storage type variable, which will be able to hold an object made on the description of storage class. Inside of start, we can create a new object with the constructor function that we've written back there. And as you can see, it requires 2 integers and 1 string. In this case, let's supply just a value of 2, 5, and some text. If we would like to, we could have also stuck variables in here, but we had none specified, so we cannot stick any variables into here with their values. We'll just plug in numbers and text straight from our head. Back in our custom classes, let's expand our possible range of activities in here for the object that is made from this class by expanding the insert combination function to something more interesting. Let's say that insert combination takes one argument as an integer, which we'll reference in here as a variable a. We'll put comma and specify the second one, which is going to be string. We'll call it string s. Anything that falls into the socket, any value, from now on inside of this function will be referenced as a variable a, and so will be for the string variable s. After this function is done executing, a and s will be killed, and that's exactly why we can use the same name for different variables inside of storage, such as a for example, and make use of a in the other function insert combination. In here, as this function is called, inside of it, let's check if the value of a is exactly equal to the value of first int plus the second int. And if it indeed is true, then we'll perform some kind of operation specified by the block of code which comes out of this if statement. But if it's not the case, we'll do whatever is specified after the else statement. Let's see what we can do in the case if the first argument supplied to this function is indeed equal to the sum of the first 2 variables specified in our storage class. In that case, let's end this function, insert combination, via returning a float type value, specifically the value of the precious number, having some sort of reward that way. As soon as the return statement is reached and seen, like in this case, it will return the precious numbers value and the function will end here. It does not matter if there are other pieces of code specified below. If we see return statement, that means that we throw out the value which we need to return and end the function there. But if it was not the case, and the first argument supplied to this function was not equal to the sum of first int and second int, then we can print out a message via the debug.log onto Unity's console. For the message, let's put the insert combination detected a mismatch between first argument and the sum of its first 2 variables. Then, after this else statement, before the function finishes, since it has a return type of float specified in its signature, we must return a float value no matter what. So let's return 0. We can put f to signify that this is a float 0, not double. Double and float, once again, are types which are used for storing floating point numbers, that is, numbers with decimals. Double is more precise than f, than float, and therefore is used by default. So if you put 0.0, just as it is, it will be considered as double by default. But you cannot return double. Your function return type says that it will produce a float no matter what. That's why let's put an f at the end of the value of 0, meaning that we want it to be a float value, not double. In fact, just to be safe, during the first check where we check if the first argument equals to the sum between the first variable belonging to this class and the second one, let's inbound the right side into the brackets so that we compare the value of the right side to the left side and we don't mess up the order of things. Back in our first script, after we've declared container for precious, that is going to be used for storing floats and is of type float, let's not initialize it by default, so it's going to have a value of null. Null is not a mathematical zero. It means nothing. So before we initialize it, those two variables, myStorage of type storage and container for precious of type float, are both having value of null. On the first line, during the start function, myStorage gets a value of the object that is created based on the storage class. From now on, myStorage references this object, and if at any point of time we would like to ask this object to do something, we'll be doing this via mentioning this variable, myStorage. Then, on the new line, container for precious will exchange its null value for something different. It will call a function that was described by the storage class, the function specific to this particular object, myStorage, that we created a second ago. This object's function, as described by the class, requires two arguments. First one is going to be the integer, and the second one is our last words. Based on the first argument, the insert combination function will either return the float value of precious number, specific to this exact object, or it will return a float value of 0. In any case, the result on the right side will become a new value for container for precious variable in this class. And then before our start function finishes, let's check if container for precious is anything but 0. That is, if container for precious does not equal to 0, and since the variable is of type float, on the right side there should be a float number as well for a correct comparison. That's why let's put an F to signify that this is a float 0 and not an integer or double, just to be safe. So if our container for precious does not equal to 0, then we'll execute this bit of code, otherwise this will be done. In the case of success, let's make use of debug.log function, in which we'll put the following message. Success, container for precious stashed a value from the variable precious number belonging to our object. And then let's concatenate the value that is now stored inside of container for precious. Otherwise, we'll produce a sad message stating, oh no, container for precious did not receive a correct value and is exactly 0. This is very important to understand that you can run the start function because your class derives from MonoBehavior. You can mention MonoBehavior and the editor will understand what you mean because you've included those two namespaces, in particular Unity Engine. Because you're using those namespaces, you can also mention other appropriate classes, such as in this case, in the other script we made use of class random, who had a whole set of functions from which we picked a range function to be specific. We could have used this random class because we've included those two namespaces at the beginning of our script. Since none of our classes here in this script derive from MonoBehavior, we can describe them all together just in one script. But in the previous script, we can only afford to have one class in here because it's deriving from MonoBehavior. Let's save our script and see if we have any kind of errors. No, here we have only one warning. Let's see what it means. The private field keyText that belongs to the storage class is assigned, but the value is never used. So we probably declared an unnecessary variable or an argument, which is not used by us later on. Let's double click on it and see where the cursor was positioned. Yes, our storage class, which has the precious number, the first and the second variable, is not making use of keyText. Yes, it gets the value from the constructor function by default and is equal to some kind of string, but it's not really necessary, so we might get rid of it. Let's do so. Having removed its declaration from here, we have to also erase it from memory inside of our constructor function. As you can see, it's highlighted with red, meaning that keyText was not declared before. Let's get rid of this line, and the third argument within the constructor function, C, is not necessary anymore. Let's get rid of it as well. Now our constructor function for this class only takes two arguments. Remember that precious number
gets the value which is generated from the values of the first two arguments.
Because we gave up on the third argument in the first script class, as we create an instance of this class, the object, we don't need the third argument at all. If we come back to Unity, this warning will disappear. Remember that the start function will only run if the class, which describes what should happen inside of the start function, is attached as a component to any of the gameObject within the scene. In this case, it's lying on our gameObject pointLight as a component. In order to be able to instantiate this class in this kind of way, the class has to inherit everything from MonoBehavior. Only then will we be able to drag it to any of the gameObject within the scene of Unity.
Now, if we press play,
this script will detect that it's attached to the gameObject and it will run its start function. It will create an instance of the class storage, to the constructor of which it will pass two values, 2 and 5. After that, container for precious will receive the value that will be generated by us calling to the function of the particular object which we've created a second ago. In this function we'll pass 7, and our last words will be, phew, we got the precious number. because 7 indeed equals 2 plus 5, the insert combination function will see a match between the left part and the right one, meaning that it will spit out the precious number's value. That is, every time we enter the gameplay mode, because we directly typed in those numbers, they will always become 2 and 5, and our first argument will always be 7, meaning that we will never get this bit of code written to the console, but will be always true and will receive this bit of code. Let's check if that's the case. As you can see, the first script class, which derives from MonoBehavior, ran its start function, instantiated the object, and then ran a function from that object, which indeed returned its precious number. We then grab the value that the function produced and stash it in the container for precious. Then we check if the container for precious is anything but 0, and indeed it's not 0. It has copied the value from the function as 3.1. That was the value of the precious number inside of this object. Let's try it a different way now. Remember that in this script, where we specified our storage class, the constructor function takes 2 arguments, assigns the variable in this class a value of the first argument, and then the second variable of this class gets the value of the second argument. We ensure that the first variable has the value which is always smaller than the second variables, and so the function that gets called from the random class, the range function, will receive correct arguments for the minimum and the maximum argument. But because it's random, although based on the first variable and the second variable of this class, since it's random, precious number will tend to be different. And it's going to be much more likely to be different the greater the range between minimum and maximum arguments for this function is. That's why, as we create the object of type storage, let's pass different values into it, such as 2 and 500, for example. The sum of them will be 502, and if we want to receive the precious number, we need to supply 502 as the first argument for the function located in the instance of this class, in this case my storage. That way, container for precious will receive the value of the precious number and not 0. So we'll get this message here. Now the range is bigger, and precious number inside of the instantiated class will tend to get different values more often than in the previous example. Here it's 247, next time it is 152, and so on. One problem with that is, if you have a look at our script, it has no public variables which we can modify in the inspector of Unity. Let's reserve space for them. We will put them later on as the 2 arguments into the constructor function when we create the object. The first one has to be of type integer. Let's give it a convenient name, such as storage object argument 1, and make it 0 by default. Then the second one will be storage object argument 2, which will be equal to 1. They will have to be public in order to show up in the inspector. And now, instead of always specifying 2 and 500 that are fixed numbers and are not going to be changing, let's supply for the first argument of the constructor function of storage class the storage object argument 1 integer and storage object argument 2. That way, as we save the script, if we select the game object with our script, we now have 2 public variables exposed in the editor. As for the sum, the first argument that is used in the function of my storage object, let's not supply a fixed 502 integer, but instead create another third variable, also with the keyword public, which is integer, and let's call it sum. Make it 1 by default. Then supply it here. That way we have a much more flexible way of controlling which sum we supply to the function, which arguments are used in the creation of the object. Let's initiate the gameplay and see what's going to be the result at the end of the start function. Success. Container for precious stashed a value from the variable precious number belonging to our object. We were able to stash it inside of our container for precious since the sum that we supplied is indeed equal to 0 plus 1. If we supply a different sum, which does not equal to the result of addition of the first 2 arguments and initiate the gameplay mode, we will get a second message. First one comes from the function insert combination of this particular object which we were working with, and then the second one is coming from the end of the start function when we tried to check if container for precious managed to stash the precious number specific to this object. For our final try, let's add something like 157, then 26. Let's make it run first, that is, let's supply a sum of like 7, clear our messages and press play. Because 7 does not equal to 183, we get the message coming from the function specific to the instantiated object, which we were working with, about the mismatch between the sum and the values of the first 2 variables of the class, and then the second one comes from the end of the start function. This time let's put 183, and pop champagne as we see that everything went right. In the final example, we'll make use of classes to pass several variables as the return of the function. Let's get rid of the specified classes from our cust classes script. And in our first script, the class of which derives from MonoBehavior, let's get rid of everything inside of it. In our custom classes script, let's declare a custom class that is of course public and name it chest for storing things, for example. Open up and close the curly brackets to signify its area of influence. And for the constructor function, we'll supply public chest, a function with no arguments for now. Let's first decide which variables we're going to be having there. Inside of our objects of type chest, we would like to store several strings. But there are going to be many of them, and declaring them one by one is not of use for us. Instead, let's declare a new type of variable, a fixed and built-in array. Built-in arrays are a very quick way of storing and retrieving different objects that are stored within its cells. Think of this as a big cupboard with many shelves, and you specify how many shelves later on. You have to declare what's going to be stored in the array. In this case, each cell will contain an integer. And to show that it's going to be an array, we put the square brackets just like this, that resemble us a box now. Then we're going to name this array with a reasonable name, such as my array of integers, for instance. We will not initialize it to anything, and we will do so only when constructor is run. We will say that my array of integers becomes equal to the new array of integers. Notice that in this case, we get square brackets inside of which we have to pass a value that will state how big our array will be, how many cells it will have. Let's have a built-in array of size 10. Now we got an array with 10 boxes, and each cell of an array has what's called an index. This one is the cell number 0, 1, 2, and so on. If it's an array with 10 cells, the last one will be 9, because we started counting with 0. That's the chosen convention for iterating through arrays. We'll be doing this in a second. Currently, our array exists, that is, my array of integers now knows that it has 10 cells to work with, and in each cell, let's plant an integer, a random one. We can go on and say that the 0th cell of my array of integers will be equal to some random number, but in this case like 102, for example. And then my array of integers, the second cell, can equal to 120, all the way up to 9. But if it's a huge list and a huge array, we can save this space and save ourselves time. Let's say it's an array with a billion of numbers. We can make use of the for loop. Inside of it, let's declare a counter of type int. Let's name it c, for instance, and let's initialize it to be 0 by default. For the second part of the for loop, let's say that it should be run all the way
while the value of c is less than
the length of our initialized array. That is, its name dot length. As you work with coding, you'll get familiar with those variables and different functions which you can use. It's all a matter of practicing. For instance, I used length many times to figure out how big the array is, and so I quickly figured out that I can use it here as well. Since our built-in array has a fixed number of cells and we just declared it to be 10, we could have said here just 10. But what if we would place not 10 here, but some other value, the variable, which might have actually come from the argument of the constructor function? So we don't know if it's going to be 10, 20, or 30. Well, in this case, it's going to be created with whatever length we would require it to be 10, 20, or 30. But then here, it's not going to be 10, no longer. It's going to be a varying length since the argument of the constructor function supplies a different variable with a different value. That's why we are using the arbitrary variable, that is, length. And finally, every iteration of the for loop, let's increase the c by 1. Inside of it, we would like to do something with each of the cells of my array of integers. Because during the first iteration of the for loop, c will be 0, on the second one c will be 1, 2, 3, and so on. We can say that the cell of the array whose index is going to be equal to our counter's value, that is c, the cell with this index will get a value that will be generated via the random.range, and let's say between 0 and 1000. After this is done, c will have a different value. For example, it was 0, then it's going to become 1, do something, become 2 due to this piece of code, become 3, 4, 5, 6, 7, all the way until it becomes 10. And when it's 10, 10 is no longer less than the length of my array of integers, which currently is always going to be 10, due to the way we've constructed it. Because of that, we will drop out of this for loop and continue doing whatever is specified after. Currently there is nothing, so our constructor function ends there. By the end of this for loop, as we drop out of it, we will have our array with 10 cells have an integer on each one of its cells. It's going to be a random integer because for every iteration it's going to be between 0 and 1000. One thing to watch out for is that although we've supplied integers here, and therefore random.range will have to produce an integer, judging by the arguments that we've input into it, we still should not trust it fully. So let's make sure that it receives it as an integer by casting the first argument of ours as an int, and 1000, the upper range, as an int as well. We would also like to receive a result of this function, the range of class random, as an int as well. And that way we ensure that the type of the value on the right side will fit into the type of the value stored in each of those cells, because we have an array of integers. In fact, if we'd like to have more control on the range of values which get plugged into each of the cells of our array, we can not type directly 0 or 1000, but instead use the arguments which we'll have to declare inside of the arguments part of our chest constructor function's signature. In this case, the first argument will be int, let's say a, and the second one can be int b. Therefore here we can plug in a and plug in b. As we create an instance of this class, the object based on it, we will have to pass two values, each one of which is going to be an integer, which will later on be used to decide upon the value, which is then used to be stored in an appropriate cell of my array of integers. This time let's add a second class and call it an array of chests. In it, we will have one variable which will be of type chest, that is, it's going to be used to store instances of chest, and all the variables which belong to this instance of chest. It will be called bundle. For the creator function for this class, we will have one argument, integer number of bundles. Inside of this constructor function, let's build our bundle to become an array with a size that depends on the value which was passed as an argument into the constructor function of this class. I misspelled number, and I'll add r here and over here. It might get slightly hectic now, but there is nothing to worry about. In a second, I'll explain everything on the diagram. By now, when we've built an object based on this class, using the constructor function, we told that this class has a variable, which is now initialized as an array with this number of cells. The number of cells were specified in the creator's function's arguments. That is, as we attempt to create an object based on this class, we will have to supply an argument, the number of bundles that we would want to. And based on its value, our variable bundle will build an array with that number of cells. Because of that, by now, bundle knows that it's an array with a certain number of cells. Each cell is designated to store an object of type chest. But so far, even though we built the array of chests and called it bundle, we specified how many cells we would like to have based on the argument of constructor function. Even though this happened, the cells are still empty. Yes, they are designed to hold objects of type chest, but none of them were instantiated on any of the cells at the moment. To fill up those cells with the chest objects, we have to go through each of the cells of bundle and instantiate an object on each of its cells. That is, for this iteration of loop, create on this cell a new chest. Remember that as we create new chest, it requires two arguments. The first one is integer, and so is the second one, which will decide on the minimum and the maximum value of integer stored in the chest's array of integers. That's why for the smallest value of such integers, let's put -20, and for the maximum one, make it something like 20,000. In our first script class, that is attached to our light object in the scene, let's call the start function, and in there, let's declare a new variable that is going to be able to hold an array of chests object. We call it myChests with the underscore, just to show you the flexibility of naming. Your name cannot start with the number. That is pretty much the only restriction. We'll call it myChests. And as the start function begins, we can create a new object of type an array of chests and store a reference to it via myChests variable. As we create an array of chests, its constructor function requires one integer that will determine how many chests its array, called bundle, will hold. Let's say that we want to have 3 chests. So what did really happen here? Let's jump back to our classes and see on the diagram. Here we've got a description of the first class, that is, any objects that are made with the rules of chest will have to look at this chunk of code. As we create chests based on this instruction, based on this class, we'll be calling for a constructor function specific to this class, this one. The same story happens for the other class, objects of which, when created, will be made using its own constructor function. An object, which is an array of chests, specified that it will have a variable called bundle that can hold a whole array, each cell of which is designed to hold an object of type chest. During the creation of this blue object, an array of chests, the first thing to do is to grab the argument that was passed during the creation of the object, such as 3, And with this 3, we can tell the bundle that it is a built-in array with the size of 3, the number of bundles. So now bundle is an array of 3 cells. Every cell, once again, is designed to be able to hold an object of type chest. But currently they are empty. To fill each one of those arrays with chests, we will start with the 0 and go all the way until we nearly reached the length of an array. The last cell of an array will have an index of 2, the first cell has an index of 0, and the whole array has a length of 3, since that's the number of bundles that were supplied in the constructor function. And so we start with 0, c becomes equal to 1, then 2, then when it becomes 3, we no longer do the loop. But for the case when it's 0, 1, and 2, the respective cell of the bundle array with our chests, that is its 0th cell, first one, and second one, on each one we instantiate a new chest. That's why we will have a chest right here, a chest in the second cell, and then the last cell as well. The way we create those chests is, as required by the constructor function of the chest class, we need to supply 2 arguments, both integers, which will decide on the minimum and the maximum allowed value for those integers which are stored in the array of integers in each one of the chests. Let's say we start from the very beginning of this for loop, where we create chests for each of the cells of our bundle array. In this case, we create a chest who will have an array of fixed size of 10, the integers of which will have a value between -20 and all the way to 20,000. And this is the case for every single cell of my array of integers. That is the property of every single chest which we'll create. The second chest will also have its own array of integers, which will also have 10 cells, as specified in the constructor function of the chest. And because the instructions on the second iteration of loop did not change, it will also have each cell of my array of integers containing integers between -20 all the way to 20,000. And so is the story as we go another iteration, in this case the third time. Also an array of integers with 10 cells, each one of which contains integer between -20 and 20,000. This is quite similar to a 2-dimensional array, as you can see, and it might be quite complex to understand from the first time. Remember that all of those instances of chests were created as a result of us creating just a single object, an array of chests, right here. In this case we passed 3, that's why our bundle of chests had 3 cells, each one of which contained a chest. In order to fill them up, we had to create a chest and place it into the required cell of type chest. Creating chest required a couple of other additional arguments. That way we've created so much stuff just by making this one object. Now having the reference to this object, having it in our possession, we can do anything with its variables. For instance, we can iterate through an array, through its array of bundles, starting from the 0th cell, going until c becomes equal to the length of my chests.bundle, but we cannot access bundle as you can see. Guess why it is so? Because bundle is private by default. It has to be public in order for us to see it from the other script. Starting from the 0th cell until my chests bundle dot length, because bundle is an array, a built-in one, and each built-in array has a variable length, as described before. Until we didn't reach its length, increment c by 1 and do the following instruction. Since now we've created an object based on an array of chests class, it has a bundle specifically with 3 cells. With this line of code, we're iterating and looking specifically inside of each cell of bundle. And inside of each cell of bundle, we've instantiated one chest. Each chest contains its own array, which is called my array of integers or something like that, containing 10 integers, always. So for every single cell of a bundles array, we can declare a new variable of type chest. That is what's held at this particular array's cell. Let's call it ch. Make it equal to whatever is inside of the currently inspected object bundle of its currently inspected cell. Because we know that the bundle's cells contain chests, we can store whatever is inside of this cell of the bundle in the variable which is prepared to store chests. That is, it's of type chest. From now on, we can refer to this particular cell's contents as ch, referring to the particular chest lying in this cell. This ch will only exist until this iteration of for loop is not over, but then once we're done and we increment c and keep going for the second time, ch will be deleted and then recreated on the new iteration. And now looking at this chest specifically, let's iterate through its own array of integers. For that, we're going to make use of a second for loop. We'll declare a counter w, which will be also starting from 0, until w is less than ch, that is our chest. It's a variable, which should be public in order for us to see it. Public array of integers, which contains 10 integers. So until w is less than ch dot my array of integers dot its length, since it's an array. until this holds true, w should be incremented by 1 and will perform an instruction specific for this for loop. I'll quickly mark out with comments the for loops so that you can see where we are. Now inside of this internal for loop, we can debug.log a message, inside of which we can state which cell of the bundle we are looking at currently. Let's do it with the capital letters. Concatenate the value of C, and then finish up our string with the square bracket. After the square bracket, we can tell the console which cell of the integer array belonging to the chest located at this particular cell of bundle, which cell of this integer array we're currently looking at. Then concatenate extra message, and supply a value that is located at this cell of an integer array that belongs to the currently inspected chest. Make sure that our first script that derives from MonoBehavior is attached to any kind of game object in our scene, and ensure that there are no mistakes in the console. Currently we have one and it's okay. Let's see how we can fix it. My chests cannot become an array of chests. It has to have a new keyword. That way we're declaring that we are creating an object based on this class. We are invoking its constructor function and passing an argument, which will produce us an object with all the variables and things prepared. This is what the first error meant. The second one, my array of integers is inaccessible due to its protection level. Let's double click on that and see where the cursor points us to. My array of integers is probably private. Well, we set it to be public, but probably we didn't save this script. So if we press Ctrl S, that's gonna solve the problem. There you go. As I start the game, the start function from this script will kick in. We will instantiate an array of chests with the bundle array, which has capacity of 3. It will create chests inside of it, and we'll be doing this instruction for every single chest that is stored within this array of chests object. Let's see what it produced us. We're looking at the first cell of bundle, that is the 0th cell. It contains a chest, and the chest's array cell number 0 contains the value of that much. Keep looking at the cell 0 of the bundle, at its chest that is positioned in there. The bundle's chest array cell 1, the second cell of an integer array belonging to this particular chest, has this value. We keep doing this all the way until we've iterated through all the cells of an integer array of chest. Then once it's done, we can increment the count on an external for loop. And now we're looking at the second chest that is stored in the bundle. The first cell of an integer array of this particular chest lying in the second cell of bundle has this value. This chest's second cell of its integer array contains this value. The third cell of its integers array contains this much, and so on, until we reach the 10th cell, this one right here. Finally, we can look at the third chest stored in the bundle and iterate through its integer cells. Of course, the number of bundles and the number of chests will be increased if we increase this number. If you put it to an extremely huge number like 50,000, you'll probably crash Unity, so watch out for that. Guys, this was a very complex example, so if you understood it, take a deep breath and congratulate yourself. I know this was a very hard example. We created objects based on one classes inside of classes of other objects, and then we created those objects inside of our start function. Not only did we do this, but every single class had its own array, which hardened things a bit. But because of this example, we managed to cover an array. See that we can store different things in arrays, different objects. We can make arrays to be able to store integers and then create integers and place them into those arrays, cells. And we also discussed possibility of how you can prepare cells array to be used for storing different objects of different classes. Congratulations, guys. However, if you didn't understand it, have a look at it again and again and again. Try coding it yourself, and I'm pretty sure you'll be able to congratulate yourself along with me, just like I did a moment ago. If you feel comfortable with the previous example, I'd like to expand your knowledge about functions and their return types. As we create an instance of array of chests, our object, we can modify this piece of code to illustrate this example. For instance, we can declare a private function which is only accessible within this class, which will return an object of type chest. This function will be called chestBirth. The function itself will contain no arguments, and its body will consist from just one line of code. That is, it will return straight away a newly created object of type chest. And if we want to create such object, we have to pass in 2 numbers for the argument of the constructor function for the chest object, just like we did on this line. That is, we basically copied it from there. Now we can call this function on this line. It takes no arguments, so don't pass anything into it. But a result of this function will be a newly created object of type chest. Once again, I would like to point out that the return type of this function is not a primitive type like integer or float or boolean, whatever we had before. Now it's a return type of chest. That is, the function will produce an object based on the chest class. We didn't assign the newly created object to be referenced by any variable internal to this function, but instead we just grabbed this object and threw it out from the function, and only then we established a reference to it via this variable sitting inside of this particular cell, the cth cell of the bundle array. If we would like to, we can also reduce down the range for the minimum and the maximum value of integers stored in this chest object. Let's allow my array of integers for this chest to only contain integers with a value between 0 and 2. As you can see, we have 0 and 1 across 3 of our bundles inside the cells of my integer array, specific to each chest. Remember that everything kick-started from this start function, which belongs to this first script who extends from MonoBehavior and whose component was present on one of the game objects within the scene. If it wouldn't be inside of the scene, then the start function wouldn't be triggered and our classes would not be born. There has to be a way to trigger this thing, and one of the possible choices is to use the start function, which is always run from the script components attached to game objects as soon as we press the play button. With this arsenal of knowledge, you are more than well prepared to jump into the work with Unity's interface. Now it's time to talk about Unity's native functions, the ones that are provided with MonoBehavior. So far we've been using just start function for our different actions. But now, because you understand all the classes, all the objects that are built upon the classes, and control variables specified in their classes, because you learned about functions, their return types, different loops and comparisons, it is now finally time to look at how we can utilize this knowledge and finally change something within our world of Unity. Let's close our custom classes with the classes specified in there and just have an empty first script class. In fact, let's close it and create a new one. Inside of my project, in the correct folder, I'll create a new script and we'll call it scene tweaks. Let's double click on it to open it up, and as you can see, the default stencil provides you a function start and update. Both of those functions are available to this class since it derives from MonoBehavior. The editor understands what MonoBehavior is, that it is a class, due to those two lines where we include two namespaces. The Unity's engine namespace, which describes MonoBehavior, and the namespace which allows us to use other functions. Scripting is all about accessing the components of different game objects and changing their parameters, as well as storing values to the predefined variables in your custom classes in order to be able to retrieve them later on and alter your gameplay accordingly. For example, statistics of your player, strength, health, intellect, they all can be stored in the objects made from custom classes. And this time we will change the brightness of this light through our script. Let's click on our light and see that it has a light component. It has different variables, each one of which has default value. You can see a boolean here, bias, which is a float, strength, which is a float as well, intensity float, and range is a float as well. Range controls how far the light can reach into the scene, and intensity is how bright it will be lighting up this range. You can also change the color, each mathematical component of which stands for R, G, and B. Let's change the brightness first and then we'll change the color. Those two functions begin to execute only when the game has started. If you want to create a script which will be altering the state of objects and their parameters of their components during editing time, we will be doing this once again but slightly later on. It is called scripting for an editor. But first of all, let's work around with those functions that are starting to execute only when we enter the gameplay mode. Once we get out of the gameplay mode, things that we did to our objects will be reverted. Because this is a component which is attached to the game object, we can reference the transform, the light, or any other components with their name. For example, we can state in the start function that we want to access the light component, and in there we want to alter the intensity. Let's say that intensity becomes equal to 0.2, down from the current 2.1. What we've done here is we've accessed the component light, traversed down to its variable intensity, then changed its value. Because this script is attached to gameObject, which indeed has a light component, we won't have any problems. In fact, we get an error because light's intensity is of type float, and once again 0.2 is double by default. Make sure to put F to signify that you want to have lower precision, but still to be able to express a decimal point. Float on the right side fits the type of the variable intensity that belongs to the light component, which sits on the same game object as this script does. When we start our game, the start function will kick in, and the game objects which contain this script and have a light component will have its intensity altered. Remember that this is a new script, we called it scene tweaks, and currently on our light we have an old script. So let's right click on it and remove component. We can then go into project and drag our scene tweaks onto the game object with the light component. because it's now on the object and there is a light component on the same gameObject as well, its intensity will be changed. There you go, immediately down to 0.2. We can make use of the update function in my case, which runs every single frame. So indeed, let's set up the light intensity at the very start to be 0.2, and then inside of the update function for every single frame, let's access the intensity of the light component that's sitting on the same gameObject as the script will be, and add a 0.01 value to it. In fact, that might be too much with my current frame rate, so I'm gonna put extra 0 there. The thing is, the quicker your frame rate will be, the faster the light intensity will be incremented, because it happens every single frame. But in my case, where I have an average of 70 frames per second, it's gonna be reasonable. Remember to put f after the number, since the intensity is of type float and not of type double, and we're good to go. It's gonna start with 0.2 and then grow gradually, increasing its brightness. Observe what's happening in the scene as well. Let's kick it up a bit, and then it will continue growing from there. If we leave it running for quite a while, eventually it will become maximum, which is equal to 8. As expected, after we exit the gameplay mode, our changes are reverted backwards to their initial state. However, if we would not like to depend on the frame rate, inside of our update function, we can state that we want to increment the value of intensity by a certain number, for example, something like 0.5 float, but then we want to multiply it by the time which it took to render the previous frame. That can be done with accessing the time class, pressing dot and accessing delta time. As you can see, delta time is a read-only variable because it has only get and no setter, the ones that we've been discussing in the beginning of this tutorial. So it's a read-only variable, and it's of type float. This is how long it took to render the previous frame. This variable signifies a change of time. Because of that, the drops in the frame rate will no longer affect the rate at which intensity grows. Even if you have like 2 frames per second, your time to delta time will be pretty big, and so when multiplied by your number, it will produce the correct value, just as if you would be running with 200 frames per second and the small delta time. Let's run our game and see how it goes. If I could screw up my scene and add extra objects to show you the drop in frame rate, you would still see the same outcome. The light would be shining just as gradually as it did a second ago. But because my objects and my hierarchy is nicely organized here, I'm not gonna duplicate extra stuff around just to show you. You gotta trust me. Multiplying by time to delta time inside of the update function will make sure that the value which you are adding to something is not affected by the frame rate. An alternative to the update function would be a fixed update, also provided by the MonoBehavior. It is run not every frame, but every increment of time. This function is used for physics. Important calculations, which have to be independent from the frame rate, are run here every single increment of time. That's why we can take our light intensity and increase it by 0.5 every tick of time that the fixed update is ran. In fact, this value is too big, so we're going to be increasing by 0.05. And notice that here we don't need time to delta time, because fixed update will be ran an equal amount of times. It's ran every single increment of time, unlike the update function. The latter one will be ran as soon as CPU has extra resources and the GPU managed to draw the image. There you go. You can shrink down or increase the time range after which the fixed update runs by going into Edit, Project Settings, and picking time. Here you can see that fixed time step is 0.02, meaning that fixed update is ran 50 times a second. If we would make it something like 0.6, for instance, then as we run the game, the longer time step will be increasing our light intensity 3 times longer. Via altering the time scale, you can create an illusion of slowed down time or a fast rewind, where you increase the speed at which time runs. Maximum allowed time step is how long your fixed time step can render until it realizes that it's out of time, quits doing what it's doing, and starts over. So your fixed update will take no longer than this amount. Notice that you can access those variables by going into class time and picking either fixed time, which is read-only, since you can only set it in the inspector, as you can see by this get statement, or you can pick timescale, which you can read and set. So in fact, the time class, which is provided via MonoBehavior, is tied directly with this panel. It is the case with many things inside of Unity, such as, for example, the input. Input controls the way of how your buttons that you press on your keyboard should be interpreted, which button corresponds to moving along the horizontal axis or the vertical one, and then inside of your script you can tie them together, horizontal or vertical axis, in order to move in one direction along one of the axes or along some other axis. Hold on for now, we'll be doing it later. However, the moral of the story is the input manager, if you go to edit project settings input, you can access this class by typing in input, and then you can have every single variable which this class provides. For example, you have a rollout of axes where you can see horizontal, vertical, fire1, fire2, fire3, and the horizontal axes are specified to receive a value when you press on your keyboard the left arrow or the right one. Alternatively, you can press A or D on your keyboard for a negative change for the horizontal axis or a positive one. That's why in your script you can type input.getAxis, and it's a function which requires an axis name as a string. Here you can see that the axis name is horizontal in this case, so we can type in as a string horizontal with a Z and the first letter being capital. The function getAxis, if you have a look at it, is of return type float. If it gets an input of A or D, it will throw out a value between -1 and +1. That is, just calling this function on its own here is incorrect. You have to assign the resulting value to some variable. We're moving away from our previous task, so just remember that time and input are just a few examples of how you can access different parts of Unity via their classes and then get the appropriate variables and their values. When we click on this gameObject, which contains light component, transform, and our scene tweaks object, which derives from MonoBehavior, we can see that the light component has the variable color. Let's access it and modify it just in start function. So as we initiate our game, we would like to access the light component on the same gameObject as our script is attached to. Pick the color, there it is. You can see that you can get its value as well as set it. So it's not a read-only variable, like for example fixed time step of the time class was. The value of this variable can be altered, and we would like to put it to be a pure red color. But how do we do this? Inside of our start function, let's access the light component that sits on the same gameObject as this script does, then access its color. Color is a variable belonging to this class of type light, and if we would like to change it, we can either access one of its components such as red, green, or blue, or even alpha, because color contains 4 components. Then change them separately, or we can change them all at once. And for that, we'll have to create a new object based on the class color. It will take 3 or 4 arguments. In our case, let's supply 3 arguments. And if we would like to have a reddish color, we would have to put a maximum value for red, which is a 1.0 float. Then every other argument has to be 0 float. Now this variable will be referenced in this new object, and because of that the light's color will be red. This change will occur during the start function once again. If you have a look, all the components are at 0 except for red and alpha, but we didn't care about alpha in this case. Also, notice that the maximum value for each component is 255. We've discussed something about it in the beginning of this tutorial. Try to remember what it was about. We were talking about bits and bytes. Bit is a set of 8 switches, which can be either turned on or off, 0 or 1. And with 8 consecutive switches, you can represent the values from 0 to 255. That is an unsigned byte. A signed byte can go both ways, negatively and positively, but because of that, it can only go half as much in each direction. Each component can have a maximum of 255, and when they are all equal, that is, the components have the same value, the light becomes white. If one of the light components is more dominant than the other ones, in this case we get the change of light. And if they are the same, but are closer to 0, the light will be shining with white, but with less color. That is, it will be darker. I'll press Ctrl Z to roll back my actions because I liked the way of the light as it was before. Now we're going to talk about optimization.
Notice how we created a new object of type color, only to be assigned to the color variable of our light object.
Let's say that every fixed update we would like to change the color of light to have random components.
Let's say that the color of light
will become equal to new color, basically the same thing as here, but this time it has to be random every single fixed update. That's why, thanks to those 2 namespaces being included, we can make use of the random class once again and access the range function of it. We can supply the minimum and the maximum value. Remember that the range function can work both with integers and floats, so for the first minimum value we will put 0f, and for the maximum we'll put 1.0f. In fact, for the minimum, let's put something like 0.3 maybe, so that it doesn't go down all the way. We'll put comma, because that was the first argument, and we will copy this instruction to the green and the blue argument. Now we'll create a new color with different values every single update, and this new object will be assigned to be carried by the light's color. Let's see how it works. Keep in mind that this is a very bad approach, and we'll see how we can fix it later on. Notice that the light will be changing very quickly, independent from our frame rate. But this is a very primitive example, of course, and it's not the best way to do it. Our mistake here is that we are creating a new color every single time. As we create more and more objects, we reserve more and more space from our memory. My computer has 16 gigs RAM, so I won't have problems for a long time, but some people might experience problems straight away after 5 seconds into your game. That's because we create new objects over and over again and are not reusing them. Instead, let's create our color just once. Let's declare at the beginning of our class a variable that will be able to hold colors and call it myColor. I will immediately initialize it to be equal to the line that we used a second ago. And in the fixed update, we can change myColor's components, such as red, green, or blue, to get a random value generated by this function. Then finally we can assign myColor, the color object, to the color value of our light, which sits on the same gameObject as our script does. Because of that, we can reference the light component with this variable. This is a much more efficient way of writing, and you're not eating your precious memory resources, because you create your object only once, and then later on you just change its components and reuse them. In fact, I get an error here because we cannot call for a range in the class which derives from MonoBehavior. It can only be called from the main thread, that is from start, fixed update, or update functions. Here, as we initialize it for the first time, inside of the class which inherits from MonoBehavior, it has to be a set value, such as for example 0.7, 0.4, and then 1. Of course they have to be floats, so make sure to put f after the values. Now we won't have this error as we run our game. This way is a much more efficient one, because if you leave your game running for a long time, you won't have any problems, especially if you have many gameObjects with the light component and your script attached to them. Because, let's say, if you have 20, you take your memory consumption and you multiply it by 20 straight away. Keep in mind that creating objects like this based on their classes is resource consuming, so try to reuse them as much as you can. Here's another problem which might occur. Let's say that we create a vector3 variable, which is kind of similar to the color one, but not really. And we create a new object of type vector, and it's similar to color because it's taking also 3 arguments upon its creation, which are also floats, but they're not bound to be between 0 or 1. Here we can say like 5, for instance, 12, and 16. Floats, of course. And then let's copy this line, change some arguments a little bit, and call this one my second vector. Here we've created 3 objects, that is, we've reserved that much space on the memory. Inside of the start function, let's make use of the variable myFirstVector, and because it's a variable which can hold vector3, let's make it reference the object that my second var is referencing. Because it's so important to understand, I will show you even on the diagram. As we declared our vector3 myFirstVector, we created an object to fit into it. Once we've created our vector3 object of type vector3, we reserved some space on the memory. And then as we created the second object, we also reserved a space for the second object also on the RAM. So now everything else will have less resources provided by RAM, because our newly created objects of type vector3 are now occupying 2 respectful spaces. We can retrieve them at any time by calling myFirstVector. That is, myFirstVector keeps track of the space on the RAM reserved for this object. And my second vector keeps an eye on the second part on the RAM reserved specifically for this second object of type vector. As soon as we say in the start function that my first vector is now going to be referencing whatever my second vector variable is referencing, we will lose the connection between the first object's space on the RAM and my first vector, because now it will be referencing the same thing as my second vector does. And this object is lost forever, the first one. RAM is a huge array of resources, and if you lose the connection like this to your previous object, you'll no longer be able to restore it. In C++ you can, but not in C#, and this will cause you to leak some objects. This object, because it's now not being referenced by anything, is considered garbage, and it has to be removed from the RAM automatically by the garbage collector provided by .NET, the framework with the help of which the C# language is working. For some period of time, this place will be occupied. That's why although you can reference this object with both my second vector and the first vector now, starting from this point in time, you've lost the link towards this object. And now it's garbage. It has to be removed automatically by the C#'s garbage collector. Watch out for such mistakes and don't make them. Make sure that you reuse your objects, since back then when we were creating a new object of type color with different colors and reassigning them to the color variable of light component, we had the same mistake, since we were creating new objects, making them being referenced by the light variable, taking up more and more space of RAM. That is, don't lose the link towards your objects on the RAM, and reuse your variables, like I've shown you in the example with light color and in here.
continuing the previous idea, once we created an object and therefore reserved some space on the RAM, then if we lost the connection to it and none of our variables are referencing this object anymore, it becomes garbage. With this line of code, we made it point towards this part on the RAM. And similarly, if we create a vector3 type variable, this variable will now be holding a link towards the second object of type vector3 that we've created here. As soon as we ask the first vector to drop its reference and stop pointing towards the first object, but instead to now reference the second one along with my second vector variable, this object becomes a garbage and just occupies some space. We've learned that and it's okay. But what also happened is my first vector received its new value as a reference. When you say at some stage of your coding that my first vector becomes equal to something else, such as an object or whatever, and you give up on the previous variable, if this variable's type was some kind of class, that means that you are receiving a value by reference. But if you declared a variable of a primitive type, such as float or an integer, for example, and let's say you initialized it to be 5 by default, then if you say my int receives the value that is first of all cast down to be an integer, and let's say it's my first vectors dot x. There is the first component of my first vector that is cast down to an integer and assigned to my int. In this case, because my int is of primitive type integer, it is being passed by a value, not by a reference. That is, my int had some space reserved on the RAM for its value, and so did my second vector for its 3 sub-values, the x, y, and z. And of course my first vector is pointing to the same object and is able to see and perceive those 3 x, y, z sub-variables as its own. When we want to reference the value inside of the x variable that is of primitive type float, my integer will still keep pointing at its own space. You simply copy the value from the area on the RAM dedicated to the x variable belonging to this vector object. You simply copy its value into my integer's space on RAM for storing its value. You've just assigned a value not by reference but by value. If, after that, my second vector, who is pointing to the same area on the RAM as my first vector, if its first component, that is x, changes, my int copied its value from before. It's not pointing to x of the second vector. My int will remain containing the value of x from this part of time, and it's not going to be affected by the change in this area. This is very important to understand. Copying the value by reference occurs when you switch the pointers and begin to reference another object with your variable. Then this variable will be affected if some other variable who controlled this object before changes, and vice versa. If the new variable forces the object to change, it will be reflected on some other variable who is referencing this object. But if you try to copy a primitive value such as float or an integer between your primitive variables that hold an integer or a float, for example, you'll simply take a snapshot of this value and paste it into the separate cell that is dedicated for this primitive variable of yours.
This time let's try something more complex. I have downloaded pictures into our folders with our project, which are pretty small and are combined to be sitting in one reasonable sized texture. I've created a folder called resources. This is a Unity's interface reserved folder, so if you create resources folder, it will have a special meaning. That's why you have to make sure that everything you position into this folder is necessary, since it will persist throughout of your game. Pay attention to the naming convention and the capital letter at the beginning as well. Here you see that I have a 258 by 258 picture with an alpha channel. It's acting like a mini atlas. Because it's so small, I could have actually be smarter if I have some other textures that I used for my graphical user interface, for example to display health bar interface or any parts of GUI or heads-up display. I could have placed those little things not in this texture, but could have added them to the big texture containing all of my GUI. The less texture files you have, the better it will be for you, unless the textures themselves will be huge. But in my case, because I have no GUI currently developed for this game, I'm just sticking with one small texture, which contains an alpha channel, which is equal to 0 pretty much everywhere, meaning that everything except for certain parts is transparent. Here I have an icon of a villain, an icon of monk, and an icon of monster or zombie, the green one. This example will not show you any kind of creatures running around the scene in 3D world, however we'll make ourselves more familiar with classes, and we'll actually be able to relate them to some objects within the scenes that way. As we'll create a monster in our world, we will see his picture pop up in front of us, right on the screen, through the use of graphical user interface, in other words GUI. As we switch between characters, between monk, monster and the villain, their stats will update in the text above, also displayed on the screen. So let's see how we can do this.
Before we do anything, I'll select my imported picture that was saved as a PNG format. Let's go from texture to sprite to dimensional and user interface. Then we can pick between either having a single sprite, that is the whole texture will be considered as one sprite, or multiple sprites. Sprites are two-dimensional objects used in graphical user interface. They are quite efficient, and you can create multiple sprites out of one texture. This is exactly what's going to be done with this setting. Now, to set up multiple sprites, we can go to Sprite Editor, then left-click and drag onto the zone, onto the areas, to cut out a new sprite out of the specified area. You can set up the size dimensions and position on the settings, and also pay attention to name. Make sure to name your sprites correctly. When I left click on the area dedicated for this sprite, you can see that I called it monk and then subcomponent to specify that it's a sprite that was derived from the bigger texture. This one is a villain sub and this one is zombie sub. Once you're happy with your setup sprites, we can click apply, close the editor, and now you can see that we have 3 subcomponents of this texture. That is, we produced 3 sprites out of it. Maximum size should be not 1024 but 256 as stated here. This will also influence your size of the texture, and in my case compressed is the best option since I don't care about colors too much, being pretty happy with black and green colors to show the difference. Filtering mode can be point, but it does not really matter since we're not going to be showing our sprites at an angle to the camera, so point in this case is good and is going to be most efficient. Then click apply. Also, an interesting fact that you might encounter is that if you save a texture in Photoshop, and it's going to take something like 400 megabytes for instance, you tried to save it with a reasonable size, but then once you drag it into Unity, and after you go through those settings, you suddenly see that the size of the texture is not 400, but something like a 1 megabyte, 0.3. That's the actual size that your picture takes up in RAM. So there is no point in saving space at the Photoshop stage and saving it to a crappy quality, but with something like 400 kilobytes, if in Unity it's still going to take 1.3 megabytes. Try to save with the best quality until it pushes actually the real size boundary inside of Unity. Now we have 3 subcomponents, 3 sprites, and it's time to set up classes for our scene. This time we will also explore more about Unity's interface, in specific about how we can target different components within the scene and how efficient or inefficient it is. To keep things neat, let's go into our folder, which we've picked to be containing our scripts. We call it tutorial 8 scripts, and open up our custom classes. This is the script where we'll describe our classes that will contain stats for monk, zombie, villain, and perhaps a 4th class, which will contain a variable common to all 4 creatures. Let's begin with the base class from which the characters will be deriving. Since none of our classes inherits from MonoBehavior, we can describe more than one class in our custom classes script. So let's declare a public class and call it common stats. It might be evident by now that classes are also referred as types sometimes. That way, we're right now busy with defining our type and explaining what it should do. I would like to once again revise the get and set methods. So in this case, let's declare a private or omit the private keyword since it's implied if not specified, and declare an integer health. I'll not initialize it at this stage, but health is common for all the creatures that we're going to be working with. That's why it goes into here. Also integer speed. In this case, those variables are private. That means that nothing else, not even the class that derives from this base class, from the common stats, will be able to access and modify this variable. In this case, let's declare a public integer and declare health variable, and maybe the private ones let's put underscore in front of them to show that they're different and are out of reach of other classes. For this one we'll put curly brackets, and inside let's specify a get method, type in return and our private variable, put semicolon, and also for set method let's type that any value that comes into this variable will be assigned to our private real variable underscore health. So it becomes equal to the value that comes into the public integer health. Make sure to put the semicolon at the end and you're good to go. If you've never seen this notation before, jump back in the time of this particular tutorial because we covered it slightly earlier. Now any classes that are referring to the objects created from this class will be able to refer to this variable, which will both absorb the value and then pass it to this one, to the hidden private health variable, the real one, or we've made it so that it's allowed to retrieve the value from the real health and then return it as if the value would belong to this public variable. So this is like a messenger. It does not contain values. It's just passing and retrieving them back and forth from underscore health. Same story happens for integer underscore speed. It also has to have a public same type variable as the underscore speed was, that is int, and this time it will be without underscore since it's a getter and setter variable, which will both be readable and also settable. Remember to put semicolons before your enclosing curly brackets for both set and get instructions. Let's make a constructor, a protected constructor. That means that the method, or the function in other words, can be called either by the class itself or by the classes that are deriving from it. Constructor function being called by the class itself does not make much sense, because that way we're talking about something called singletons, which will be covered later on. But protected keyword means that any kind of class that inherits from this one will be able to call its constructor. A constructor function has to have the same name as the name of the class. In this case, it will take two arguments, both of type integer, so that their value can be fit perfectly into the appropriate two variables specified before. And let's refer to this one within our constructor function as h, and then the second one should be integer s. You can have multiple constructors if you want to, in case if you want to have overloading. That is, you can have an option of passing either 2 arguments when calling the function, or 3 or 4, but that way you have to have different constructors specified with different numbers of arguments, etc. We're gonna do this now. However, let's finish up this particular constructor for now. As we receive a value upon the creation of this class, in the first argument, let's assign this value to our health getter and setter variable that is going to be then stored in the private variable, which will be done by the health variable itself. So all we need to do is specify that the health messenger variable receives a value of h, and then the speed messenger variable receives the value of s. That's it, that's our constructor done. But let's say we want to have another constructor, for example, also protected one, the one that can be only called by the children of the class, the inheriting classes, and this one takes no arguments, for instance. Here we'll set up the health to equal some kind of default amount, for example 4, and speed also 4. Now when we have two constructors and the base class common stats made up, let's create some other subclasses which will be deriving from it, or inheriting in other words. This one will be public class monk, and also I'll duplicate it a couple of times, then rename the names to be something different, for example villain, and let's say zombie. Each one of them will inherit from common stats. I'll double click on it to select the whole word, and then after monk I'll put space, column, and then paste my common stats to signify that the class derives from common stats, and then has the access to any property that is marked with either public or protected within the common stats, as well as to the functions that are marked this way. In addition to the speed variable and health one, our monk will have a third one. It will be of type public float and will be called dignity. Any class outside of this one can access this variable directly and change it. We're not making use of getters and setters in here because it's quicker this way. However, you have to pay attention that you don't accidentally change dignity or anything by mistake. The villain will have a public boolean variable called feared, and the zombie will have a public boolean type that can be only true or false, hungry. For the constructor of monk, we'll just put one constructor without any option to overload the class. For the arguments within the constructor, we will first of all put the float d, so that this argument can be used to assign a value to our dignity variable. Then the second one will be used to initialize the value health, and the third one will be used to initialize the speed. Inside of the constructor, let's state that as this function runs, dignity becomes equal to the value of d, the first argument. Notice that if we try to access the speed variable that is public and is the messenger variable, that will take care of setting and rewriting the variable of the real speed variable. If we try to access it, we can do so, only because it's public, or if it would be protected, we could do so as well. We can set it up to be equal to the third argument, the speed. And we can do so with the public variable health specified in the base class as well. It becomes equal to our second argument. That way we set up both dignity, speed and health just from this constructor function. We don't have any other constructor functions and don't provide alternative to this one, meaning that there is no option of overloading the constructors.
And choosing in which way we want to create our monk object that extends from the common stats class.
It's just going to be this one all the time. As you create the object of monk, you will always have to pass 3 arguments no matter what. The old-fashioned way and the more correct way of initializing your variables from the class which derives from some certain base class would be not to write it like this and assigning values to the public variables declared within the base class, but to instead put after the constructor function of your monk, put a colon and then type in base. Then in base, drop just the names of the variables. That is, base class has 2 constructors, and let's do the first one. In this case, it awaits for the first value to be an integer, then it's going to be processed to be assigned to health variable, and the second one is speed, also an integer. As we have declared the variables and their types here, we can then just grab the names of those variables, such as health and speed, and then pass them in like this: health, comma, and speed. We will not make use of those last 2 arguments within the monk's constructor, but they will be passed to the first constructor of base, which will then be able to initialize its health and speed variables. This is a more correct and old-fashioned way of initializing your class, who is a subpart of a bigger class. That means that as you create an object of type monk, you are essentially creating your object based on this part and the common stats as well. However, if you initialize just monk, you'll have health and speed uninitialized. That's why you also have to call the constructor of the parent class, the bigger one, so that its values are also initialized. And you do it like this. Or the previous way, the easier one, where we set up the public and protected variables between the classes just by typing in their names. Let's do the similar thing for the villain. In this case, it will take a Boolean type value as a first argument that will be then assigned to the feared variable within this class. For the second argument, it will be taking an integer h to be assigned to health of the parent class, and also an integer speed. We're then going to call the constructor of our base class. Let's say that we don't want to have any kind of flexibility within the villain. That is, every single time it's created, it's always going to have a speed of 4 and the health of 4 as well, no matter what. Let's call a constructor of base, and as you can see, if we have two options here. Currently, we can pick the constructor with no arguments, and the second option, if we press the down arrow on our keyboard, we have to pass int health and int s if we want to have more control on the initial stats of our character. In this case, we're going to be using the first constructor, so we're not passing any values, and they're going to be initialized to be 4 by default. Because we're not passing any kind of values for health and speed to the base that way, we can get rid of us declaring the second and third argument of our villain constructor function. Our villain constructor function, the only one, will set up its public feared variable feared to be equal to whatever the value was passed to the villain upon the creation of the object based on the villain class. It's going to be either true or false. And since we're calling the constructor of the base class like this, it's going to use the second constructor, which does not take any kind of arguments, and will initialize the health and speed to be equal to 4. In the case of zombie, I'm going to declare a constructor function, which will take Boolean type variable. I'll call it hu for hungry, whose value will then be assigned to the appropriate hungry variable within this class. This time, let's do it the quickest way. Let's also have our constructor require other two variables, that is health and speed. I'll declare a type of integer and call it h within this constructor, and then integer s. I will now omit putting column and then base, and just do it the quickest way, since you already know how it's done properly. Here, I'm going to assign to our hungry variable within our zombie class the value that was passed through hu socket, and then I'll assign the value of h to the public health messenger variable of common stats. Health will then grab this value, then we'll take care of it further on, setting and passing the absorbed value to the real variable of the base class, that is underscore health. So here, the messenger variable will receive a value of h, and the messenger variable speed, that is also public, will receive a value of s. Remember that we can refer to speed and health, which belong to our base class, because they are containing the keyword public. It would also be possible if they would be with the keyword of protected, meaning that they can be accessed by the classes which are deriving or inheriting from this bigger class. This way we have declared one big class, the variables of which are common within the next 3 classes. This way we've saved ourselves space of constantly typing the same variables over and over and over again for each of the classes. If we wouldn't write this class, we would be required to type in health and speed, health and speed, health and speed for each single of the classes. But now, because they are simply deriving from common stats, it's just a matter of setting up stats which are different between monk, villain, and zombie. That is, monk has dignity, villain has feared, and zombie has something else, such as hungry variable. It's just a matter of setting up those via the constructor for the appropriate class, and then calling up the constructor to assign the values to the variables health and speed. Because we now have 3 blueprints, or 3 classes, each one of which has a complementation in the form of common stats class, we can now make use of them in the other script. However, I noticed one thing, is that we're still lacking one variable that is common to all the creatures. It is the name variable. That's why in the common stats I'll pass a private string name, actually underscore name, because it's the hidden one. Let's provide getters and setters, just like we did before. Don't forget about semicolons. I'm not writing them on different lines, just to save space. And this time we have a variable underscore name represented by the getter and setter variable name. In the constructors, let's initialize them properly. For the default constructor, with the one that doesn't have any arguments, I just put default creature for the name. But for the customizable one, I'll supply a third argument of type string, and I'll put n, just to stand for the value of name, the one that's going to be referred like that within our constructor, until our constructor function isn't over. and then assign to the name messenger variable, or directly to the underscore name since we're in the same class. But to the name, we're going to assign the value of the argument n. That way, once this constructor is called, we have all three variables initialized. And also for the constructors within the monk, villain, and zombie, let's supply another argument, string n. In this case, we pass a third argument like this, following the convention discussed previously. For the villain, we're calling the base class. Since we want to make use of the default constructor from the base class, we shouldn't pass any arguments to it. Notice that we would like our villain to have all the time health initialized to 4 and speed initialized to 4 as well. That's why we've chosen before the constructor for the base class without any arguments. However, now with the introduction of the name string variable that has to be also initialized and belongs to the base class of common stats, now we cannot make use of the base class, since the name will always be default creature, and you might want to have different villains, each one of which will always have its health and speed initialized to 4, but the name should be different. Because of that, we're now forced to use the constructor with 3 arguments, but now we won't be passing any kind of variables pre-declared in the constructor function of villain, except for just one more variable. Let's declare a string variable n, and then in the base, let's pass for health and speed the values of 4 and 4. That's why every single time the base constructor during the creation of villain object is called, it will always be grabbing the values of 4. And we can still specify the name, which is going to be the variable n that was declared in the arguments of the constructor of villain just a second ago, via string n. Now we have zombie remaining. It also has to supply a string value to the constructor of the base class, but in the zombie case, remember that we didn't make use of the constructors of the base constructor, because we took a shorter path, just directly assigning the values to the public messenger variables, which took care of it further on. Here we're saying let the name variable that is public and belongs to the base class, let it have the value of the argument n, like so. That's why in this case, in the case of zombie, we're not even calling the constructor of the base class as we create the zombie object, because everything, all the initialization happens within the constructor of zombie. Unlike in the previous example with monk and villain, where we've decided to go a more correct and a more old-fashioned way, calling the classes constructor and the constructor of the parent class as well. When we save our script, we now have one parent class, which contains the variables common to all other 3 classes, mon class with the variable dignity, villain, which has all the variables described in the parent class, but now it has no dignity but a feared variable. And the same story happens for zombie. It has its own special variable called hungry. They are all initialized within their constructors, and we can make use of them in the other script. Inside of Unity, I'm going to double click on scene tweaks and get rid of anything that it contains except for the start function and maybe update. Notice that this time we're using namespace Unity Engine, just like as always, system collections, and this time Unity Engine.ui, user interface. This will allow us to work with the GUI that was introduced in 4.6 and manipulate images on the screen easier. Here, in the scene tweaks class that derives from MonoBehavior, let's declare a variable of type monk, and let's call it mymonk. Then the second variable, also villain, and of course zombie, myzombie. As the start function kicks in, when we enter the gameplay mode, we will initialize mymonk variable that can carry objects of type monk by creating a new object that is based on the monk class. Because of our constructor, monk takes in the float d, int h, int s, and n, standing for dignity, integer health, s for speed, and n for name. Last 3 arguments, of course, will be passed to the constructor of the parent class, and after it's done, monk will have its 4 variables initialized and ready to be used. For the dignity, let's input something like 10.0f, because it has to be float, not double. For the second argument, I'll supply a value of, let's make our monk have a health of 5, and the speed has to be something like 4, similar to the one that we've supplied by default to the villain. As for the name, let's call this monk, let's call him Patrick. Remember that you supply the value of string within a pair of double quotation marks. As we finished creating this object, let's put semicolon to signify that we finished working on this instruction. We have to also create an object of type villain, which has a constructor that takes just 2 variables, boolean f, that is it feared or not. In this case, the villain will be spawned with the variable feared equals to false by default. As he's instantiated, he's never feared. This object will have a name, YOLO Swaggings. And finally, myZombie will grab a reference to the newly created object of type zombie, whose hunger is going to be false by default. The second argument is health. Let's make it equal to 3. The speed will be 6 because it's the quickest of all the creatures described in here. and string n, let's call him Stinky. Once again, we have to supply 4 variables upon the creation of this object, and only 2 as we create the villain, because of the way we've set up our constructor functions for the villain, where it takes only 2 arguments, and the zombie, where it takes 4 arguments. That is, as the game is run, we immediately create 3 objects: new monk, new villain, and a zombie object. Now we have 3 pointers that are pointing towards those objects, and the objects are therefore not considered as garbage, since they're referenced by some variables. Inside of update, we're going to make use of a couple of new approaches, and in particular we're going to make use of the input class. We're going to be testing if we press any key during the update function, and remember that this function is ran every single frame and is quite heavy on resources. If you supply too many actions during the update function, it's going to be quite heavy on your game. So whatever you put in the update, make sure that it's low on size, meaning it will put the minimum strain on your computer. Inside of the update, we're going to be first checking if input, and input is the class that supplies different variables. In our case, we are interested in the variable called anyKey, and it's a Boolean variable. As you can see, it's read-only. It has only the getter. It only returns the value to be copied from the variable anyKey, and you cannot set it directly, since there is no setter method specified. The difference between anyKey and anyKey down is that if you keep holding the button on your keyboard, anyKey will be true. But anyKey down is only going to be true within the moment as the button goes down on the keyboard. The action of pressing the button, holding the button, and releasing the button, that is on the key up, not specified here, but those 3 actions can be described by 3 different variables. Here, anyKey means that if the key is going down, is being held, or goes upwards, anyKey will be true, otherwise false. And in our case, we need anyKey down. So if user pressed any kind of button, just the moment of pressing will run whatever is specified within the code after the if check. If no, then fine, we've saved ourselves so much time within the update function, skipping all of those instructions that will follow inside of this if statement. Some of you might think we're going to be registering buttons and then going through the switch statement to save ourselves time, but this is not really possible within the way Unity was implemented. And even if we get some kind of button and then scan quickly through the switch statement, that is quicker than any if or else statements, if we use the switch statement, it only means that we're going to be able to work with only one button. However, during the gameplay, user might press several buttons at once, like he wants to go not forward or directly to the right, but maybe diagonally. So you need to take this into account, and the approach of using switch statement is not useful here. That's why we're going to make use of if checks all the way through. Since everything that we're going to be doing right now is going to be encompassed via the if statement, there is a great chance that if the button was not pressed, there is a big chance that the code will not be executed. For example, in the cases where the user did not press any kind of button. That means that the update will be really short during those times, and the game will be running very, very quickly. But if we do need to process the key, we first do the check just like usual if any key was down, and then start to figure out which key was pressed. After the input any key down has been successful, let's check for if the input.getKey, which is a function returning true or false, depending on the variable passed. And here we're going to see if the key code.m was pressed. So if the button m was registered, the get key for this particular argument will return true, signifying that basically the m was pressed. And if it happens, we're going to do 1 bit of code. We will also do a check for an input where we get the key, and we'll pick the key from the enum key code. We didn't discuss enums yet, and we surely will in a second. But the enum is basically a collection of variables, and you can pick any that was specified within there. This enum is pretty big, and it describes all the values standing for each of the buttons. In this case, we're checking if we pressed the button V, standing for villain. And if yes, then some other piece of code will be executed. And finally, we'll make use of the input class's getKey function once again, and we'll see if the value picked from the enum key code, the value z, will produce a return type of true. And if yes, then the result inside of the brackets of if will be true, and the following code will be executed. I would like to switch between different characters, and I cannot have more than one character in this example on the screen. I could have straight away positioned them all up in the front on the screen, but I want to show you the interactions between them. That's why if any key down was true and some key went down, if the first condition inside of it is not true, we will do the second one. Otherwise, no. That's why we'll put else in front of the second if statement. So if true, we do this. Otherwise, if this true, we do this. Otherwise, if it's not true, we do the third statement. Notice the interesting thing. See on how many checks we'll have to do. let's imagine that we indeed got any kind of key down. The first check, the one that is always going to be performed, is this one. Depending on if it was true or not, we are now have to either check or not check with the second statement. So we're doomed to check the first one, and let's say it was false. Now we have to check the second one. If it's true, then we will omit checking the third one, and it will sum up to the total of 2 checks. And in the worst case, we will be doing 3. That is, this one is false, we had to check it. Now we check this one, it's false, and because it's false, we will check this one. Back in our scene, we've imported the texture file in our resources folder, from which we've created 3 sprites. They will be used to be shown on the screen. However, in order to be able to access the space of the screen and to be able to show something different than the one that camera sees, to overlay our own images on top of the screen, we have to create something new. Go into gameObject and create UI, canvas. Canvas represents your whole screen that is currently visible. If you change your screen, that is the one on the game, to be larger, the canvas will expand. And if you shrink it down, the canvas will become narrower. The way GUI works since 4.6 is that you can drop different elements onto the canvas, and they will be drawn on top of the screen after your scene has been projected into the camera. Having selected our canvas, we can go into Component, UI, and then stick an image component. Or if we would like to, we can create a gameObject of type UI to be image as well. The image became its child. And as you can see, on our canvas, we can drag it across the screen, and it's going to be positioned to the appropriate area on our screen. Those arrows in the center are called anchors. Depending on where you position them, the image will be either stretching in appropriate ways or being clamped to a specific part of the screen. For example, if I position the image here in the center and try to resize the window, because the anchor is specified to be in the center of the canvas, the image will stay in the center of the game screen. But let's say if the image is dragged to be on the left side, when we resize our screen, the image behaves differently. Notice that the anchor is composed from the 4 arrows. If I press F to zoom up on my image element, that will be carrying textures supplied by us later on, the anchor itself is made out of 4 subcomponents, the 4 arrows. Unity created an excellent way of resizing and keeping track of your images, because those arrows of anchors can be dragged into the corners of your canvas, into the corners of your virtual screen. And each element on the canvas will have its own anchor. Here you can see that those arrows are positioned in different corners, and because of that, if we try to resize our game view, the image will be scaling appropriately to the whole screen. If we set our anchors to be exactly in the corners of our image file manually, then as we resize our game view, the image will be scaled in a percentage as well. So depending on the aspect ratios of your screens and their resolution, you'll have different sizes of the texture taking different portions of the screen, the way you desire. Because we've manually repositioned and readjusted the anchors, we now have a custom representation for the anchors in the rectangular transform component. We can left click on it and then set up the anchor to be somewhere in the top left corner, for example. That way, as the screen is expanded, picture stays relative to the top left corner, since all the 4 arrows composing the anchor point are positioned in that particular spot on the canvas. After repositioning your image, its aspect ratio might have been changed because we began with the rectangular image and now it's stretched upwards. We can resize it by re-entering the width to be 100 once again and the height to be 100 as well. If you'd like to, you can also resize its scale in the X, Y, or Z component. It does not really make sense to scale it in the Z component along the Z axis since it's flat. But you can reposition them to have a different position in Z to make sure that they lie on top of other gameObject UI elements, such as other images or inventory parts. This is a gameObject which has an image component, a rectangular transform, and a canvas renderer. The image component has different variables, amongst which is the default multiplicative color, which will be multiplying the sprite texture supplied into the source image. It has to be sprite. It cannot be an ordinary texture 2D that is used for texturing assets within your world. It has to be sprite. And we did set up sprite at the beginning of this example. Here, by default, let's attach just an image of monk by simply dragging our sprite into the appropriate field. Since the outline is quite dark, let's position it somewhere to the reasonable place where you can see it on the screen. Somewhere here, for example, maybe in the middle, and then set the anchor to be in the bottom center part of the canvas. All 4 arrows are aligned within 1 dot. That means that the picture will not be rescaling with the screen. It's just going to be stuck to the center of the screen. Here you go. As you can see, when I resize my game view, the values for width and height stay the same in the rectangular transform component of our gameObject containing the image component. As we press the buttons within our script, it's going to make sure that we switch those pictures around. Remember that our sprites are belonging to the icons file, they are children of it. It's positioned in the resources folder. Resources folder is the Unity's officially reserved folder, and it has its own particular meaning. That's why we've picked resources and placed our objects in there, because later on we're going to be retrieving them from this folder at runtime. Returning back to our script, let's see, if we pressed the key code M, we would like to display a picture of Monk. If it's V, then the villain, and correspondingly if it's Z, then the zombie's sprite. Our script is called scene tweaks, so I'm gonna pick an object within my scene and zoom up on something within my scene. For example, my camera. On this object, my camera, I will stick a script, scene tweaks, the one that we've been working on. As you can see, it's another component. I have different scripts, but you shouldn't care about them. Many of them are disabled and are not working, and other scripts are for adding different visual styles to the resulting picture. Our scene tweaks is an enabled script, but it doesn't have any public variables exposed. That's why we don't see them in the inspector. And we should not see them really, because the script will take care of them, instantiating appropriate objects and plugging them into appropriate variables to reference those objects. It's going to happen on its own within the script, so we're not exposing those variables, my monk, my villain, and my zombie, in the inspector anyways. Because we now have the script working on the camera, as we enter the gameplay mode, the start function and the update will be working, since the script belongs to the object that is described in the hierarchy of our current scene. If the script would not be applied to anything, then those two functions wouldn't run, since the class, deriving from MonoBehavior, would not be instantiated. Now, because it belongs to the camera, our canvas object is a different one completely, and we cannot reference any components on the canvas directly from the script. We first have to find the canvas within the scene. Remember that back on the light, if I click on the light and select it, in previous examples we had a script component attached to it as well, and from that script we could say, okay, during the start function, let's say access the light variable, dot, and then access the variable within this light component, for example intensity, and change it up a bit. We could do that. We could say light dot intensity, because the script belonged to the same game object as the light component did. And the way MonoBehavior worked was that the light component could be referenced with the shortcut lowercase light. And the same story could have happened if we would like to access the transform of the same object to which our script was attached to. We could just say transform with lowercase t, then dot position to access the position, and then for example dot x to read the value of x. Here, because our camera contains the script, but the canvas is a different object with its own components, we will have to do rather slow operation, which is not advisable when working on serious games. We'll be looking at how we can improve this later on, but for now we have to somehow find the canvas object in order to be able to reference its child, the image object, which contains the image component which we want to alter and substitute the pictures back and forth into it. And it has to be done while the script is located at the camera object. So back in scene tweaks, that belongs to the camera, we're going to declare a variable of type image. That means that this variable will be able to store a reference to the component of type image. And we are able to mention this type within our script because we included the Unity Engine user interface namespace up there. Because of that, if we type image, it makes sense to the editor. And our variable being able to carry reference to image component, we're going to call it underscore image component. In fact, I'm going to rename my canvas as the screen canvas just to show you the versatility of how the objects work. Something like screen canv. And it's a child game object, child of canv, image. So now from camera, which has the scene tweaks and has a variable of type image that can store reference to the image component, from this script we have to find an object called screenCanv within our hierarchy, then access its first child, child of canvas image, then search for a component called image on this game object, and then stash the reference to this image component to our predefined variable image component right here. We're going to do all of that inside of our start function, because start function happens only once, and the operation which we're about to do is very resource consuming. It's not efficient and is not used in serious games. First of all, we're going to say that our image component variable, that is private and is not seen in the inspector when inspecting our script. The image component will get the reference or the value of whatever is going to be on the right side. And on the right side, we're going to be working with the class gameObject, which provides us different functions and variables. The one that we're looking for is called find, asking for a string value, which is the name of the object we're searching for. In there, we need to supply the exact name that is shown in the hierarchy of our scene, and we're looking for a screen canvas. In order to be safe, I'm going to select the screen canv, then press F2 to rename it, Control-C its name, then click on the empty space to cancel, and then just paste it into here. That way we're sure that we are supplying exactly the same name that's in the scene. Once we find this game object, we need to somehow reference the first child of this game object, which is a game object as well. Once we found this object, we're going to put dot, then by typing in transform with the first letter being lowercase, This means that we are accessing the transform component of the game object which we are currently at. The transform contains all sorts of things. Once I put dot, you can jump back and forth between transform components, audio components, the collider components, the game object itself. It has different functions. From the transform you can jump even to the light that we've used before. But in this case, we are interested in the function called getChild, which takes in an integer, the index of the child, and we know that screen canvas has just one child. Its index is 0, the second child would have an index of 1, the third one of 2, the fourth one of 3, and so on. Just like in an array, where you reference the first cell with a number of 0, the second one with a number of 1, and so on. By asking the gameObject class, provided by Unity Engine namespace, we are asking from the gameObject class to use the function called find. In there we're supplying a single required argument, which is the name of the object which we are searching for. This function will return a reference to this object, and of this object we would like to access the transform component. The transform contains many variables: position, scale, rotation, but it also provides several functions, amongst which is the getChild one. And the getChild requires one argument, that is the index of the child. And the first one has an index of 0. There is only one child to speak of which, that is the child of canvas image. And once we get it, if we would search for some kind of old component such as light of this particular child of canvas image or anything, we could do so by typing in just the light variable or the transform, for instance, to access the particular transform of this exact child of canvas image object. But in this case, we would like to access an image component. And image does not have a shortcut variable. So if you type in image, you'll see that it does not mean anything to the editor. That's why you have to search for a component explicitly by using the gameObjects class function called getComponent. It has its own notation, which we didn't talk about, but before the round brackets, you have to supply the type of the component which you are searching for. We're searching for the component of type image. And inside of the round brackets for arguments, we're not passing anything. Just passing which type of component we're searching for is enough to be able to retrieve this component image from this particular object. We're able to use getComponent in here because the initial class which we were working with was gameObject. GameObject contains both of the functions find. It knows about what transform is. The transform knows that it has the functions getChild and other ones, and the getComponent is explained by the gameObject itself. That's why we made use of all of those functions just in this one line of code. So we found the canvas, from its transform we found the first child, and from this first child we retrieved the image component. The result of this line is then assigned to be referenced by the image component variable predefined by us before, and the image component variable is able to hold anything of type image. And the image is the component we were searching for, so the types match. The type of the right side matches to the type of the left side. And now this particular component of this particular object is being referenced with the image component. This all happened in the start function, and gameObject.find is a very resource extensive function, just as getComponent is. We'll see later how we can elaborate on that and how we can improve the speed and omit using the getComponent and gameObject.find functions. But for now, let's just use them. Plus, we are using them only once in the start function and not in the update. It would be inappropriate to use such heavy functions since the update gets called every single frame. But now, once we did it in the start, the image component is initialized to reference the appropriate image component, and we can make use of the image component variable inside of the update or wherever we would like to. Now, referencing this component from the script located in our camera, we also have to create an array of sprites to have a compact storage of our monk, villain, and zombie textures. That's why let's declare a built-in array that will be used for holding sprites. To declare a built-in array of type sprites that will be used for holding sprites, we're just going to type in the sprite type, then the square brackets, just like we did in the beginning of this tutorial. And let's call them mySprites. It will be initialized in the start function as well, somewhere in the beginning. MySprites becomes equal to, and now we're going to retrieve whatever contents were stored in our resource folders. That's why we've positioned our texture files in there at the very beginning. We're going to state that resources, which is a class controlling the folder called resources, and resources class provides us several functions. The one of particular interest for us is not load, but load all, because we would like to load not just one single object, but the sprites all together. As you can see, load all requires a string path, that is the path through all the subfolders lying in the resources folder, and it will return us an array of objects. Object itself is one major class from which all other types are deriving. That's why I can say that the game object is an object itself, because object is the biggest class from which all other classes are always deriving, all the types. Even our custom classes of type monk are also objects, because this happens behind the curtain. The load_all function can be overloaded by supplying different arguments. The first one, we have to state in those kind of brackets, which we've encountered in getComponent before, we have to specify which return type we would like the function to have. And we will receive an array of this type by the end of the function as a return. The only thing that we need to do is to supply the string path. The second option is to supply the string path and not specify the type. That's why the return type of the function will be the general object. And then we would have to cast it manually down to the appropriate type, be it the sprite, transform, or whatever. We've done casting before in this tutorial. Make sure to go back and check it out if you did skip some of the video. So without stating the return type of the function and just supplying one argument in terms of path, it will produce an array of objects, but you'll have to cast its type to the required one. And then there is a third type which is not of use for us at the moment. We're going to work with the very first argument, and since we are expecting the return type to be of type sprites, we're going to specify that the return type of the load_all function has to be sprite. Once this is done, all we have to do is now to supply the path that has to be a string. Notice that in our resource folders, we can load all the subfiles belonging to this file by just stating the class icons, like this. Then this array on the right side that we've got as a return will be assigned to be referenced by mySprites. And so by now, mySprites is initialized, and depending on the number of children right here, it could have different number of cells. But because I have 3 subchildren here, mySprites is a built-in array which was initialized to be of size 3. You cannot change size later on, it has to be the same number, but remember that this happens during our start function, the initialization. So as the game starts, only then you'll not be able to change the number of subcomponents in the class icons during the runtime of the game. But once you quit the game, all of those functions are no longer valid, and mySprites becomes uninitialized once again, since this piece of code happens only once the game starts to run. However, built-in arrays are very quick in terms of speed, and although after declaring their size you cannot change it, you can very quickly index the appropriate elements. By stating, for example, mySprites square brackets 1, this means that we're referencing the contents of the second cell. 0 is obviously the first cell of the array, and the second is the third one. In our case, this is equivalent of stating the zombie sub sprite. And we're going to make use of this inside of our update function, where we are going to say that our image component variable that references the component of image on our child of canvas image game object. This component has different variables. The one of our particular interest is the sprite variable, which controls this value right here. And if we pressed the M key, the value of its sprite variable becomes equal to, well, the 0th cell of mySprites. That's because mySprites loaded all sprites from the class icons, and the first element, that is the 0th one, was the monk. As we press the M key on the keyboard, we would like the picture of monk to show up. Otherwise, if the input was the V key, that means that we want to display the villain. If the key code was Z, that is, we want to display a zombie, who is the last in our array of sprites, and it has an index of 2, since it's the third element of the array mySprites. Pay special attention to the comments that I've written just a moment ago, and read through them because you might understand whatever you missed within the last couple of minutes.
After saving our script and seeing this
Sign right here stating that it's rotating, we're gonna go into console and check that we don't have any errors.
we only get warnings. The first one
I get from some other game object that I've imported into my scene, and it's currently out of our scope. It's the monk character, the 3D mesh. And the last 3 warnings are coming from the fact that we did declare our my villain, my zombie, and my monk, and we actually did initialize them to reference to some objects made during the start function, but then we didn't make use of them in our update function or anywhere else. We didn't perform any operations on them. That's why Unity is stating that warning, did you really want to have this? But in our case, we're going to improve on that later on. Currently, we're just interested in seeing that the images will be switching back and forth or not as we press the buttons. Once I press the play button, the start function will kick in. We will initialize mySprites variable that contains 3 sprites. We will create 3 objects, one that will be referenced by the variable myMonk, the second one by the variable myVillain, and the third one will be based on the class zombie and will be referenced by myZombie variable. Finally, the start function states that we have to store a reference inside of the image component variable, the reference to the image component particular to the child of canvas image game object. Then the start function is over, and we will only have the update function working for us from there on. In the update function, we'll be searching for any user's input, on the keyboard, and if there was one, only then we're going to check which button we pressed. Was it M, V, or Z? And if yes, the variable sprite belonging to the image component will absorb the appropriate value from my sprites from one of the cells of my sprite. Let's see. M brings up the monk, V brings up the villain as you can see here, and the Z brings up the zombie. Once I exit the gameplay mode, the update function stops and we are returned back into the editor mode. No start or update will be ran in this mode. We now have the capability of switching the images back and forth by substituting them into the image component sprite variable from the appropriate cell of my sprites. But what about my monk, my villain, and my zombie that have all sorts of different variables tied with them? We would like to display them as well on the screen. That's why, back in the hierarchy of Unity, click on the scene canvas and then create a game object of type text. And as you can see, it also has a rectangular transform similar to the child of canvas image that has anchor, position, scale, and rotation. It has canvas renderer, so it can be seen lying on top of the game view. And as you can see, it's a very vaguely seen text on the bottom left corner. It has a color of gray, and we can change it by clicking here, then dragging the slider to be of a particular color that we desire. We can even set it to be transparent by changing the alpha component. Let's increase the font size to be slightly bigger. The anchor point, let's set it up to be the top left corner. If we resize our game view, if we change the aspect ratio of our screen, the text will not be stretched and will be just repositioned relative to the top left corner of the screen. Now we have to either manually reposition it via those controls or see where our canvas game object is, then drag it upwards along the canvas. I'll press F to focus on it, or you can press Shift F to lock your focus upon the object, and as you drag it upwards, you'll be refocusing on it. Because the anchor is top left corner, once I resize it, the text stays in the top left corner as well. If my corners of the anchors would be positioned on the borders of the text, then as the game view is changed, the element would be stretched. It's the case with any UI element. However, on the text, it just influences the area of input of the text. That is, it does indeed scale and becomes wider as the game view is expanded, and the border becomes narrower, consuming more and more text, which is then not shown. If it would be an image element, it would be scaled down. But we are interested in its pivot to be set to the top left corner. This is the text which will be carrying information and stats of our characters as we switch between them. Don't forget that you want to save your scenes, so press Ctrl S as you work, because Unity sometimes might crash if you've written a badly designed script that has, for example, some kind of loop which does not terminate, etc. Save your scenes regularly so you can return back to it if needed. This is a text component belonging to this game object. Let's rename it child of canv_text. Now our screen canvas, the big rectangle representing our game view, has two children. This one has an index of 0, this one has an index of 1. And so, back in our script that is attached to our camera, we now have a reference to our image component on the game object child of canv image. Now let's prepare a variable to be able to access the component of text, and let's call it text component. We can initialize this variable along after the image component in the start function. And let's do it the long but easier way, revising our stuff once again. Then we can have a look at how we can shorten our code. So we would like our text component to receive the reference or the value from whatever is going to be on the right. We're going to ask our game object to provide us a function called find, because we would like to search for our screen canvas. Make sure to input the correct name, and once we did find it, we can pretend that we are currently inspecting this screen canvas game object. We would like to access its transform component that has a shortcut expressed with this kind of variable transform, and the transform can provide us all sorts of functions and variables, but the one that we need is to get the child. Remember that our child of canvas text game object is the child number 2 of screen canvas. That's why we're going to put an index of 1 here. Then once we are on that game object, we can finally get component of type text. If it would be just an ordinary component such as light, camera, collider, we could simply reference it just like we did with transform here by saying .light or .rigidBody, .collider. But because it's not a common component to have, it's a UI component, we have to explicitly search for a component of type text. And by now we have an opportunity to reference the text component
from this particular child of screen canvas game object.
But as I said before, this is not a very compact way of writing. Notice that we're not doing anything new up to this part. GameObject.find is quite a capacious function, and we would like to avoid using it as much as we can.
That's why inside of the start function, right before we begin to find any game objects,
we can declare a variable that is going to be storing reference to the game object, and let's call it temp game object. Immediately let's initialize it to this line. Actually, let's rename it to screen canvas, just for the convenience.
once we find the gameObject screen canvas, we will get a value of type gameObject on the right side, which can be immediately used to initialize the screen canvas variable of type gameObject on the left. So screen canvas variable right here is indeed referencing the gameObject in our hierarchy screen canvas by now. From now on, we can omit using this part of line, the expensive gameObject.find function, and just plug in the reference to the gameObject that we've already established before. Screen canvas, we can access its transform, get child, and then get component. In fact, we can change the type of the screen canvas to be a transform if we would like to be even more neat. That way, after we found the gameObject screen canvas, we can press dot and either type in get component of type transform, or just like I told you before, since it's a common component, we can just use the shortcut variable transform. That way, we got a transform on the right side, and we can stick it to the variable which accepts transform on the left side. If we use the screen canvas, we can now omit everything up to this part as well, where we access the transform both here and on the line below. And instead, just say screen canvas, by which we're implying the transform of the screen canvas, dot get child, and continue with instructions that differ on different lines. This way, our text component has been established, and now we're referencing the particular text component of this particular gameObject within our hierarchy. We can then alter its text field to display the strings required by us to the screen. They'll be carrying stats of our monk, zombie, or villain. We would like to switch text on that component in exact moment once we get one of the keys down, be it M, V, or Z. And so we're going to state that the text component dot text, because we want to have an impact on the text field that it controls, it becomes equal to, and since the key pressed was M, we would like to display the values from that particular object that we created before, my monk, and it's going to be just an integer value, for example, health. And notice that the health is an integer and the text is the variable which requires string. You can check which type it requires by stating that our text component and picking up text, and as it comes up in line you can see that it's of type string right here. It's both readable and settable, but it requires string. My monk.health is of type integer. Its value can be also read and grabbed, but it's of type integer, so our right side and the left side don't match. That's why we have to take our left side into brackets and then use the universal function which is accessible pretty much from anywhere, which is called toString. That means that we are converting everything previously bound in brackets to string, and it's a function which will return string that can be then used to be applied to the left side. If the key pressed was V, that means we want to display health of my villain object. It's also of type integer and doesn't fit into the type of the text variable. That's why we make use of toString function on it. And we get our right side converted to string, which can be then applied to the left side. Finally, let's display my zombie's health when the Z key is pressed. Remember that we are going to pass those values to the value of text component variable only once we registered a press in the key. So it's only going to occur once in a while, because our child of canvas image has a monk image assigned by default, and the child of canvas text has default text of new text. That's why we see those two things before we start the game. We can actually get rid of new text and have actually nothing here. Let's run the game and see which values we get for the health of monk, the health of zombie, and the villain. As you can see, the villain has a health of 4, which is just displayed as a value because we didn't type in additional strings nearby. The zombie has a health of 3, and the monk has a health of 5. We can make it more clear by what it is by actually typing in string nearby and then concatenating it to our older stuff from before. Here we can say health of villain column, and then I'll put space to give it some area between the value of health and the string. I'll copy this direct string and paste it into the previous paragraph, and it's a health of monk, and this one is the health of zombie. Let's re-enter the gameplay mode, and then after we press M, we get health of MO, which does not fit into the specified borders of the text because we need to increase the width. Let's do so now, and increase the width to something like 200, then reposition it to be here. Pressing M, we get health of monk is 5, health of villain is 4, and health of zombie is 3. Excellent. Now, last thing to do is each one of those characters had a name as we were creating them during the start function. Our monk has Patrick, the villain is YOLO Swaggins, and the zombie is Stinky. Let's now make use of it, and instead of typing in zombie, health of villain, health of monk, let's type in the health of, and then concatenate the string, the value of their name. Notice that I have one string here, health of, to which I concatenate the value of the name, which is string, so it does not have to have this addition of toString. And then I concatenate a string with a column and a space to give some area to the value which I concatenate near it. It's health and it's an integer, so it has to go through this stage of going through toString function. Now each one will have their name as specified with each particular object during their creation. As you can see, health of Patrick is 5, health of Stink is 3, and health of Yolo Swaggins did not fit. So we can change its width to be something like 400. But notice that once again, if you exit the gameplay mode, the width will be readjusted. Set up default values in the inspector outside of the gameplay mode. We did an excellent job here. Having increased the height of the text field input, you might want to have different variables being represented on different lines. And to do this, it's very simple. You just have to supply a string which has a \n, and this states new line. \ character is called an escape character, and the combination of \ and n is called the new line. In this example now, the villain will have its health on another line. When I press M, you can see that health of Patrick is 5, but when I press V, the value of health of Yolo Swaggins is actually brought to the next line. You can change the spacing and everything within the text component as you exit the game, and it's quite handy, so make use of it. As you keep working on your projects, just remember that you shouldn't type many things over and over again. Make sure to spot them out and create shortcuts like this. For example, where we do gameObject.find and access its transform, instead of doing this every single time, we just predefine this resulting component of transform and store it in the screen canvas transform type variable, which is then just plugged in the required instruction, and we keep searching from there, from this variable, saving ourselves quite a lot of writing time and the runtime as well, because we've caged this variable.
Once you've learned how to jump between different objects and describe those transitions between your objects within your script, it's very important to ensure that you will remember how to do it. In that case, here is our hierarchy, and we have a camera object which contains the script. I'll quickly recreate the interface here to illustrate the point. Let's say we have a hierarchy here, and it contains different objects. For example, object A, object B, and C. On C, we have our script, which inherits from MonoBehavior, makes use of start, update, and other functions which MonoBehavior provides. GameObject A in our hierarchy contains a light component, and GameObject B contains a box collider, and also a second component, a material renderer. That's our hierarchy, and when working with our script C, let's say we have a variable of an appropriate type. It will be changing because it's just an example, but we have a variable which accepts some certain type, and we would like to assign a correct type to this variable. Let's say in this case our example variable of some certain type, doesn't matter which one, let's assume it's going to be correct, would like to reference the object to which the script C belongs. That is, we would like to reference via this variable the GameObject C. In this case, we can make use of the shortcut variable, which is called GameObject. Some people are making use of this and then put .gameObject. This just means this script or this component. Sometimes you'll see this .gameObject, but GameObject itself, with this word being omitted, is equal of saying that we are now referencing with this variable our GameObject to which an instance of this script belongs. In this case, of course, your X variable has to be of type GameObject. Similarly, your X variable can reference the transform component that belongs to the same GameObject as this script does. To reference this transform component, your variable of course has to be of type transform, and remember that you declare types starting from the capital letter by convention. So our X variable begins to reference the transform component of the GameObject to which the script C is attached. We can use once again the shortcut variable because this is a quite common link to use, and Unity provided us a very quick way to reference it. You can also access the component renderer that is attached to the same GameObject as this script by first making sure that you can assign the appropriate reference to this variable by stating the type of renderer and then using the shortcut variable renderer. And now suddenly you are referencing with this variable the renderer component which belongs to the same object as the instance of the script C will. Renderer has different variables. For example, once you established the link to renderer, you can make use of its other variable, for example like material. For that you put dot to signify that you want to access its own variables, and then put material, for example. You should immediately see that there is a mismatch, since now our X variable is referencing a material, but its type is renderer. It has to be changed to material in order to be correct. That way, just ensuring that the type of your variable fits its value or reference, you can establish really quickly the shortcut to the component of the same GameObject as your script belongs to. But let's say we want to access a component which is not expressed via the shortcut. That is, we can't use something like transform, rigid body, or maybe collider, or light, for example, or renderer, shortcut variable. In this case, we have to explicitly state that we want to get the particular component. Let's start with a simple example. Let's say that the type of our variable is transform, and so we'll be grabbing a reference to the transform component.
it becomes equal to, we could have used the shortcut transform and it would be correct, but instead an equivalent statement, the one that takes more computing time, will be making use of the getComponent function, specifying which type you're searching for in those brackets and putting your type in here. That is, we will be putting transform type here, and then the arguments you don't need to supply when working with C#. This statement omits a couple of things. It implies them. First of all, an old and well-established way to say it would be to put this dot get component of type transform. By saying this, we're saying the instance of script C, and on the same game object as this instance belongs to, we have to search for a component T. Because we didn't say this dot, the editor will immediately imply it. So by saying just on its own get component of type T, we're implying that we're searching for the component on the same game object as this instance of script C will belong to. So once your type of variable and abbreviation T is used, for example, you can get component of type T from the same game object as this script lies on. This shorthand notation, if expanded, would look the following way. Some random type T, we don't know which, it's just an abbreviation, example variable, becomes equal to, first we begin by stating this, that is, we start searching from this particular instance of script, putting dot, we go into gameObject, that particular gameObject which holds the instance of script C, and then from the gameObject we make use of the getComponent function. Of course, we supply our type, that can be transform, renderer, any class that you're searching for, T just for an abbreviation, and that way we can get any component that lies on the same gameObject as this script does. If we omit this line, we will get the first statement, and it means just get component locally from our native game object. However, if you'd like to retrieve a component from some other game object to which this script does not belong to, you would then have to make use of the function called find, which derives from the gameObject class. For example, we would like to access the light component on the gameObject A, but our script sits on the gameObject C. Because of that, we cannot state that getComponent of type light, since this means refer to the same game object as we are located at and retrieve the light component. There is no light component on the object C. We first have to get to object A and then use getComponent of type light. Because of that, since we're going to be establishing a reference to the light component, we will put a type of our variable to be light. We will make use of the find function of gameObject class. If you recall, this function takes a string argument, that is the name of the game object which we're searching in, inside of the hierarchy of the scene. Here, its name is just A. Remember that it's a string, so enclose it in the double quotation marks. This will mean that we are already on the object A. And from there on we can make use of the getComponent function, so we'll put dot, and then type in getComponent of type light, and as you specify the type, of course it has to start with a capital letter, since Unity classes are always named with this convention. As for the arguments of this function, it doesn't take any, you may leave them empty. Now, further on inside of our script C, if you ever say x variable, you imply that you mean the light component, specifically on the game object A. Novice programmers might make a mistake where, for example, they were searching for light component, they did gameObject.find, they found the appropriate object on which the light component lies, and then they put some kind of shortcut variables such as .transform, .collider, and then for some reason after that they put .getComponentLight. Anything here, for example, if you put .transform, yes, you jumped to the transform of this game object A, and you can also put .collider, and now you'll be referencing the collider component if there is one on the game object. But then if you put .getComponent.light, this code becomes irrelevant. Since why would you jump back and forth first to the transform component of the game object, then to the collider, and then you'd start to search for the light. You can search for the light immediately after you've reached your game object. So this line of code or anything like that is not necessary. Of course, getComponent is a more complex way of retrieving the light component instead of just using .light variable. But .component always works, whereas sometimes there are no shortcut variables. Such as, for example, when we were using the UI element, the class image. There was no shortcut variable .image, which we could utilize.
We had to explicitly state that we're getting the component of type image.
This is also the case if you would want to reference a script on the object. For instance, let's imagine that the object A contains light component, but it's not in our interest, but it also contains a script B. Script B, in turn, specifies a public variable of type int. We'll call it myInt. And it's initialized to 5 by default. Let's say from script C, which belongs to object C, we would like to access my integer variable, which belongs to the instance of script B on this particular object A. For that, once we established the shortcut, for example gameObject.find, we found our gameObject A, we received the component, but this time we shouldn't be searching for the light component, but for the type, which is our script name. We're searching for the component of type script B. And once we got it, we also have to make sure that the type of the variable which will be referencing it is also gonna be correct. In this case, it has to be of type script B, so that it can hold the reference to this retrieved script B. And now we can say that this particular instance of script, we would like to access its public variable, myInt, and then it becomes greater by 1, so plus plus semicolon. I beg you, please make sure that you don't use gameObject.find or getComponent inside of the functions which are happening every single frame or often enough, such as update or on GUI. It's best to establish links like this once, such as in the start function, and then utilize this variable further on inside of your update. Inside of the update, you already know that this variable is pointing directly to the required cell on the RAM, where this particular script B is located. You don't have to go through the expensive process of finding it because you already have a reference to it. You can use it inside of the update function or anywhere else and quickly access its variables in order to change them. So keep this in mind. Remember that you should not jump from component to component in order to get the one that you are looking for. Make sure that if there is an opportunity such as .light, .rigidBody, .transform, that is the shortcut variable to be used, make sure to use it instead of using this getComponent function. Keep in mind that sometimes variables might be read-only and you might get mistakes, and ensure that when you're establishing a link, that the type of the variable which will be holding the produced result on the right fits to the type that you will receive on the right side as the result.
We looked at different ways of creating our own types,
at how we can describe classes and work with the objects that are based on them. But there is one more thing that I mentioned once in my tutorial, but didn't explain so far. There is one more data type which you can make and should make extensive use of. They are enums. To declare an enum outside of any class but within our custom classes script, we can say enum, type in the name of the enum, myEnum, and then within the curly brackets, or we can specify values. Let's say, for example, Monday, Tuesday, Wednesday, and Thursday. After you finish declaring your type, after the curly brackets, put the semicolon. This is a privilege of enum. Usually you don't put semicolons after curly brackets, but here you do. What's cool about enums is that each value, Monday, Tuesday, Wednesday, or Thursday, has an index behind it. That is, the first one has an index of 0, second one an index of 1, then 2 and 3 at the end. Quite similar to how we index the cells of the array. But what's very easy about enums is that you don't have to specify whether you want to access the first element, the second one, or third. You just have to type in the name of the value. It's very handy to work with enums when you have to manipulate different variables, such as, for example, helmet, shoulders, armor piece, axe, or sword. You don't have to remember which index they are and reference them by index. You just type in their name that was predefined before within the enum. In the zombie class, let's make another variable, which is going to be private. So I'm going to omit the public keyword. We'll declare the type of the variable, myEnum, and we'll call it 4 days. I'll actually initialize it straight away in here, and I'll type in that it receives the value that was described in the type myEnum, and within our constructor, we can initialize our 4 days to be always equal by default to the value Tuesday, for example, and stating Tuesday by default does not mean anything to the editor. Although indeed 4 days is of type enum, it would actually make sense to be able to type in like Tuesday or Wednesday because they belong to this type of myEnum. But sadly we have to do it explicitly. So our 4 days, which is of type myEnum, will receive a value of Tuesday, which was described in myEnum type. Semicolon to end the line, of course. You can also do different conditional checks. For example, in the constructor, we can always perform a check if our variable declared on top of our class 4 days has the value of, say, Thursday. And if yes, we'll perform a block of code. If you jump to some other script, you can still make use of myEnum in there, because myEnum was declared outside of any classes. For example, it's outside of the zombie class, villain, or monk. All of those classes, therefore, can make use of this enum and use the values described in there. If we would put myEnum inside of some class, then of course you would be only able to use this enum within the class. Just declare your enum outside of any class and you can use it within any class, even if it's declared in some other script. For instance, my scene tweaks. In the update we can make use of it. As you can see, we can say myEnum.anyValues, etc. and manipulate it from there on. Remember that enum is a set of values. They are not variables. Those values can be assigned to some variables on the left side, but you cannot reference them and just manipulate them on their own. They're not variables, they're just values, behind which there are integers. And instead of saying, for example, item 1, item 2, item 3, we just say the value of Monday, Tuesday, Wednesday, Thursday, etc. Continuing to explore beautiful interface of Unity, I would like to show you how you can create an object which is affected by gravity, and once it touches the ground, it catches on fire. Let's quickly create a mesh inside of our 3ds Max, a 3D mesh, which is going to be like a lump of cloth, or maybe a cloth chunk. I'll jump into 3ds Max really quickly, and that way we'll show you how I can implement my ideas into life very quickly. Creating my geosphere, I'll jump into Modify panel, we'll press F4 to see the wireframe, and reduce the segments down to 1. I'll convert my object to an editable poly, we'll grab a couple of vertices, and we'll drag them to the side, distorting the object that way. Maybe with those vertices selected, I'll press R to scale them from the center, and we'll scale them downwards. This way we have some kind of irregular lump. And now one last thing is to apply a material to see how it will fit on it, and then unwrap the object. For the diffuse, I'll pick my atlas, and we've been talking about atlases in the beginning of this lesson, so make sure to check it out. I got my atlas right here. Once again, atlases are an excellent way of combining your textures into just one single big texture, that way increasing the productivity, because it's much more wise to have less textures than small ones, but many of them. Let's uncheck map seams and make sure that we only have peel seams. Press 1, go into the vertex mode, click point-to-point seams, and lay down seams so that we can then pelt the object really quickly and establish patches correctly on the UV table. When this is done, I'll press 3, select one of the polygons, expand towards the seams, or just press Ctrl A to select all of the polygons. And then click Pelt, start the pelt, go into Settings for Relax, pick by Face Angles, and start relaxing. Close this, commit, and then scale down the object to fit into the UV table. If you want to see the background to be the texture, you can either pick the texture and then go to bitmap and select the atlas to be shown as a background, or I have it already here because I've been using it before. This object has to be sampling somewhere from the area where there is cloth. It's going to be a small detail, not very important, quite small compared to the average world. I'll press F4 to hide the wireframe and F2 to hide the selection, the reddish selection on my polygons to see the texture better, and actually deselect peel seams because we're done with peeling. This object is going to be quite small and it shouldn't be really textured with a great detail. However, if you have this fixed amount of texture and you would still want your object to be more detailed than that, you can do so following the idea expressed in the beginning of this tutorial by grabbing this half of the polygons, flipping them horizontally and making sure that the edge which they join at, those two edges are aligned perfectly. You can either do it by hand or press 1 to go into the vertex mode, click Ctrl S or click here to snap, and then with Move tool just snap those vertices so that those two edges are joined properly. Check out the beginning of this tutorial to remember how to do that. We've been working on the wooden log back in that example, go check it out. But now we've increased the detailization of the texture on the object by a factor of 2, which is quite nice. We can now right click and convert the object to editable poly, or exit any editing regimes, press 3 or click here in my case, and collapse all stacks. But it's much quicker to do it, just convert to editable poly. I'll go into Utilities panel because I was scaling my object, and will reset X form, making sure that I name it properly, like a lump of cloth, and having my reset X form applied to the object, I'll go back to the Modify panel and either collapse all the stacks or once again convert to editable poly. Now the UV coordinates for our vertices were set up via the unwrap UVW modifier. We've reset the X form, we've renamed the object properly, and it's very important to check against the units in the world space. Unit setup, they should be metric, just like as always when working with Unity. And we can go into top view by pressing T, press Z to center on the object, and going into tools, measure distance. I'll click here and here, and you can see the distance is 30 centimeters. It's going to be perfect for our object. But if it wouldn't be, you would have to rescale your object by pressing R, going into the perspective mode, so press P, and then scale from the center. And if you are in different scaling mode, so if you press R too many times or click and hold here, you have to be in the first one. But if you are in different one, just scroll back to the normal one and scale from the center appropriately. In my case, I'll not be scaling so that I don't have to do my reset X form once again. Having it named properly, I'll just export it as an FBX format. Before you actually export it, I forgot to mention that it's very important to ensure that your pivot point is centered within the object and that the object itself is centered within the world. Then you can export it. I'll make sure that I don't export any animation because I don't need it, and I will not embed media because I'm not bothered about materials. They will be reapplied in Unity. Y-axis is up because that's how Unity coordinate system works. Up is not Z like in 3ds Max but Y, and the scene units are converted to centimeters. Make sure it's not automatic. I'll click OK, and now we have an object exported without any errors. I'll close 3ds Max, will not save my progress. Back in my project, since we've already exported it into correct folder, if we go into items 1, we will have our lump of cloth object residing there. Let's drag it into our scene, and because it already has UV coordinates established, you can see that it's nicely lying right here. The problem is, even if we didn't embed the media into our FBX exported object, it still brought its materials, just like discussed in the beginning of this lesson. So I'll get rid of the materials folder. Here I'm just gonna reapply a material that I've created before, which is just a bump diffuse material, which doesn't have normal map yet because I didn't bother to make it, but it already has the atlas applied. And this material is applied to many different objects. I'll explain why later on, but once again, applying one material to different objects might save you a lot of performance. Now we have our object here, and even though we have it as a prefab right there, this prefab has some information about the previously established material folder. That's why I'll create a new prefab, and we'll call it cloth lump. This one I'll put a double underscore to show that it's obsolete, but it's still necessary. If we get rid of this prefab, even after we dragged our lump of cloth on the cloth lump, if we get rid of this prefab, cloth lump will stop functioning. Let's get rid of this one from the scene, and I'll redrag it into our world. Because we want to make sure that it drops on the ground and is influenced by gravity, our game object cloth lump, which has a mesh renderer, a mesh filter and transform components, and a quick link to material, we can add a new component to it, which lies in physics, and we will add it a rigid body component. Rigid body allows you to interact very quickly with the Unity's physics. It has very simple parameters as for setup. It also requires you to have some sort of collider on the object if you want your object to be colliding with some other entities from the scene, not just being affected by gravity. So we'll go to physics and we'll apply a sphere collider. As strange as it might sound, sphere collider is the quickest of all the colliders in here. Because sphere collider, you just have to check for the radius based on the position of the object. And there you go, you got your whole sphere for you. Capsule collider compares two radiuses and then compares distance between them. And box collider is the most complex of those three. The one which is even more complex is mesh collider. And I have mesh collider applied to my terrain object right here. By the way, my terrain is a custom terrain, and it's not the Unity's native terrain. I made it myself, and it allows you to basically do all the things that normal Unity's terrain can do. But this one has an opportunity for you to add something like parallax occlusion mapping or height map offset and use the tessellation shader, unlike Unity's terrain, which cannot do that. So I made my own terrain, and what's cool about that is you are not bound to Unity's terrain, which ends after some spot, and you can paint that way different objects. I'll focus on this terrain slightly later in this tutorial, just to show you the demo of what we're going to be making later on. In this case, we're focused about this lump of cloth, but my terrain has a collider attached to it. If I click on my terrain, you can see that I have mesh collider, and I just dragged my terrain mesh onto there. Mesh collider allows you to have arbitrary number of vertices, and it's mostly used if you have something complex, such as for example terrain, or if your object which you want to have the collider, if this object is concave, that is bent inwards, then you would be using an expensive mesh collider. Actually, I'll turn off the lights and we'll go into terrain and we'll drag my terrain object into the scene. And you can see that it's quite complex mesh in terms of points, but I tried to optimize it as much as I could. I modeled it in 3ds Max. And because it's a custom object, I had to write a custom script to paint it with different textures, or parts of the textures, etc. If I go into preferences, go into colors, and set my alpha to be something higher for the selected object, you can see the wireframe of the object. If you compare it to Unity's terrain, yes, it does not optimize itself or tessellate as you zoom in closer, but it's very optimized in terms of points. And if you think about it, you can use this in RPG games with ease. And you can have different terrains stacked near each other. Of course, you have to be more precise about their joining point, but because my terrain intended to be just one single piece without any kind of neighbor terrains, I didn't care about the border lines. But yes, you can copy them and have different terrains and then load them part by part with the help of my script. So if you are in this part of the world, you only load this terrain and any kind of nearby terrains nearby to this one. But if you, let's say, go into the second terrain, then you load more terrains, and as you proceed further, you are hiding the objects which you left. This procedural terrain is something that Unity doesn't provide to you. So gradual loading and unloading of terrain pieces is not possible with Unity's terrain, but it's possible with mine. And later on, if you keep watching those tutorials, you'll figure out how you can make your own terrain and how to make it to be painted.
we'll have a look at this example once again, slightly closer to the end of this lesson. And currently, let's focus on our rigid body. After applying my mesh collider to the terrain object, I opened up my terrain prefab and dragged the terrain mesh onto the mesh required for the mesh collider. That is, my terrain has its collider, which is referencing its own mesh in order to be used for the collider. So we're checking against its own points when calculating for collisions. But because of that, since we have only one object who's using the mesh collider in our case, we have a very precise calculation, and as our object will fall down to the ground, it will follow the ground pretty neatly. Because I'm using tessellation shader on my ground, just for demonstration purposes, to show off what my terrain can do, the object after colliding might actually go through some of the mesh vertices. That's because it's comparing with the mesh collider of the terrain, which is using a non-tessellated version of the terrain. That is the one which has less vertices than this tessellated one has. We will talk about tessellation slightly later as well. I'm just mentioning it currently so that you don't wonder what it is. But if it doesn't make sense, just keep your ears closed and follow me without worrying. Now we have mesh collider applied to my terrain, and we have a sphere collider applied to this object. As well as that, our cloth lamp has a rigid body, and in fact I don't require an animator component, so we'll right click on it and we'll remove component. We need mesh renderer and mesh filter for the purposes explained before. Rigid body defines how our object interacts with the physics of Unity. It has a mass of let's say 10 kilos, and the drag is basically how quickly will it stop after the force has been applied to it. In this case, the drag has to be 2. Angular drag is how quickly it stops spinning after the force has been applied to it. Use gravity has to be turned on so that it falls down under the gravity. And if you want it to be stationary and not rotating, you can freeze rotation along particular axes, the local ones. Remember that you switch between local and global by clicking on this button. Local is how your pivot point was positioned within the object. Global is how your object is positioned within the world. And the same story happens for position. Collision detection can be discrete, that is periodical. Continuous, which is more expensive and you constantly check for the object, is more precise. And continuous dynamic is used mostly for moving objects. But because our object is not very important and is not something like a character, we cannot afford really to use the continuous dynamic because it will be consuming resources for nothing. This object is not very important to our game, so it will be discrete. Interpolate means that computer tries to figure out the position in space of this game object based either on the previous frame or on the next one. Is kinematic means that it will not be affected by any colliders belonging to other objects and is going to be controlled via the script. However, it will still have an opportunity to push away colliders of different objects that are not kinematic. So for example, if I have a sphere collider and a rigid body on this object, that means that this object will be able to fall down under the gravity and have different forces to be calculated upon it. It will be able to hit and then not go through the support bulk, but it will not be affecting bulk, and bulk will not be falling down if it crashes into it. That's because although bulk has a box collider, it has no rigid body. Now, having rigid body and sphere collider applied to our game object, we can press play and see how it falls down onto the ground. In case if it does go through the ground, that means that the precision of collision detection was not precise enough, as strange as it might sound. It has to be either continuous or continuous dynamic. There you go. The object rolls as it touches the mesh collider of the terrain. The object rolls in the scene. If we put it on pause and drag the object upwards, it will also fall down, and will fall down from any kind of crate that it hits. If we reduce its mass down to something like 1, then it will be falling with smaller speed and accelerating slower. And of course, if your sphere collider has a bigger radius, something like this, then the object will actually hover over the ground, because it's the collider against which we're calculating, not the object's mesh, of course. Remember that any settings that you do within the gameplay, such as for example the radius and the mass, will be reset as soon as you exit the play mode. If you change something, make sure to do it not while you're playing the game. Once this is done, we're gonna think about how we can light our object as it touches the ground. In order to create an animatable fire, we have to somehow make a sequence of images of our fire, the flame, progressing through time, and then store it on one texture. Such textures are also some form of sprites, and there is a very good program I found on internet, a royalty-free one, which can be used for generating explosions. It is called Explosion Generator. You can search on internet, and if you double click it, you have to first read the file called readme, but if you press enter, you'll generate an explosion, and if you press enter again, you can generate another one until you find the one that you like. Once you're ready, you can press escape. This will exit the program, and everything was stored in the bitmaps folder. We can then open the Photoshop,
create a new file with those dimensions 512 by 512 and drag our image into the Photoshop. In this case, I'm only interested about a couple of rows, and I'm creating an atlas that is going to store different particles. The first couple of rows are going to be dedicated for the particles of fire, the second one probably some kind of magic particles, and then the third one will be a smoke. It progresses left to right, top to bottom. Right clicking and rasterizing my layer, I'll select this part with marquee tool, press V and then drag it to the side. I will do this once again, stylizing my flame particles this way. I'll copy this part, press Ctrl V to paste it, and we'll position it on top of some flames just to have an effect of it growing and then fading out. Once this is done, I'll get rid of my background layer and we'll merge the remaining ones into a single layer. After that, I'll go into Select, Color Range, we'll pick the black color, increase the fuzziness to 200, and we'll press Delete. Here is another sprite sheet that I got from the internet, and as you can see, I'm preserving the space between their frames. Vertically and horizontally, they are all spaced out at an equal distance. You can save the resulting atlas as a PNG texture format and call it something sensible, such as particle fire smoke atlas. I'll quickly throw it into the correct folder, which is gonna be resources. As follows, if we go back into Unity and check our resources, there we go, we have our particle fire smoke as a texture. Make sure that alpha is transparency ticked on so that you have a transparent texture. Maximum size, make it 512, the native size of our texture. And I've also went ahead and created a particle material, the shader of which I've picked to be particles additive. You can pick whichever one you want, and it works pretty much the same way as layers in Photoshop. Just how it's going to be interacting with everything that's located behind the particle. Is it going to be visible, darkened, or is the particle going to be glowing, etc. Now when we have a material and a texture applied to its shader, we can click on our object, which is cloth lump, the one that has rigid body and collider components already attached. Then go into Component, Effects, Particle System. There are plenty of tutorials on YouTube on how to use particle system component. It has different options, and as you can see, it's already been animated as soon as we added it into the scene. The emitter is pretty big, and you can change the playback speed of how quickly the particles are emitted and see how long they have been emitting for and go back in time if needed. You can pause or stop, obviously, the particles simulation, and in our case the object is pretty small. We're going to click on shape and then reduce the radius down to something like 0.1 and reduce the angle to about just 4 degrees maybe. Because our system is loopable, duration does not matter for us. Increasing duration will increase the loop, after which the emission of particles will be repeated. Pre-warm means that as we start our particle system, particles will behave as if there was at least one loop of emission before that. For instance, if we click stop and then simulate, they'll appear as if they've been emitted for quite a lot of time. Whereas if we untick this and start to simulate, they'll begin from the zero. Their lifetime should be pretty small, that is, they die after just half of a second, and the start speed should be higher as well. Go into emission and increase the rate at which they are emitted, so that we have more particles at once. Let's click on size over lifetime, make sure it's checked, then click on the curve and drag the curve to the desired state. We can also right click and add the key so that it grows up to the center, up to the middle, and then fades out to the minimum size as each particle approaches its death. I'll increase the default size of each particle, but we'll keep the shape of cone of the appropriate size. Currently we have the particle system attached to the cloth lump gameObject. If we select the cloth lump, if we go into gameObject and create an empty child, we can prepare this one to be holding the particle system instead. Now all we have to do is right click, copy component, go into particle holder, right click on transform and paste component as new. Let's then get rid of the old component from the old gameObject. And then we can click on our gameObject particle holder, then drag it downwards so that the ball is engulfed in flames itself. Currently it's just white balls, which will become flames as soon as we attach texture to it. If we scroll down and click on the render tab, it's possible to drag our particle material instead of this one. Since we're displaying the whole texture on each particle at once, we would like to go into texture sheet animation, make sure it's enabled, and supply the number of tiles that each texture has. Here we had a texture with 8 by 8 tiles. In Unity, that's supplied to be so. But make sure that we don't animate the whole sheet, but do animate a single row. Not a random one, row 1 or row 2, the one that we would like to. And if you click on the graph, you can see on how quickly you transition between frames as the particle approaches its end of lifetime. Of course, if during the lifetime of the particle you would like to loop your cycle more times than once, you can increase number of cycles in here. For example, 4 or more. I'm happy with just 1. As well as that, when we move our object, you can see that particles move with it and are not being emitted relative to the world. Because of that, simulation space should be not local, but world. As we change the position of our game object, flames stay behind, as if they are simulated, just like they should be. We can also click on the particle material that is used within our particles, expand it, and change the softness of particle as we desire. Of course, we could have picked a different shader for our particle, for example, particle multiply. Just like with layers in Photoshop, you get a different effect. This is some kind of dark magic fire. And this one, vertex lid, is from some old RPG from 90s. When working with particles, we can click on size over lifetime and adjust them as you wish. Finally, there are different ways of rendering your particle. You can have them face the camera all the time with billboard, or have them always pointed upwards, or be always vertical with horizontal or vertical billboard settings. Particles can receive shadows and can cast shadows as well. In fact, each particle is just a single quad with 4 vertices that is being emitted from a specific point in space. They are acting pretty much like meshes, with one exception. Their vertices are being animated by the particle shader. That's how you would recreate the particle system in CG, for instance, if you would be writing your own particle shader. In my case, when working with the object cloth lamp, it would make more sense to work with a separate material that is created specifically to function with burning objects. For example, I can create a material which will then have its own texture atlas designed specifically for objects which are burning or are stationary but burnable. Once we have everything, it's good to revise the hierarchy that we have. We got our cloth lamp, base game object, which contains a normal material and a sphere collider. And then we have a game object particle holder carrying a particle system component. Particle system component is using a specific row within the particle atlas supplied to it. This particle atlas is used by the particle material with particles additive soft shader algorithm. We can now create a script specific for this object, the cloth lamp, so that it catches on fire once it hits the ground. Keeping the neat hierarchy, which is very important when working on the project, we'll go back into tutorial 8 scripts and create a new C# script, which we'll call burning cloth. Open it up, and we have our common setup. We're not going to be actually making use too much of the update function. That's why we can get rid of it. But the one that we'll be using is provided by MonoBehavior class. It is of type void and is called onCollisionEnter. Once we go into Unity's documentation, you can see that we are inspecting the class collider, which provides us several functions. The ones of particular interest currently to us are onCollisionEnter and then exit. Once you click on it, you even get a couple of examples in different languages. As stated here, if you are not using the information with the collided object, you can leave out this argument section as empty and don't pass any arguments of type collision. In our case, we will require it because we have to check if we are touching the ground or some other collider. First of all, cloth lamp has to receive our script, burning cloth, as a component. If you get this kind of error, it says burning cloth does not exist and therefore cannot be added. If we inspect closely the name of the script, it's burning, then capital letter C and small letter L. Burning cloth. Here it's burning big C and then big L, which creates a mismatch, and since the script derives from MonoBehavior, it has to have identical name in the inspector as well. Now once it's finished calculating, we can drag the script onto the object and it's going to be fine. In it, once we have our onCollisionEnter function, we can actually specify in the beginning of MonoBehavior a shortcut variable, which is going to be of type gameObject, and call it child gameObject. Inside of the start function, we can immediately initialize this gameObject by following previous examples, where we can state the transform of the same gameObject where this instance of the script is attached. From the transform, we can make use of the function called getChild, and since we know that the gameObject which contains the particle component is the first child, we will supply an index of 0. This means that we're going to be looking at this particular gameObject, not at any of its components, but just at this particular gameObject. If it provides you this error, where it cannot implicitly convert type transform to gameObject, to fix this, we have to make sure that we're not inspecting transform of the child gameObject, but are looking at the gameObject specifically. Now our right side returns gameObject type and can be assigned to the left side, which is designed to hold references to gameObjects. Now the only thing we get is a warning, because we never made use of our initialized variable, but we will soon. That way, with our script, which is located at cloth lamp, we are being able to reference this particular gameObject particle holder. From there, we'll be working with its component of particle emitter, etc. As well as that, I'll click on the ground, which has a mesh collider assigned to it, and then tag it with a terrain tag, because it has a collider. When our gameObject with our script attached to it and having a sphere collider hits the ground, we will call this function. In there we have to supply an argument of type collision, and I'll call it call, for example. Then check if our argument dot, and I need to find something that will allow me to get into the game object, like this. Now referencing the game object of the entity which hit the collider of our cloth ball, our local collider. And from there I can pick the variable called tag. If it's exactly equal to the string terrain, then proceed with the following code. Otherwise just fall out and don't do anything. It was some other collider, not terrain. But if it was terrain, we can make use of our child game object, press dot, click on particle system. We would like to alter one of those variables. If we're not sure about which one we would like to change, let's copy this name, open up Unity's documentation, and in search, drop in particle system. I'll click on this one, and as you can see, it has all the variables, which are obviously related to the real world variables visible in the particle system component. Read through which one you would like to change. In my case, I would like to change enable emission on and off. It's of type boolean, that is, it can be either true or false. If it's true, particle system will emit particles, otherwise not. That is, on collision enter, if the tag of the game object with which we collided, if it was terrain, we will enable emission on our child game object's particle system component. That's as simple as that. And now with the second function, void on collision exit, previously described by Unity's documentation in the collider class. On collision exit, right there. Once again, we'll check if the tag of the game object's collider with which we stopped touching is exactly equal to terrain. If yes, then the particle system of our child game object will set its variable enable emission to false. Press save, go into Unity, and check for any errors. It's saying that the function on collision enter is already defined, and indeed it should be exit. Save your script. Once it's done compiling, the error will go away. Now just make sure that the script is attached to the appropriate game object, which has a sphere collider, so that on collision enter and on collision exit functions will work. We have our script here, and our particle holder is indeed the first child of cloth lump, so its initialization will be done properly without any errors. The cloth lump itself contains a rigid body, which will ensure that it falls down under the gravity. On the other hand, collider will prevent it to go through the terrain. As you can see, the object is burning, but it's rotating so quickly that the fire particles don't know which side to emit. They are emitted in all directions, since the emission cylinder rotates vigorously with the object. We can temporarily fix this by freezing the rotation on the object so that the emission cylinder stays unchanged and always points upwards. In this case, we need to increase the playback speed to 1 to see the real-time speed of the particles, and if they're going too quick, we will decrease their start speed and will increase their lifetime. I'll also reduce the number of particles in the emission rate. Observe the following thing. If we rotate particle holder, which rotates obviously as the cloth lump rotates, then the fire raises at an angle to the ground, which is not what we really want. An easier fix to this would be to check that the cloth lump's child is always looking upwards. That is, in the function void on collision stay, without any kind of arguments. If we're touching any of the colliders, transform's rotation becomes equal to the class quaternion, which is the class for rotations. You can read about it in the Unity's documentation. .Euler, and set the world rotation to be equal to 0f, 0f, and 0 float again for all three components. Once you hit play, as soon as the collider of our game object touches any other collider, we will ensure that the particle holder is rotated appropriately to the described rotation right here. Now it's pointing horizontally. I can illustrate the case like this, but we can have it rotated by -90 degrees along the x-axis. Now it's always pointing upwards, and we can even get rid from our particle holder component, because we're tracking its rotation, tracking the values inside its transform from the script of its parent. If the parent rotates, it still pays attention to the rotation relative to the world space of the transform of its child. So it's all good. Finally, our fire has to emit some light. That's why I'll pick my cloth lump and we'll add a component rendering a light. Light's color can be something like yellowish. Its range will be reduced down to something like 2. I will increase the intensity to illustrate the point. And now it's just a matter of turning this component off and on as we touch the appropriate collider. Therefore, as we begin to touch the appropriate collider, we can state that the light component of the same game object as this script belongs to .enabled, it becomes equal to true. Otherwise, the light component of the same game object as this script belongs to becomes equal to false. As soon as the game object stops touching the ground,
the light stops glowing and we don't get any fire emitted. I can actually turn off this light for the duration of our game to see the example in a better view. As you can see, as soon as we start to touch the ground, the light begins to burn. When we stop touching it, light turns off and the fire particles stop emitting. Let's drop it somewhere on the roof. First of all, we'll get no light until we touch the ground. However, there is one thing. As soon as you tell the light component of your game object to cast shadows, the game object's mesh prevents the light from escaping its surface. That's why the game object itself has to have some kind of layer attached to it. We can add a layer and call it burning. Pick our cloth lamp and set its layer to burning. Don't change children because there is no point in affecting particle holder anyway. And then the light component of our cloth lamp has to light everything except for burning. That's why now it doesn't get affected by the mesh of burning. As soon as the collider leaves touching the ground, we get no light. Once again, if we touch the ground, we get shadows and the light begins to shine, as well as our component on particle holder enables its emission tab. If we wouldn't want our game object cloth lamp to be of layer burning all the time, we can change it on the fly. As we start to touch the terrain, we can say that the game object which the script is located at, its layer becomes equal to layer number 10. Otherwise, it's going to be layer number 0. So on collision exit, the layer of our game object where the script is located at becomes equal to 0, the default one. It might make sense to make the layer be default at the beginning by default. So once the collider starts to touch the ground, cloth lamp receives the layer of burning, allowing the light to shine through it. But as soon as the collider stops touching the ground, light component gets turned off, the child object turns off the variable emission on its particle system component, and the cloth lamp receives its default layer. We can improve on simply turning on or off our light and have it always enabled, but maybe change its color to a variable that was predefined before at the beginning of our lesson so that we don't create it every single time. Let's call it my color, initialize it during the start, so create an object of type color. Equalize our light's color variable to carry a reference to my color object with one F everywhere, meaning that the light is white, that is be white by default. On collision enter, the R component of my color will become equal to the G component of my color variable, which will get the value of 0. So all of them will have a value of 0, except for my color's blue component, which will remain as it is. And now the light.color variable will receive a value of my color. We will repeat the procedure here, but here we will invert it, restoring my color R component and the G component to be equal to 1, and then copying the value from my color to the variable color of light component. The component which belongs to the same game object as our script does. This is very important, that's why I stressed it so many times. Because I want to illustrate the point that the light will now be just changing its color, I'll also have to make sure that the cloth lamp has always a layer of burning, otherwise the light will not be showing through it. And I'll get rid of the corresponding line from my script, where I changed its layer at runtime. Now it will be always of layer burning, and we'll see the light shining through it all the time. Once it touches the ground, it becomes blue. This change occurs only during the specific moment when we begin to touch the collider of the terrain, and when we stop touching. Just during those 2 moments occurs the switch, not during on-collision stay. What happens during on-collision stay is we ensure that the child component is always looking up in the world's direction, so that the flame raises upwards and not to the side. Having learned so much about classes and their instances, about variables, functions, physics of Unity, how to access and modify different parameters of components on different game objects within your scene, we still haven't finished one more additional topic, which is very important. It is the movement of your character. Before we finish our lesson for today, this is something I would like to explain to you, and this is not difficult at all compared to what we've been through so far. In my assets folder in the projects panel, I've got my monk folder set up, in which I've imported different FBX files with a plain monk, and then following the example of tutorial number 7, I've exported a couple of FBX files with animations from which we're only going to be using the animations. This prefab of monk can be dragged in the scene, and we can then shape out the final character out of it, which will then be animated as we start to move it around the scene. Because I'm doing a first-person view game, I will position my camera in front of the face of the monk, inside of its hood.
you can see that the monk is not properly textured yet, and we will have a look at this in a second. There are a couple of things I would like to talk about that belong to the texture subject, such as dilating pixels and making sure that the seams on the character are not being shown. After I position my camera on the place of the character's eyes, we can see that the face is obscuring partially the camera with its triangles. This is especially visible in the game view, and as we're going to be rotating our camera later on with the mouse, up and down, left and right, we don't want to have the face on our way. That is why, from the monk which was dropped into the scene, I'm going to locate the face, that is this object. I can double check it by disabling and enabling the gameObject, and indeed it's the face. I will apply it a layer of character head, the one that I made, my custom one. If you don't have it, obviously add a layer, then pick it from this list in here. Now our head has the layer of character head, and the camera makes use of the culling masks mixed, where it renders everything except for the character's head layer. Now we can rotate as much as we want within our hood of the monk, and we won't see the face. In fact, if I bring the camera forward and turn it around, you'll see that it renders everything except for the monk's head, which is pretty scary. But because we're not gonna see the monk's face during most of the gameplay until it maybe is reflected. Because of that, it's not very important, and we just call it. But it's still there for other cameras of different players. For example, if you're playing with via internet with your players online, you still want to render the face to other cameras. It's just this one who makes use of the culling mask. Another very important subject that I would like to consider is that notice that in my monk folder I have my materials folder as well, and all the parts of the monk, the hands, the face, the dress and the pouches that he's carrying on his belt are all gonna have the monk diffuse material. As you can see, as I'm applying it, they all grab different parts of the texture because of the way I unwrapped the character. You can see on how you can do this and how you can unwrap your character to be able to sample from the same texture via watching tutorial number 4 and 5 as well. If I unclick lights, just so that we see our character without any shadows applied to him, notice how I don't have any seams whatsoever on the hands or the face. Although the face was unwrapped symmetrically, there are no ugly seams. Yes, there is something to improve on in terms of symmetry, but there is no ugly seam anywhere, and you don't see the patches, the UV patches being joined together on the character. This is very important, and you achieve this via doing something called dilating the pixels. I thought actually that there was so many tutorials on internet about dilating pixels, that's why I vaguely mentioned it in previous parts. But as it turns out, I had many subscribers telling me that they don't know how to dilate the pixels. That's why I'll show it to you in action. Have a look here. I have my old texture, which is monk diffuse, and my new improved texture, which the monk is currently using on his material. It is called monk hands diffuse. If the monk's material, the monk diffuse, will have the monk diffuse texture applied to it, the old one, you'll see the immediate difference. Not in the color, because it can be changed, but in the way the seams are arranged. I'll maximize this window, and you can see that indeed there is a very ugly seam, mostly because of the border bleeding and the colors, but also because of the quality of the texture and the fact that we don't use the dilated pixels approach. It is very visible on the face. This is exactly where the border of the UV patch goes through, and it's very clearly seen on the face. The texture itself is of poor quality. That's why you see that the seams, that the knotted pattern on the top of his robe is very low pixel. How can we improve this? I will open up my PSD file from which both of the textures were produced, and as you can see, having made use of tutorial number 4 approach, where we've textured our character efficiently, I have my half of the face and the head be located on one spot of the texture, and one of the hands is split into many patches, and I'm hoping that because of the dilated pixels approach, my seams will not be visible, so I can split my parts into as many parts as I want, covering more and more of empty space with the texture. My dress is taking up the biggest space in here. That's because it was not unwrapped symmetrically, since its geometry is asymmetrical. Everything would be too similar if the dress would be symmetrical as well. But if we save this texture as it is in the JPEG format, the background will become white, and I can demonstrate this by navigating into the correct folder or actually making use of the shortcut, because to that folder I've been traveling so many times. It's the monk folder and materials. I'll save it as JPEG, for example, tutorial 8, no dilate. I will save it as a maximum file size possible, because if we compare it in the assets monk materials, monk diffuse, which was the very first texture, the most crappy ones, has the size of just 57 kilobytes. Our newly saved texture, no dilate, has the size of 420. But if we jump into Unity and look in the inspector menu, monk diffuse texture, which is currently applied to the character and reveals therefore crappy seams, looking as if it weighs just 53 kilobytes, when unfolded in the RAM, it takes 0.7 megabytes. That's the true size of the texture. So there is no point in being greedy and saving it as 53 kilobytes, because everything that you're doing is giving up on some extra quality of the texture with the same size. So 0.7 megabytes right here, much bigger than 53 kilobytes. But our tutorial 8 no dilate also has the same weight as our crappy old texture, even though it looks bigger in the Explorer, 400 here and just 53 kilobytes in here. But because our newly saved texture, although it's of much higher quality, even though it will have nicer texture resolution and less compression on it, it has no dilation. That's why when applied to the character, the seams will reveal themselves, since the UV patches are mapped exactly to sample from the borders. And here and then you'll see that because of that, the UV patches are making errors sometimes and are sampling one extra pixel of the white background, which will produce ugly seams, on which we'll elaborate in a second. So here you go. Monk Diffuse grabs our tutorial 8 no dilate, and as you can see, because the UV patches of our mesh are mapped exactly to the borders of the UV patches on the texture, we're getting nasty seams all the way through. To finally dilate our things, I'll show it to you on this Monk Robe Diffuse part of my texture. I've already got rid of the background that was accompanying it by simply going to select, color range, clicking on the black background and getting rid of it. Now when I have my plain layer, other layers are showing through it, but I can click on it and press Ctrl J 4 times so that I have 4 duplicated copies of it. I'll move them downwards, below the ancestor Monk Robe Diffuse from which they came, and starting from the bottom one, I'll move the patches just a couple of pixels upwards, then I'll switch to the layer above, move it a couple of pixels to the right. The next one, I'll move it a couple of pixels downwards, and then the last one will be moved a couple of pixels to the left. With the top one selected, I'll shift click on the bottom one and press Ctrl E to fuse them. Those ones will be called robe dilated, and with this dilated layer selected, I'll go into filter, blur, and select Gaussian blur, and just blur it by 1 pixel. Our dilated layer has to be below all the other layers, undilated ones, so that it does not appear on the way of other layers, such as head or fingers or hands. The same thing will happen to the face now. I'll grab it, press Ctrl J 4 times to duplicate it, then move the 4 layers under the head, and starting from the bottom one, I'll move it upwards, just a couple of pixels. The next one will be moved to the right, next one downwards, and the last one to the left. The 4 layers will then be merged into one layer, which will be placed above the dilated robe. As well as that, the dilated face or the dilated head will get Gaussian blur applied to it. That way you can improve on all of your UV patches, giving your UV patches some space to breathe in case they make a mistake and sample slightly to the right of their set space. Because of that, on that area space there will be no white background, but will be extra couple of pixels provided by us, dilated. We can then save this texture, of course with the best quality as we can, in the JPEG format. Tutorial 8, well, we've already done dilate, but this one will be called no dilate, just to illustrate the example. I'll rewrite and save it as almost 400 kilobytes, because if unfolded in Unity, it's still gonna take 0.7 megabytes. And as you can see, majority of the seams went away. You still have a couple of white spaces showing through, because I did not work on dilating other layers. I was just illustrating the example. Also, you can see white spots in here, because as we're moving it upwards, to the right, downwards and to the left, there are still some corners remaining. You might want to go with a clone stamp tool, press S on the keyboard, and do it in Photoshop, just clone and cover up those corners as well, before you apply the Gaussian blur. But we don't need tutorial 8 no dilate texture, because I already have one called Monk Hands Diffuse that I've been working on, and it has everything, including the pouches, being with no seams. Notice that there is no seam on the hand, where there was a very noticeable one previously, where the index finger joined the palm, and on the face there are no seams whatsoever. Obviously our monk has got a material applied to it, the custom one that we made, and I've positioned it in the Monk Diffuse folder. I'll get rid of those materials because we don't need them, and although we assigned our new material to the instantiated copy of the monk prefab, if we drag the monk prefab into here as well, you'll see that it lacks its materials applied to it. That is why we'll call this monk an obsolete one, and we'll show this with a double underscore before its name. Then I'll just drop it into the materials folder so that it doesn't bother us, and we'll create a new prefab which I'll call monk. From now on, we can drag the monk from our scene into the monk prefab, and this one, as we instantiate it, will contain the reference to the mesh and to the newly created materials. We're not going to be using the older version of prefab, but we still need it, so don't delete it. Couple of last things to do is that after we've established our camera to be in an appropriate spot, that is inside the hood, not being obscured by the face, we can make it to be the child of the monk by dragging it on top of the monk, and I'll actually drag it just under the monk to make it child number 1. Since the scene is pretty dark without lights, I'll grab this light and we'll position it in front of the monk just to give it some extra light when he's walking through the level. To make it follow the monk, I'll also make it a child of the monk, and we'll make it the second child. As we move our main game object, for the monk you can see that everything follows with it. The camera and the light change their values inside of transform appropriately. With the monk main game object selected that controls everything, I'll go into component, physics, and give it a capsule collider component. This is a quite common collider for the characters because it has rounded edges on the bottom and top, and some height to it as well. For the direction of my height of the capsule, I'll pick the y-axis, we'll increase its height upwards, and we'll position it appropriately so that it encapsulates the character's mesh correctly. Now, even though our character has the collider, it's still not affected by physics, and I would like to do so just to simplify our lives with the Unity's provided gravity. So I'll just stick a rigid body onto our monk character, and we'll increase the mass to 70. Beware that if your character and the objects within your world have the scale multiplied by 2, that is, for example, if this crate is not 1 meter tall, but let's say 20 meters tall, and if your whole scene is scaled up that way incorrectly, then your mass obviously in rigid body will have to be much greater, since physics are working from a Unity's default scale, that is 1 to 1. But because my character adheres to the scale of the world, his mass is 70 and the physics will be working correctly. It's gonna use gravity, and I'll freeze the rotation of the character. Collision detection will be continuous dynamic because it's a character, and it's very important to make sure that we collide with all the colliders within our scene and that all the checks we perform against them are gonna be quite precise. This is a very expensive option, but because we do it on just one object, one character, it's totally fine. Now if we drag it upwards and start our game, because of the rigid body and the use gravity option, he'll fall down and will collide with the mesh collider of my terrain. Like this. We got our light also rolling in the background, but currently it does not belong to this example. We've frozen the rotation so that he doesn't tip over under the influence of the Unity's physics. If we untick the rotation, he'll simply fall down on the ground. It's still not very precise, and we'll be doing something called raycast in a second. You'll see what I'm talking about, but the motion of the character will be jagged once he bumps into something. He'll still try to go through the wall and will be vigorously pushed backwards as soon as we add the appropriate script. Speaking of which, we can create a script in here in the monk folder, or any folder that's appropriate to you to keep the clean hierarchy. The C# script, which will be called player move. Having my monk game object selected with my collider and rigid body, I'll create a copy of this player move class as a component by simply dragging it on the monk object. I'll save my scene and we'll drag the modified monk onto our custom monk prefab, just to rewrite it. Now when we instantiate monk prefab, we'll have the monk character both with rigid body, the collider, and the script. Before we do anything, let's go quickly into edit, project settings, input. And as you can see, there is a rollout called axis, and there are several axes with different string names. For example, horizontal, vertical axis, fire 1, mouse Y or mouse X. Similarly to how I explained in the beginning of this lesson, if we open up horizontal axis, it's a variable that belongs to the input manager, and its value ranges from -1 to +1, depending on which key and for how long you've been pressing it. Alternative positive button is D, and the positive button is the right arrow on your keyboard. Because of that, you can affect the input with both the arrow keys on your keyboard and the WASD keys familiar to the gamers. If the D is pressed, it's a positive button. Because of that, the horizontal axis variable will begin to gain its power and will soon become 1. Similarly, if you press A, it will begin to subtract this value and will become -1 soon. Fire 1 is achieved with left control or the mouse 0, which is your left mouse button. You can also set up fire 2, for example, to be your mouse 1, which is your right mouse button. And then mouse Y and mouse X axes get affected as you move your mouse to the left or to the right, horizontally in the mouse X direction, and vertically is going to be mouse Y axis. As you move your mouse up and down, the value for this rollout, the mouse Y axis, will be growing. For our next example, two rollouts of particular interest to us are horizontal and vertical axis, because we'll be moving our character left and right with them, and then mouse X and mouse Y to rotate our camera up and down, left and right. Those axes are located in the input manager, which will be referenced via the class input. You'll see in a second. For now, I'll save my scene and we'll jump into the player move script. Because we already have a rigid body component attached to the monk game object, it will be pulled by the gravity. But we restricted its rotation in the world, and so it's up to us to make it rotate and move around. For now, since this script belongs directly to the monk game object, the main game object which controls everything, we can control it straight away from the update function. Inside of it, you can simply access the transform component of the same game object which the current script is located at by, of course, using the shortcut variable which was discussed many times. so the transform of current gameObject, and we can access the function called translate. Function is void, that is, it does something to the system but does not return anything. It's a modifier function. It changes something. And it requires a value of type vector3, which will be referred as translation within the function. There is also a couple of different ways to overload this function. If you don't want to supply a vector3 object or variable, you can simply pass 3 parameters, and they will be considered by the function as a vector3 as well. And so on. You can also provide relative to which space to translate this gameObject. That is, do you want to work along the local axis or the axis of the world? Currently, the translate takes 3 arguments, that is float x, y, and z. And so for the x value of float, we will provide whatever we'll get from the input class, the function's name horizontal. This is the first argument of translate function, the x1. Remember that the horizontal axis from the input can range from -1 to +1, and they're constantly being checked. So at any frame, there will always be some value associated with those axes. All we have to do is just to grab it, and then straight away to make use of it as one argument for our translate function. We'll put comma, and because we don't want to move our character up and down currently, we'll put 0 for the y argument, and for the z axis, which is the forward axis, we'll supply an input, and we're considered about retrieving the float value of the axis who has the name of vertical. Notice that horizontal is with the z, not with the s. Sometimes people catch themselves upon this. Now we've got 3 arguments for our translate function. The input from horizontal, which is either -1 or +1, which goes into the x. Up and down motion will be always 0. And sometimes we'll get different inputs from the vertical axis, that is from the inputs tied with W and the S keys, as described in the input axis. But -1 to 1 in x, 0 in y, -1 to 1 in z. And we close the brackets to close the input area for the translate function. We've supplied the arguments, now the semicolon, to end the instruction. And because this script is applied to our character, if we enter the gameplay, it will be pulled by the gravity since it has the rigid body component attached to it. And as you can see, we can move left and right along the scene, descending and ascending along the terrain and its collider. But we're moving very quickly, and this is because, once again, we're making use of the translate function in the update function. The more frames we have, the more times the translate function will be applied, and the quicker the character will be moving. That's why we have to somehow modify the arguments. The -1 and +1 should be multiplied by the class time.delta time, that is how much it took to render the previous frame. If it rendered very quickly, delta time will be quite small, and the resulting change of horizontal axis will be quite small as well. So quicker frame rates, slower movement. Longer time to render the previous frame, the bigger value of delta time variable of time class, and the resulting argument, be it y or z, is going to be greater. Let's save our script and test it out now. Now, independently of the frame rate, we're going to be moving with the same speed through our scene. If I maximize the window, therefore increasing the pressure on the graphics card and getting lower frame rate, we're still going to be moving with the same speed. But as you can see, the motion is jagged sometimes. That's because our collider interferes greatly with the collider of the ground. And even though we're using continuous dynamic collision check and are interpolating, this motion is still far from perfect. We'll see how we can improve upon that later on. For now, we're going to be bothered about rotation of the camera. Because camera is the first child of our Monk gameObject to which the script is attached, we have to establish a link via the script to our first child. Let's declare a variable that will hold a gameObject type, that is the reference to this gameObject, or what's better, to its transform. I'll call it camera transform. Inside of the start function, I will initialize it. Camera transform of our predefined variable, camera transform, gets the link towards the transform, which is located at the following path. First of all, we need to reference the transform of the current object where we are located at, that is where the script is located at, which is of course the Monk gameObject, its transform. From there we can make use of the function called getChild and supply an index of 0 to reference the gameObject, which is the first child. It is very important therefore that we don't mix the light and the camera, and that the camera gameObject stays as the first child, not to mess up the hierarchy. As we reach this gameObject, we can access its transform by putting .transform. And this is our final destination, because our camera transform is designed to hold the type of transform, as declared before. Now when this link is established, we can reference it in the update or wherever we want, and will mean always, by stating camera transform, the transform of the Monk camera. Notice that you cannot go deeper and supply another type, such as rotation, which we are going to be changing actually, Position and rotation are variables which are deriving from the transform class. But you cannot be sneaky and say, okay, I'll design my camera transform to be holding variables of type rotation, to go even deeper into transform. This would be impossible because you pass a link to the transform of the camera by reference. However, any values inside of its variables such as position or rotation are always passed by value. If you do attempt to prepare a camera transform float variable, for example like this, and then assign it to be equal to the transform of the first child dot, let's say, position dot x. This is totally fine, since the x variable, which belongs to the position variable, holds float values. But what you've done here is you simply copied the value at current state of time from x to camera transform. Remember that primitive types such as float, integer, character are not establishing reference from left side to right side. You simply perform assignment by value. That is, if you call in update camera transform plus plus, you're not going to change the value of x in the position in the transform component of your first child. You are simply going to increment the value that was copied and stored in the camera transform. You did not establish a link. You can only establish links to the objects that were created from class. This shortcut transform points to the object that was created out of the transform class.
If your camera transform variable is designed to hold objects of type transform,
you will indeed establish a reference. And later on, when stating camera transform dot position, you can debug it or whatever, and it's always going to be changing depending on the situation and depending on the current position of the first child, because you've established a reference via the camera transform. Since its type is not primitive, the whole variable is designed to hold references of objects made from this class. So be careful and make sure that you don't make this mistake. Otherwise, you'll be quite surprised why nothing changes as you increment camera transform's value, because there is no link. But now, with this variable, we are able to point to the transform of the monk's camera, not to its values, but to the object itself, meaning that we are able to reference it. And so during the update function, we can grab this first child's reference transform, and from there, make use of the function rotate. As you can see, it has 6 variants of arguments through which you can scrub by pressing up and down arrow on your keyboard after you've opened your first round bracket. The function's return type is void. That is, it's focused at modifying something within the system, but not actually returning your value. So let's say you've input some kind of arguments into here. Those are not correct, but assume you will. And let's say that you declare a variable of some type and call it t. Then you attempt to assign the value that you think will be on the right to whatever the return type of this function is. This function indeed takes 3 arguments, but its return type is void, and you'll get a mistake because you'll not get anything on the right side, and therefore the variable which is declared on the same line will not be able to grab any value and will not be initialized. Here we're saying that the transform component of the first child will invoke a function called rotate during every single update of this script, and we have to supply 3 arguments. We're going to work with this 6th version. We have to supply a change in the x, a change in y, and change in z, and also the space relative to which we are rotating. Is it relative to world or locally? You'll figure out how this works in a second. For rotation, imagine that you are currently looking through the face of the character. The z-axis is pointing outwards from the script, and the x1 is looking to your right. Y is looking upwards. So if we would like to rotate our head left and right, we'll have to perform a rotation around the y-axis. If we would like to rotate our head up and down, it's going to happen around the axis which is sticking to our right. That is the x-axis. So for x, we'll once again ask the input class to provide us a value of the variable which will be retrieved via the getAxis function. We are interested in mouse up and down movement, that is the y. As we move our mouse up and down, we would like our character to nod the head up and down as well. Nodding, if you think about it, happens as you rotate the camera around the axis that sticks to your right. That's why it's the first argument, and it's why we're searching for input stored in mouse y-axis. To rotate your head left and right, you're going to revolve it around the axis which sticks upwards, that is the y-axis. And because of that, the argument which we're about to supply is going to be concerned of the 2nd argument. We've already supplied the x argument, now we're supplying the rotation around the y-axis. Once again, it's going to be input. We are concerned about mouse horizontal movement, because if you want to rotate your head left and right, you obviously want to do it with the horizontal mouse movement around the y-axis. That is why we've put it to be the 2nd argument. And now finally, the rotation around the z-axis, which is sticking outwards from your screen, and it would be the clockwise and counterclockwise rotation. It is not necessary in our case. That's why we'll always put it to be equal to 0. We don't want to rotate our head clockwise and counterclockwise. In our case, if we're controlling the character head with just mouse, vertical mouse movement is supplied as the rotation around the x-axis, that's why it's the first argument. The second argument is concerned of y rotation, the y argument, rotation around the y-axis which sticks upwards from the screen. And the argument which is concerned about the rotation around the z-axis is always going to have its value equal to 0. Having saved your script, we can jump into the gameplay mode and see how our camera reacts to the movement of mouse. Indeed, as you move your mouse left and right, you get appropriate change in the first child's rotation. But as you try to move your camera down, it instead moves upwards. And the same thing happens if you move your mouse upwards, the camera points downwards. So it's an inverted motion of camera. Because of that, you have to invert the result of input of mouse Y by putting simply minus. So now the vertical mouse input will be inverted, but the X will stay the same, meaning that we can point our arrow to wherever we want to and we'll get the appropriate response. You can also lock the arrow if you don't like it by simply stating once somewhere in the start function, for instance, that the cursor, which belongs to the screen class, is going to be hidden or locked. We're going to say that the screen class, which is provided with the Unity Engine namespace, its variable lock cursor, a value which can be read and set as well, as stated here. And it's boolean, so it can take either true or false value. This variable will get a value of true. We do want to lock the cursor as we start our game. From now on, during the start function, we'll lock our cursor and it's going to be hidden from us until we press the escape key and decide to quit the game. Notice that the rotation which occurs here is happening locally. That is, our camera becomes tilted in a very strange way. We're not rotating relative to the world space, and we do so locally towards the local axis of the camera, and pretty soon the camera gets messed up really quickly. If I pause the game, you can see that we are looking sideways now, and having selected mount camera and picked local axis, you can see that the axis of the camera are no longer pointing in the appropriate directions. Suddenly the upwards axis is looking to the side, like this.
The Z is still pointing forwards,
but the X is now looking downwards. That was not the case as we started the game. I'll start it once again and press the pause. And as you can see, the y-axis are looking upwards
and the Z is looking forwards.
But then after some time it will get messed up. This is why the rotation around the y-axis should not happen around the local axis of the camera, but around the global axis, which never changes. Inside of our rotate function, we can supply a fourth argument, which is relative to which space we are rotating the object. And obviously, because it derives from the space class, we have to provide a value which derives from the space, dot, and as you can see, space is an enum. It has two values, self or world. We want to do it relative to the world axis. Notice what will happen now. We can rotate as much as we want, and the y-axis will never get messed up because we're rotating around the y-axis. However, the x-axis stays relative to the world as well. It does not change and rotate along with the camera. That's why as we turn to the side, the x-axis still keep pointing to the side of the camera. And so we'll do two rotations. I'll duplicate this function. In the first one, we'll supply a rotation of 0 in the x-axis. That is, up and down, nodding of the head will be 0. But the rotation around the vertical axis, looking to the side, to your right and to your left, is going to occur relative to the world indeed, because we don't want our vertical axis to ever change. In the second call of this function, we'll get rid of the y component this time, the y argument, the second one. It will be 0, since it's already altered in the previous function. But this time, the x-axis is going to happen relative to the space.self. Our local axis will always be pointing in the way the camera points, and will be performing the rotation around its x-axis, the nodding up and down, relative to ourselves, to our local axis. But we will always rotate head left and right relative to the world space. As you can see, now we can look around normally, and our camera does not get messed up. We can look up and down, and look to the left and to the right, relative to the world space. Even if we look downwards, yes, indeed our local y-axis is pointing upwards, currently towards the play button, but the world one, if you can see on the left, is still pointing upwards. That's why as we change the inputs value for the mouse X, the horizontal movement, by moving our mouse left and right, we are rotating around the global y-axis of the world, and not around the local one, which would be pointing in this direction, messing everything up. As for the X, nodding occurs around the red axis, which is constantly changing its position, not the world's axis. This required us to do two calls of the function called rotate. Also observe that we can move our character right now, but not in the direction which we are looking at. First of all, the motion is quite jiggly, and we'll fix on that as well. In fact, we can get rid of the rigid body component for now, because we're just concerned about the forwards and backwards movement, left and right one as well. We don't care about being pulled by gravity at the moment, so I'll get rid of this component temporarily. Using rigid body for the character is a very rusty and quick way to simulate gravity and be pulled by the surface, but if the surface itself is very rigid and is using a mesh collider, which has irregular surface, you'll get quite a noisy movement as you attempt to move your character leftwards and rightwards across the land. We'll create something different on our own with a set of colliders. However, for now, let's see how we can move in the direction which we are looking at. Since if we point our camera to the right and press the upwards key, we're still going to be moving along the axis relative to the world space, not to the one we're looking at with our camera. Because of that, we're going to apply the rotation around the vertical y-axis, not to the camera transform, but to the transform of the game object itself. By changing this to transform and applying rotation around the vertical axis, the second argument, the y-axis, with the horizontal input of the mouse, we're going to be rotating the object itself because we're accessing its own transform. But the rotation, the nodding of the head up and down movement is going to happen with the camera's transform. Now, as we move our mouse to the left and to the right, we're going to be rotating the whole monk. And because it's moving relative to its local axis by default, it's going to move as I press forward key in the direction where its z-axis is pointing. If we're looking up and down, this just incurs a change in the camera. We're not being pulled down by the gravity, that's why we cannot go down and are forced to go through the wall if we would like to do so. Having done such a sweet job for our character and making him move, we can now give up on using the rigid body to pull our character downwards towards the ground and then make use of our own invention. Here I'm thinking of making use of one additional opportunity provided by the physics class. It is called raycast, and it is extensively used in shooter games. Performing a raycast means that you are sending a ray in the specified direction and checking for any intersections with colliders within the scene. You can do it cheaply with just detecting if the collision happened or not, or ask for a slightly more expensive one, but being able to retrieve more information about what was hit, at what distance, at what incline, etc. Because of that, we'll cast a ray downwards from the very head of our character, downwards towards its feet. The ray will be of an infinite distance, or quite a big one, and we will check if we are colliding with the collider whose game object has a tag of terrain. First of all, let's establish the ray and see if it's working. We're going to be performing such checks inside of our fixed update function. Raycast is quite expensive operation, so we'll do it now and then, not every single frame like during the update. We've discussed fixed update before and how you can improve its quality by changing the intervals at which it runs in Unity's settings. Go and check it out in the beginning of this tutorial. To be fair, I'm going to simplify our life by a great amount, and I'll just go to Unity documentation and search for a raycast. As you can see, it belongs to the physics class, and it's a function which returns boolean, and because it's static, it means that it can be used without instantiating a class. To use it, we just mention the class and make use of the function. I'll scroll down to the one which I need, and I need exactly this one. That is, we're declaring a raycast hit variable inside of the fixed update every single time it runs, and after that we're performing a check. We're making a call to the static function raycast, which was described in the class physics. The physics class we can access because we're making use of the namespace Unity engine. If we get rid of it, you'll immediately see that everything including MonoBehavior, transform, raycast and physics are unavailable for you to use. Also, the start and update functions will not be recognized, since MonoBehavior becomes unsupported. But having returned it back and saving our script, giving it some time, you can see that everything falls back into place. That is, inside of the fixed update, we are declaring a variable hit of type raycast hit. Raycast hit will be an object which contains different variables with different information. We'll make use of certain parts of them. But inside of the if statement, we can make use of the raycast function which belongs to the physics class because it returns boolean. You can go and check with the Unity's documentation that this is true by inspecting it in here. Also, if you open up the arguments brackets, you can see that it indeed is a static function, returns boolean, and can be overloaded with 12 different versions of arguments. Here we're supplying the position, which contains x, y, z, mathematical coordinates, from the transform component, which belongs to the same game object as the instance of this script does. So basically the position of this script, we're sending our ray downwards. Its length is 100 float units. If we want to, we can actually ask for it to be mathf dot and make use of the variable called infinity. But 100 seems okay.
One more variable, which we didn't talk about, is out.
Out means that anything that gets thrown into the function as this argument, the function will do something, but then anything that it does to this argument will be actually applied to the variable that was declared before the function. Let's say for some reason the third argument has to be of type integer, and we pass an int hit into the function with the keyword out. Function grabs it, works on it, and says that okay, it has to be incremented by 1. Because this argument had an out keyword, the hit that was specified before the function will get its value altered. So it's not like passing by value, it's passing the argument by reference for a further change. After this function has done something, it will first of all return boolean to see if we did get any kind of intersection with any colliders. And while doing so, while producing the final output, it will also do something to the hit variable. Because of type raycast hit, it will alter its required variables appropriately and will update different values inside of the hit variable right here. We can then make use of this hit variable after the function has finished executing. But because its output type is either true or false, we can totally put it in the if statement. Because I want to put more than one line of code after the if statement, I have to put curly brackets, and then I'm not bound to just a single line of code. Nothing hard on this line, we're just declaring a float distance to ground variable and then assigning it a value that we extract from our raycast type hit variable that got updated via the function during its execution. And you can see that we can pick anything, collider, and from there if you want to we can even pick gameObject or transform, which belongs to the same gameObject as this collider does. But in this case we're interested about the distance to the collider, and if distance to ground is greater than a certain amount or equal to, well, let's say for now greater than 2.0f float. In this case, we'll make sure that our character gets pulled downwards by a certain amount, so that this value gets smaller until this check is not true. That's why we'll ask the transform of the same gameObject as this script belongs to. We'll ask it for the function translate by the following amount: 0 float sideways, something for the second argument, and 0 forwards. For the second argument, that's translated by negative 0.1. Remember that although fixed update does not happen as often as update does, it will still occur about 30 times a second, which is a good thing, but the values have to be reasonable here. Along with our raycast, we can also debug.drawRay. It's another function which allows us to draw a ray. A ray is different to the line because it has a start and the direction. The start of our drawRay will be the transform of our gameObject.position. Position, as you can see, contains further x, y, and z variables, but it's of type vector3 itself. That's why we'll supply it as a first argument, and then for the second one it has to be vector3 direction. Let's create a new one, although it's not a good practice, but we can create a new vector. Since it's debug anyways, we'll get rid of it later on. New vector3, and we'll supply 3 arguments. 0 in x, negative 100 float for y, it has to be float as well for x, comma, and we'll put 0f for forward direction. It will be exactly equal to the ray that we're casting via the raycast, because here the direction that we're specifying in the raycast is the inverted upwards vector, which is downwards, and its length was set to be 100. Here we're just saying, okay, grab the transform position of our object and draw a ray of length 100 downwards, because it's a negative y direction. We can also change its color by supplying a new color, let's say 0.5 for red, 0.5 float for green, and 0 float for blue. If we go back into Unity, in the console we get an error saying that the best overloaded method match for Unity transform translate float flow float has some invalid arguments. That means that for arguments that we've provided, there was no alternative overloaded method, so there was something wrong in here. Indeed, translate takes float arguments, as specified in here, and if we look closely, we did specify float to be 0 for the first argument, but we didn't do it for the second one. It has to be float as well, otherwise it's being considered as double. So double precision with a decimal as well, but it's not float. So the function refuses to take the value of this argument. If you have a look, at the bottom of the character there is a yellow ray, which is not clearly visible, but now you can see it. It's bright yellow and it's pointing downwards. That's exactly how our raycast is being cast as well, along with this ray. On a different line, it's being called. If I pause the game and bring our character upwards, you can see that indeed the character gets brought downwards due to the fixed update function if the distance towards the collider whose gameObject has a tag of terrain, if its distance from the beginning of the raycast is greater than 2 units. We can actually reduce it down to 1.8 so that the monk touches the ground appropriately. After it's done executing, you can see it in the bottom right corner. Now he goes down more. It's still not enough, and we need it to be something like 1.5, maybe 1.4. Or actually the alternative would be to bring the start at which the raycast begins casting to be somewhere higher. That's why when we call for our raycast function, the argument that we'll supply in the transform, instead of the first one, the native position of the game object, which the script belongs to, we will actually subtract a value from the position. But because it's a vector, when we subtract something from it, we also have to do it via the vector. Because of that, let's declare a variable at the very top of our script so that we don't redeclare it every single time, of type vector3, and give it some reasonable name. For example, something like character ray offset. It will be initialized in the start function to establish a reference to the new vector3 object, which will have a value immediately passed to its constructor to be zero float in x, something in y, and then 0 float in z. For the second argument, that is the y, we will pass an offset of 1, and then once we have this vector, we can constantly add it during our raycast check to the current position of our transform. We thought about subtracting, but it's going to be correct to add it instead. Constantly during this raycast function, we are reading the position vector3 of our gameObject's transform, and we're sticking on our predefined vector, which has a value of 1 pointing upwards. That is, our raycast ray starts 1 unit higher than it would be normally. And for debug.ray, let's do the same thing. Wait for our script to finish initializing, and you can see that the ray is now being cast from a higher position than before. If we increase the value that we pass during the creation of the vector object, which then gets assigned to our character ray offset during the start function for the further use, to something like 2 in the y argument or maybe 4, then the ray will be cast not from the game object's position, but with a vector added to it which has a value of 4 higher than the game object's transform position. In fact, there is one interesting thing. If we indeed increase the starting point of the vector to be something like 4, then its starting point will be somewhat higher, somewhere here, and now it's outside of our capsule collider. It's gonna encounter a hit at the top of our capsule collider. Because of that, we are now hitting the capsule collider instead of allowing our ray to start inside of it and go through the collider, hitting the ground. So raise the starting point of your collider, but be reasonable. If the starting point goes outside of the capsule collider, you'll be hitting with it instead, preventing you from further actions that are described in here. 2 float seems okay, and because of our debug message which just grabs the same value of our predefined vector, because of this debug log, we can immediately see where the ray is being cast from. Now because it's higher than before, the distance is calculated from a different point. If I raise the mesh of the character and don't enter the gameplay mode, you can see that the ray is being cast from this point, somewhere from the head of the character. We don't need it to go that much down, so I'll reduce the character ray offset to an amount which suited us, something like 1.4. Now we're raycasting 1.4 units higher than the default position of the game object. The monk still has to be higher, therefore I'll reduce our offset vector by a smaller amount so that the ray starts to be cast from a slightly lower point. This seems okay. This way we've produced gravity. However, if there is an incline in the terrain, the character will go through it. Think about why. Let's drag our character somewhere closer to the different building, somewhere here. If I bring it up like so, you can see that it begins to touch the collider perfectly. But if I take over the control for the game, you can see that I'll still go through the ground. This is because we're checking for collision with the ground, and if we detect that it's at a distance greater than specified one, in our case if it's at distance greater than 1.4, then we translate our game object downwards with every single fixed update. And it holds true because we're still recording collisions with the terrain even as we go through it. We're not being pulled down anymore because the distance between the start of the ray and the terrain collider is smaller than the set one. But in this case, we should state that the character has to be pushed outwards to an appropriate distance. Because of that, we'll say otherwise, we need to detect by how much we're below this set amount and discard this change. Because of that, we're going to apply the translate function to the transform of our game object. And for the arguments, we will supply 0 float for sideways movement, because we don't want to translate our game object leftwards or rightwards, something for the vertical movement, and 0 float for forward movement. Our second argument, y, is going to be the interesting part of this code. Let's say that for now we put it to be offset by a positive 0.1 float vertically, opposite to this instruction which tells it to go 0.1 negatively if the distance is greater than 1.4 float units. Because of that, as we go into Unity and enter the gameplay mode, the character will start to jump up and down as it hits and leaves the collider, because as soon as the distance becomes less than 1.4, it's by a very small fraction. And we're still telling our game object to increase its vertical position by 0.1. 0.1 plus the little fraction by which the object was displaced on top of our 0.3 makes it higher than 0.4, forcing us to go down and subtract 0.1 from our vertical position. Because of that, we're constantly jumping between else-if statement, increasing and decreasing our position. That's why, first of all, we have to get rid of this equal sign and then check if our distance to ground is less than 1.35 float. And in fact, distance to ground here should be greater than 1.45 float. We're giving it some error space. Now, as soon as we detect that we are less than this amount, we can increase it by 0.5. So by the half of the previous amount. And here we can do the same. But this still produces a very jagged up and down movement, and you can see it relative to the spear as we are raising ourselves along the terrain collider, that is walking up the terrain. That's because this amount is still quite big. Instead, let's leave it like it was, that is, subtract 0.1 float vertically if it's greater than this amount, but if the value of our vertical position is less than this set amount of 1.35 above the collider, the x argument is going to be 0 float, we'll leave something for y, and the z, the forward movement, is going to be 0. For the y component, we'll state 1.4 float minus distance to the ground. That is, we'll pop it up back by exact difference between the current distance to the ground and the minimum one. The translate function requires a float value, that's why we're gonna inbound this in the brackets to signify that it's just one argument. And the editor might still not understand that this is a float value. So we're gonna explicitly state that all the brackets on the right are gonna be cast to the float value. Now all the three arguments are of type float, and the translate function will work. We've done a very good job on making sure that our character does not fall through the ground and gets attracted to it until our raycast ray reaches an appropriate distance to the collider. Because of that, he's staying pretty close to the ground, but as we move upwards, you can still see the tiny jiggly motion, the bouncy motion up and down, especially when you're close to objects, and if you're going not along the perfectly horizontal line. Because of that, we have to take into account the normal of the surface which we've hit with the raycast.
We've already talked about normals in 3ds Max, and this is exactly the kind of thing that our following example will demonstrate.
Currently we are translating our character some certain distance in the x, y, which is 0 always, and z. The values get changed depending on how much input we receive from the appropriate axis, and will propel our character forward. But in this case, I would like my character to move in the direction which is parallel to the ground, not try to smash through it always forward, hoping that those two if-else statements will save me and will pop my character back in place. That's not really how it's done. Because of that, I'll declare my third helpful vector 3, which I'll then use
to alter my input parameter of the translate function.
I'll call it translate fix, and this vector will be initialized just to the one which points directly in front of our game object. So translate fix is now going to point towards the vector 3 object, which will have 0 for x, 0 for y, but is going to have a value of 1, that is, it's going to be pointing forwards at the beginning. During our fixed update, right after we declare our distance to ground, we're going to be changing the value of our translate fix to the following. Translate fix has to now point towards the newly produced vector, the one that is going to be the result of vector3.cross function. We've talked about vectors before, their components, but in maths there is one interesting thing which you can do to your vectors. If you decide to cross multiply vector A by vector B, you'll get a third vector as a result, which will be perpendicular to vector A and vector B. So for instance, if you multiply the vector which has a length of 1 and points in the x direction by the vector with length of 1 pointing in the y direction, when you cross multiply them, you'll get a resulting vector which will point in the z direction and will have a magnitude of 1. That's why we would like to receive a vector which will be parallel to the ground that our raycast ray hit. The surface which we're hitting, of course, has a normal, and the flat surface will have a normal which is pointing directly upwards. The surface which is tilted will have a normal which is pointing towards our camera at an angle. If we would like to get a vector pointing in the forwards direction from us, and which is parallel to the surface which we've hit, it's going to be the result when we cross multiply our local right axis, the x1, by the normal of the surface which we've hit. That's why I'll supply in here our local transforms dot, and there is a value called right. This is a local right, and for instance, if I select my object, currently the local right is the x-axis, which is pointing to the right. If I rotate it a little bit, in the local representation, my x-axis will be pointing in different direction. That is the local right of this gameObject's transform. The second argument which I'll supply is the normal of the hit collider. If we now call for debug.drawRay, we can supply its start to be the transform.position. Remember that you can't supply the transform as the first argument because it's a reference to the component. The position, on the other hand, is a variable of type vector3 which fits in the first slot. The second one is the direction, and for that we're gonna supply our translate fix. It's the direction along with length as well. With this line of code, we're going to be able to see our translate fix starting from our transform position of our monk, to which the script is attached. As you can see, there is a white line coming from the bottom of the monk, and depending on the incline of our surface, we get it pointing in different directions. Currently, it's pointing upwards, but then as we turn around, the normal of the surface with which our ray collided, cross-multiplied by our local right, produces another vector which is parallel to the surface, and is displayed with the white ray. As you can see, now it's pointing downwards. If we turn around, it's going to be pointing upwards. This vector is the key to smooth transition and movement of our character. Now, when we've established our translate fix vector for this instance of fixed update, it was already stored in memory, and the next update function can already make use of it. Vector, as explained before when you were watching the beginning of my intro to Unity, each vector has mathematical components. And in this case, the y component, the one that is pointing outwards from our character, also being parallel to the ground, is gonna have some certain magnitude. We don't care about the x or z components, but the y component is the key. Once we've received our vector here, we can now actually translate our character up and down whenever we want to move him forwards, but we'll have to of course multiply it by time.delta time, and multiplied by our translate fix vector by its vertical y component. And this is going to be our translation of character up and down. Notice that now he's going to be displaced upwards and downwards in the direction where the vector is pointing. And now the transition is very smooth. As soon as we reach the flat surface, we're no longer moving forwards. And as we start to approach the surface of which is a decline, the vector now begins to point downwards and we begin to descend. You can clearly see it if I turn around like this, and we begin to descend downwards. Notice that there is now no jiggly movement. We will only get ourselves equalized to the ground in case if we somehow manage to fall through it or fall from above. As long as we are within the range and are not triggering this check, the translate fix, which is parallel to the surface and is pointing outwards forward from our character, it will provide its vertical component, which allow us to displace ourselves parallel to the ground and not go through it, forcing our else-if statements to push us back in place. We're just sliding along its surface very nicely. It's quite cool. I actually forgot that I turned off the tessellation on my shader. That's why I'll put it back in, because it's here for demonstration purposes. Now that we got our character, finally it's just all about making him animated, and I'll show you around what we're going to be doing in the future. That is how we can develop our own terrain. Our monk character, which is explained with this prefab in here in our monk folder, it has an animation component, and currently we have 0 animations on this character. Let's increase it up to just 2 at the moment. I'll click at monk.addWalk, which is the FBX imported prefab containing 1 animation. Having my monk at walk selected, I'll go into animations. We'll drag our monk at walk into the preview area, and as you can see, I've animated him just walking along the surface. It's a very simple walk cycle. We've been doing this in tutorial number 7. I'm pretty happy with it. I'll just make sure that in the rig itself, the animation type is legacy, and that animation is called walk. It takes up 24 frames. We can shorten it by pulling either of the ends of the slider and set it as a loopable animation. Then we can click apply, and our animation file will be readjusted. It's this file in here, the walk one. Back on our main monk prefab, it actually has to be rewritten with our monk that we've been working on, and only then we should apply animations to it. So I'll click on my monk and we'll drag it on top of the monk prefab to now establish a new connection and rewrite the current prefab with our new version of monk. Now we can begin to throw animations onto our prefab. I'll make sure that the animation size is something like 2, and we'll stick the walk animation from the monk at walk into the first element. By default, we're not going to be playing anything. Also, I have couple of animations fused into one in here, and the FBX file which is holding it is called monk@inventory and as well as idle. As you can see, when I play its animation, monk crouches to look in his inventory, and then he stands idle for some time. We can check which time it is by precisely setting up our frames, or if I know which frame it is, I can just enter it here. Unfortunately, I don't remember which frame it is, so I'm just gonna find it by trial and error. It's starting at 71, and we can add another animation, which is going to be inventory idle, and it will last only up to 71. Actually, it should last up till 70. I'll click apply. Because of that, we have now 2 animations, and those clips are stored in our monk@inventory idle. Here you go, 2 clips. Idle and inventory idle. Here, let's make sure that the monk prefab makes use of the idle animation. It's going to be the second element in our animations array. We will be playing them as soon as we start to walk with our character. Once we got our animations dropped onto the monk character from other FBX files, it is now time to make use of them. During the start function, I'll access the animation component local to the same gameObject as we are currently located at with this script by using the shortcut variable animation, which can also act as an array of your animations. That is, you can access any animation that you've dropped previously into the animation component, for example, the walk clip, and having accessed it, we got different settings to tweak our walk animation further on. In this case, my walk animation should be always playing at a speed of 0.6. At 60% from the normal speed at which it was imported. Inside of the update function, we're going to check if we're receiving any kind of input from the user. In here, I'm gonna check if our horizontal and vertical axes belonging to the input class have any value other than 0, and 2 vertical lines is a logical operator which is OR. That is, if either the left side is true or the right side is true, then the whole statement will be true. If you would want to use AND instead of OR, you would have to use the double AND %sign. This means that both of them have to be true for the whole statement to be true. In this case, indeed, I need AND, because in order to play an animation idle, I have to ensure that I'm not receiving any input in those 2 axes. If the horizontal input is exactly equals to 0, and if the vertical input is exactly equal to 0, only then we'll perform the following code. We will also do a check to see if there is an animation playing in our animation component local to this script. And as you can see, there are 2 things. IsPlaying is a Boolean variable which can be either true or false, which is going to be true if there is any animation playing in our animation component. IsPlaying function allows you to see if the particular animation clip is playing at the moment. I want to see if the animation called idle is playing at the moment, and by putting an exclamation mark, this statement will be true if there is no animation idle playing. Once this is true, I can make a call to my animation component and start to play my animation clip idle. If you make use of play, this will abruptly change your animation clips in place, resulting in a very sharp change. Because of that, we're gonna put crossfade and smoothly change one animation into another one. But if there is no input on any of the axes and the statement is not true, if there is an animation called idle playing, then we don't do anything and keep on playing it. If, however, we do get some kind of input, then we would like to check, first of all, if the animation called walk is not playing, and if it's not playing, then crossfade into walk animation. Remember that our walk animation is going to be playing at a 0.6 speed from the default one, because I found it to be too quick relative to the speed at which monk moves. The idle animation is set to be loopable. If I click on the file which contains it in the inspector, that is the monk@inventory idle, having picked my idle animation, you'll see that it's loopable because its wrap mode is loop. You can change the wrap mode anywhere. For example, in the start function, you could have said that the clip called walk from our animation component, its wrap mode becomes equal to wrap mode, which is an enum, and we could have done it play only once, for instance. But we need to make sure that it's loopable. Because it's set in the inspector, we don't have to do it here, otherwise it would be a necessity for those checks to make sense. Let us check if we get any kind of errors. And inside of the console we get a message that we cannot implicitly convert type double to float. We need to add the suffix f obviously, because our getAxis horizontal works with float. If I open up its opening brackets for arguments, you'll see that indeed getAxis is of return type float. That is, if we compare its return type, it has to be compared to a float value. After we save our script and it's finished calculating, this is also the case for our animation walk speed, because the speed is also of type float. We'll add f in here to fix the error. Don't worry about this warning because it's concerned about my other animations with which we are not working in this case. So if we don't give the computer any kind of input, we're going to be playing the idle animation. As soon as we press on one of the buttons, WASD, we start to play the animation of walking. But as we stop, we keep playing the idle animation, where he's doing some kind of heavy breathing.
Yo man, I'm here to cleanse this place from evil. Obey me, and you shall be saved.
The reason why we get a delay of movement is that we will only begin to crossfade into the idle animation only when the horizontal input has reached a value of 0. As soon as I release my key button, the get axis does not get immediately down to 0 because of Unity's smoothing. That's why as soon as I release my key, there is still some time until it becomes 0, and only then we start to crossfade into idle, which also takes some time to transition smoothly between the animations. Because of this, we're not going to be searching for if we have any kind of input from any of the axes, be it horizontal or vertical, when we want to check if it's needed to crossfade into animation. But instead we'll make use of a different function called .getAxisRaw. AxisRaw returns either 0, -1 or 1 without any kind of smoothing. And this is exactly what we want for this kind of purpose. Now we won't have to wait until we figure out that we actually reached the 0 on all the axes, and we should start to play the idle animation. There you go, immediately after I release my key, he crossfades into idle animation. We still receive the smoothed out input as we translate the character, but this is a different story. Here it does not matter, whereas if we quickly need to check if we need to begin to crossfade into different animations, it's very useful to see if we're actually receiving any input at this particular moment of time. If not, immediately start to crossfade into the appropriate animation. There is a couple of optimizations that can be done to our script. In particular, when you're done with debugs, get rid of them, because debugs are quite expensive, especially if they have to be produced within the different internal loops. We don't have any loops in here, but still it's nice to get rid of them. I'll press Ctrl F and search for debug. It seems like we've already got rid of all of them. Remember 2 rules. Try to minimize the code inside of your functions which are run many times, such as update for example. Don't perform heavy operations in it, and God forbid establish any kind of relations with gameObject.find or getComponent. If you ever need to do this kind of stuff, make sure to do it once in the start function. The start function is where you initialize the variables, establish references to objects, to later on reuse them within your other functions. And it only really matters if your code is heavy once the profiler of the game says so. We'll see how we can profile our game later on, but profiling is basically seeing at which point of time your game can hiccup. In such instances, you put your profiler on pause and then inspect the particular moment of time, going through resources and seeing what caused the big overhead at this particular moment of time.
After you've optimized the character so that it changes its displacement vector and uses it to translate itself forwards parallel to the surface, you've now avoided those moments in time where you smash into the ground in the hope of being popped back in place vertically with your if-else statement. But if you look closely, when you stand on some kind of slope, be it a slopey ground or maybe a tilted surface, that is the terrain, your smooth movement works only when you move forwards. But if you try to raise yourself along the hill sideways, you'll see that you are still being popped back in place with your if-else statement, since you are still trying to jam through the geometry horizontally. The way we've written our functions does not modify our direction horizontally. It only helps us to do so when we want to move forwards. So think about that, how you can improve on it, and come out with the answer. I'll provide you the answer in about 10 seconds. Think about it, pause the video, experiment, and then come back to see how you can improve on that. The trick to this is to declare a second vector, which is called slide translate fix, and the first one was the forward translate fix. We declare them in the beginning of our class, and then we initialize them to point to vector objects in our start function. Just like before, our forward translate fix vector is the one that is perpendicular to the transform right vector, that is the local right vector that points to the right of our game object, and the normal that we've hit under us. With that way, we'll get the forward translated fix vector, which will be pointing parallel to the surface which we've hit, pointing outwards, forwards from us. Side translate fix has to be also done with a cross product vector between the forward vector that was produced just a second ago, and the normal as well. If you think about it, you will then have a vector which is also being parallel to the ground, but is at 90 degrees angle to the forward translate fix one. I then just debug.drawArray of our forward translate fix with the white color, and I draw a ray with the red color for our side translate fix as we enter our play mode. So let me see some kind of slope, establish it in here, and you can see for yourself. Now we have two vectors. The white one is pointing upwards and is parallel to the surface which is under us. The red one also adjusts itself, but it's always at an angle of 90 degrees to the white one. And so if you try to move yourself to the left and to the right, the red one will come into play and help during this horizontal movement. White one will work for the forward movement and the red one for the sideways movement. But to do this, you still have to provide a couple of instructions, and what I've done here is I've taken a different approach. Now I'm making use of two translate functions. If you remember, translate function has different ways of supplying arguments, 6 ones as you can see here, and we're picking this one, where you have to supply a vector3 translation and the space relative to which we are moving. First of all, let's establish the horizontal movement and translate our character horizontally. In this case, we will see which kind of scalar value we'll have, that is the one that contains just one mathematical component, unlike vector which contains 3 mathematical components. But here we see if we're getting values between -1 or 1, then we multiply it by the time which it took us to render the previous frame, making sure that the speed at which we move does not depend on our frame rate. And then finally, we're multiplying all of that scalar thing on the left by the negative vector side translate fix. So it's simply modifying the length of the vector, the direction of which was pointed with the red drawArray debug. We're making use of our horizontal vector, the value of which was defined in fixed update. It has to be a negative in my case. You can try with a positive one, but you'll soon see that you are moving in the opposite direction. So just put negative here in front of the vector and then modify its length by how much you want to displace your character with the scalar coefficient that is formed from getAxis horizontal value multiplied by the difference of rendering frames value. And then finally, you have to do it relative to the world space. You can test out with the space.self to make sure that you displace yourself relative to the gameObject in the direction of the vector. But as it comes out, and if you think about it, it's not going to really work. You have to do it from the world space. That is from the 0th coordinate of the world, rather than from the 0th coordinate of our gameObject. And then we do exactly the same thing, but this time we're making use of the forward translate fix vector. That's the direction at which we're going to be displacing our character as we get inputs from the vertical axis. And then we multiply this -1 to 1 range value by the time it took us to render the previous frame. It also has to be done relative to the space world. And there you go. Now your character will be moving properly in all the directions. One very important part which we still need to consider before we finish the core of this lesson is the productivity. Well, it might be kind of early for you, because I assumed that you just started. However, as you develop your games, it's a very important knowledge to have. How can you improve the performance of your game? First of all, how to see if performance is bad, and where to seek mistakes. Today we'll not be going over the profiler and looking for mistakes in the profiler. On the option that sits in the window, Profiler. This thing will allow you to see the spikes and hiccups of your game at particular time when it's being run. What we're going to be focusing today on is the rate of frames per second that is being rendered every time to the screen, and we'll see what it depends on. Strictly speaking, there are two things to worry about. That is how well your GPU is working and how much offload you're putting on your CPU. CPU is the central processing unit, that is your processor, which is busy working on the scripts, setting up the relations of things, but also quite an important piece of its job is passing the information to be drawn by the graphics processing unit, your graphics card. This kind of instruction that is being passed from CPU to GPU is called a draw call. Every single time you have an object on the screen whose geometry has to be rendered, it has to be passed to the graphics card so that it can perform certain mathematical operations which will finally result in the picture on your screen. For every single object, this instruction has to be issued to your GPU, and it is called draw calls. One important thing is that every single CPU has something as called CPU cycles. That is a certain number of instructions that the CPU can take at a given time. They directly relate to your number of cores inside of the CPU and the CPU frequency. The higher the frequency is, the more cycles the CPU will have.
For example, 3 GHz equals to 3 billion Hz, which equate to 3 billion cycles. And because this number is limited, you have to issue as less draw calls as possible. Of course, you don't do one draw call within one cycle, one CPU cycle, because it's a very primitive way of manipulating data. You need several of the cycles to issue a draw call. But your cycles are a limited resource, and if you spend it on issuing many draw calls, your CPU will be busy passing the information to GPU and will not have its resources available for other things, like calculating gravity, physics of your game, scripts and artificial intelligence, not mentioning the programs that are running in the background along with the game of yours. So this is one aspect of productivity, making sure that there is no overhead on the CPU side. But then there is the GPU side. An overhead can happen on the GPU side if there is too much geometry to render, first of all, if it's very complex, and if the shaders, that is a sneaky way of calling programs that describe how to render surfaces, if your shaders have a complex code inside of them. All of that will cause your GPU to throttle and will cause an overhead on the GPU side. On the other hand, if we have problems with CPU, that means that we have too many draw calls being issued. As follows, we will reach some kind of limit, after which we'll not be able to issue any more draw calls to the GPU, and the GPU will stand idle, because it will be quickly done with the instructions which we provide to it, and it's going to be a bad thing, because GPU has to be working to its maximum capacity. It's in our best interest. So we have to take off the load from the CPU, but how do we do this? How do we reduce the number of draw calls? As you can see, when I run my game, I got different kind of geometry all around my level. I got grass, bushes, all kinds of buildings, mountains, everything, and my draw calls don't tend to go above 200 of draw calls. As you can see, I'm batching my draw calls. That is, I'm not sending many draw calls by the CPU to the GPU that are small in size, but I'm gathering them up in bundles, only then sending the data about several objects in a single draw call. As you can see, the scene would like to draw at least 900 of draw calls, but I managed to save a vast majority of them by batching. Batching, static batching, is something provided by a pro version of Unity. And because of that, instead of 900 draw calls, I'm only doing like 100. So my CPU is sitting there and it's safe, because it's not taking a huge overload from it. Something for a simple game as this one, 200 draw calls seems about right. And actually looking at the scene, it could actually be optimized so many times. However, this seems to be a reasonable number, but remember that if you're developing your game for a mobile platform such as iPad 1, you should not go above 50 draw calls, because this is an absolute killer for iPad 1. Whatever you do, your levels should only have maximum of 50 draw calls. You'll get a different draw call as you assign different materials to objects. So let's say I create like 1,000 materials in here, and every single object of mine will receive its own material. Yes, this provides a greater flexibility, but suddenly, because we have 1,000 materials within our scene, our draw calls will rocket to 1,000. Because every single object is using a different material, we won't be able to even talk about the static batching. In order to do static batching, such as for example the one that I do for this grass, is first of all, your objects have to have a same material on them, and they should be marked inside of here as batching static. If those two rules are met, then your objects will be packed into bundles during the runtime of the game and will be sent not one by one, but in a pack to GPU, making sure that your CPU is safe and cool. However, as you can see, since I have only 200 draw calls at maximum, or maybe 250, and I'm saving something like 1000, have a look at my top right corner, or even way more than 1000 of draw calls in certain times, I'm still getting a quite low frame rate per second if I'm playing in a full screen mode. My frame rate holds at about 30 frames per second, slightly more, but it's mostly due to the fact that I'm using a tessellation shader on my terrain, which I'm not a fan of at all, and I'm running this version of the game in the editor and on the laptop. Because of that, I'm putting a strain on the GPU of the computer, which is actually an integrated one. It's not a free card like you get in the portable computers. It's just an integrated chip, which is quite weak. However, even it manages to pull off something like 30 frames with the tessellation and the reasonable number of draw calls. As you can see, my scene consists, although it has so many objects, it consists of about 100,000 of triangles altogether, and I'm rendering most of the time just about 40k of triangles. Keep in mind that this 100,000 of triangles is because I have a catacomb passage inside of the cave, and it's full of stuff as well in there. That's why all the triangles in the scene add up to 100,000. I also have a village building right there, and a few trees all around the scene. So all in all, I did all I could, and now it's just our GPU that is throttling. There is not much we can do about it, rather than just use simpler shaders and less geometry. but for demonstration purposes I had to use a tessellation shader for the terrain. If I wouldn't be using it, it would be something like 70 frames per second in the full screen mode. Because we're focusing on draw calls in this example, this is exactly what the atlasing was about. GPU does not like to switch from texture to texture, and it takes a pretty decent amount of time to do that. So we would like to supply one single texture so that GPU can just slide across it and pick certain regions if it needs to, instead of substituting a new texture every single time you want to render another object. Because I'm using atlases, such as for example the herbs grass atlas, I can have different objects within my scene, each one of which was mapped in 3ds Max, just like we talked before, to sample from a specific area of this atlas. That's why when the GPU renders all of those objects, all of those objects can have the same material and share the same texture, but still be different and grab different parts of the texture, resulting in less switches for the GPU when it works with textures. And because it has the same material, the objects can be batched, taking the strain off the CPU as well. Because of that, we are packing our textures as much as we can, so that we can stick the same material with the same texture on as many objects as we possibly can. Be it the grass, different parts of the buildings, or even texturing the character. As you know, the monk himself is being textured by just one single 1024 by 1024 texture. You saw it yourself, as we were working with it before. Because of that, all of his parts have the same material and he's rendered with just one draw call. All of his geometry parts, be it the hands, the pouches, the belt, the dress or the face, they all share the same material, which has the same texture. When GPU works with those parts of geometry, it does not have to do any kind of switches at all. It works with one single texture and is very happy because all parts are sampling from it. No switches are required. However, because Monk does not have a mesh renderer, but instead, if we click on it, you can see that it has a skinned mesh renderer. That is, the vertices of this model have different transformation matrices applied, are bound to behave differently depending on the transformation matrices that they are bound to. That is how the mesh was skinned before. Because the mesh of the Monk has the skinned mesh renderer applied to it, it cannot be marked as batch static. You can only do this to the objects which have a simple mesh renderer, not a skinned one. There is still one thing which is called dynamic batching, but it has a very small limit of vertices that your mesh has to be comprised of. For example, it will try to batch dynamically your objects if, when summed up, their vertices are below something like 180, maybe 300, I don't remember. So it's a very small number and is almost never practical. But still, for my Monk, there is still one benefit, a huge one, which is we save on the number of materials and just texture all of his parts with one single material that has one single texture. Speaking of the static objects such as my grass, herbs and bushes, they are all sampling from the same texture, and because they are not moving and they have a mesh renderer, they can be marked as a batch static, and because they are using the same material, have mesh renderer and are batch static, they are being grouped in packets and sent to GPU in packets as well. GPU is very happy that they are all sampling from just one texture, and the CPU is happy because it has its cycles freed up due to the low number of instructions that it had to issue to the GPU. Keeping draw calls low and reducing the number of vertices within your scene, as well as simplifying your shaders, will bump up your FPS by a quite high amount. You have to figure out for yourself. If you run a game and it throttles, that is, the frame rate is quite low, try reducing the resolution of your game. If the overhead still persists and you're still getting low frame rate even at low resolution, that means that the CPU is throttling. If, however, you reduce the resolution and you get a significant increase in FPS, which is quite often the case, then it's the GPU, because the more pixels it has to render to, the more difficult it will be for GPU to work. With this strategy you can determine easily if it's GPU or CPU you need to work on. One golden rule is make sure to think through an efficient way of building your game, be it geometry, coding, writing shaders, animating, making textures and reducing the number of materials. But don't worry about productivity until you test the game on your targeted platform, and only then, if you see that the frame rate is below 60 frames per second, only then start to determine what was the cause and begin to improve in this area. But nobody has cancelled writing good code, remember that. I mentioned 60 frames per second, and this is really the golden rule. The vast majority of displays, be it your TVs or displays of your computers, are capable of outputting 60 images on your screen per second. This creates and sustains an illusion of real-time response. However, if your frame rate is above 60 frames per second, that means that you're wasting something. For instance, if you get something like 100 frames per second, you're wasting those 40 frames which you could have used on using more beautiful shaders for your game, or more detailized geometry. Tend to keep it at about 70, 75 relative to 60 if you're developing for a personalized computer platform, because sometimes frame rate tends to drop. And if it drops, you still want to have it above 60. This is pretty much everything that you need to know at this stage. It's quite a lot of information to digest, and I hope you enjoyed it just as much as I did.
In fact, just before we finish off for today, I'd like to show you what will happen if I do come back for part 9. Lately I've been working on building extension for Unity, which allows you to import your own meshes for the terrain. We've touched on this one slightly during this lesson, but I didn't talk about it in detail. And what it is it basically allows you to select the mesh, and granted that you have a couple of scripts located in some of your folders, precisely in editor folder, because of it you'll be able to alter the texture directly on the terrain and build different objects on its surface, such as grass, quickly positioned bushes, etc. The terrain is using a tessellation shader right here, but this shader is a special one. It's the one I've written, and it incorporates tessellation method provided by Unity just to demonstrate one special and beneficial thing that this terrain has and which Unity's terrain lacks at the moment. As you know, Unity's terrain at the moment does not allow you to apply any kind of tessellation material to create those bumps on the surface of rocks and uneven surfaces sticking out from the ground. This one does allow you to do so. And it's quite interesting to see how many people ask me, well, how do you texture terrain? Terrain is so big, not even 4K texture will be enough to let it sample from it. This is not how you do it. There is a very clever way of achieving what you're asking me to do, and it leads you towards terrain painting. What we have here is we got a terrain which tessellates itself the closer we get to a certain point and creates those kind of bumps that you see here. We can increase the displacement by which it's being pushed away from the ground by dragging this slider displacement on the terrain material shader. But I prefer to have it on reasonable amount, so something like this is fine by me. It creates nice visualization of rocks, but to be fair I prefer parallax occlusion mapping shader, which is quite complex and nobody else has implemented it yet in a straightforward way. So I decided to go temporarily with the tessellation shader, and you can see because of that sometimes artifacts on the ground that it looks like the ground is wavy and is built not really of a solid material, but some sort of water because it moves. To avoid this artifact, all you have to do is to bump up the edges to have more of them, but this obviously hits your GPU very hard. This is fine by me, it's fine for demonstration purposes. Real-time displacement of the vertices is okay. But as I said before, I would prefer parallax occlusion mapping. However, we have a terrain right here, and it's a whole square of displaced geometry, which is imported here and then subdivided by Unity into little chunks. In fact, I'm gonna go into Edit, Preferences, into Colors, and make the wireframe active, give it an alpha of 0, so that you can't see what the wireframe is. If we come closer, you can see that indeed the ground is quite rigid and uneven because of the rocks and the displacement map, which is being applied through the shader to the ground. What I've allowed myself to do, granted that this is an object of terrain with the script called terrain paint, which I've written myself, granted it, and having inside of the editor folder a script called terrain editor, when those two things meet, when we select an object with a terrain paint script, terrain editor from the editor folder notices this and provides us a set of tools described in the terrain editor script, which you can see being debugged here right inside of the editor window. The way I made this is at the moment I have only 4 textures to paint with: rocks, soil, grass, and stone. Here, let me show you. I'm gonna click here so that it highlights in the project panel, and as you can see, it's this one. I'm gonna double click on it so it opens in the Explorer. This is the kind of texture that we can work with. It's not too big. As you can see, this is just 1024 by 1024, therefore every single piece is just 512 by 512. Because of tiling, we can make those pieces repeat each other, have a very detailized look of the geometry. If you can see here, when I zoom up, and perhaps let's turn off my light, when I zoom up on the surface, you can see that the texture really repeats itself. Well, it's hard to spot because I've overlaid different intensities and did my best to make this as unevident as possible. But what it is just a square, terrain square, with some vertices offset, on which I've applied a shader which grabs 4 pieces from this texture and tiles them on top of each other. In fact, I can select my terrain with a shader and set the tiling to be something like 5 perhaps. As you can see, the texture became low quality. That's because it's not being tiled, and it's repeating less, but it's stretched over the whole terrain by a greater amount. If we set it to be 1:1, just as it's supplied, so we grab 1/4, we stretch it across this square, we grab the second quarter, stretch it across the square on top of the first one, grab the third quarter, stretch it on top of the first 2 quarters of texture, and do the same with the grass. You'll see in a second how we blend between them, but if we do that one to one, you can see that the texture is really crappy. That's why I'm going for 20 by 20, and this way we repeat texture 20 times in each dimension. We tile it 20 times. So we tile rocks 20 times, the gray rocks, the soil is tiled 20 times, and the grass is tiled as well 20 times, both in X and Y. Having this kind of atlas with 4 textures, and effectively using it as 4 separate tileable textures, we then make use of one single small texture, which is 256 by 256 pixels, as you can see in here, which is a red, green, blue, and alpha channel containing texture. And what we did here is we told our shader, which is sitting right here on the terrain mesh, we told it, okay, have a look at our filter texture, and if at particular pixel the red value is 1 and all others are 0, that means that on this area you should reveal the grass texture and hide all other textures. If it's 0.25 for red, 0.25 for green, same for blue and same for alpha, that means that all the textures, both the brown rocks, the gray rocks, the soil and the grass, they have an equal value. So on that area, reveal each texture a little by an equal amount so that the final color combines to 1. And that's it pretty much. Just to clarify it even more, I'm going to select the terrain filter once again. The green channel corresponds to this kind of grayish stone or pavement, whatever, and this is exactly how we reveal the gray texture at this particular point, where the green channel is at maximum, that is 1.0, and all other channels are 0, reveal the gray texture in here, and hide the other textures on that area. It was very tricky to figure out how to tile given an atlas without subdividing my terrain mesh. But in fact it's possible, and that's exactly the sneaky way that I was referring to somewhere in the middle of my tutorial. Back then, we figured out that if you have an atlas, it's really not possible to tile the textures within it, even if the textures themselves are tileable. When you think about this in a regular way, there is not really a way to tile a texture, because if you scale up your UVs, thinking that you want to grab more and more parts and tile the texture, you're gonna grab other 4 things. But it's really a matter of offsetting the UV coordinates, shoving them back into the correct place, and keeping to sample back from 0. This is something very complex, which we're going to be probably discussing in the following series if I do come back for part 9. Because not only that is important, but also making sure that there are no seams visible, and one drawback is that if you attempt to tile parts of the atlas, it is possible, but it will reveal ugly seams, which will destroy the look of your terrain, especially if you view them at an angle. That happens because of mip-maps, as well as anti-aliasing. But granted that I have this, I have a very efficient way of sampling my textures, reducing my draw calls once again, and the same story happens for a displacement texture. This is just a black and white texture, and where it's white, pixels, or in my case vertices because I'm using tessellation shader, in those white areas they'll be offset by a greater amount. So it's just a matter of tiling up the ordinary textures on top of each other and revealing them in appropriate areas according to the filter texture, in the same way as tiling parts of the height map atlas and also revealing appropriate parts according to the same filter texture. If you have those 3 textures, you'll have your terrain painted. You won't require a bizarre 4K texture to texture it or whatever, or anything crazy like that. Just tile your textures, reveal them, and GG. But it's gonna be quite difficult for you to paint the filter texture because you have to create it somehow. And to go back into Photoshop, paint it, and constantly reapply it in Unity to see how it looks like is really a big pain. You want to have a way of being able to paint it directly in the editor, and this is exactly what I did. You can paint the filter texture inside of the editor and see the immediate changes which it performs via the shader, which looks at the newly altered filter texture and adjusts and reveals the tiled parts of the atlases accordingly. For instance, you can see that if I select the red channel to paint on my filter texture with the help of my editor script by pressing H, this is just how I've coded my editor script inside of the editor folder for the terrain. But if I do press this, I've immediately placed a marker for myself to see that I'm painting in a red channel with a strength 0. I can paint with different strengths, like 0.6, 0.8, and if I'm painting with red, you can see that it's corresponding to the bottom left texture of my diffuse texture atlas. Once again, as you can see, it's styling itself, constantly repeating the texture over and over again, but because of that, we have a very crisp looking texture. Of course, if we tile it something like 100 times, you'll see a clear repetition, and it's going to be very detailed. Good when you're close, but not too good when you can see it from far away. So 20 was okay by me. And if I press J for instance and paint in green, also with 0.8, you can see that it's revealing a gray rock. Obviously, if I zoom up, the displacement texture is also picking up the appropriate area from the black and white atlas texture, also according to the filter texture that was supplied to it, and which we are modifying by painting via my script. We can paint with different brush hardnesses, brush opacities, which I can change by pressing different buttons. For example, we can paint with a very barely visible brush opacity, or paint with a fully enhanced one with opacity of 1. Once again, if I zoom up and actually bump up the displacement so that you can see better, as I'm applying the color to filter texture, you can see that it's being used straight away by displacement atlas as well. That's something for demonstration. I'm not a big fan of tessellation shader, but that's what you can achieve with my tool. And hopefully I will come back and we will be able to learn about that. I'll have to teach you about shaders, the editor scripts, to enhance your skills, making it able for you to build your own tools and speed up your working process. Also, I made it so that if you press G, you can draw grass pieces. So you place them on the ground, as many as you need, and they have random rotation so that they don't look like they are formed in a grid and are parallel to the world coordinates. So they have random rotation, each one is just a polygon with 3 vertices, and you have 2 polygons to form a cross of a grass blade. It is pre-modeled in 3ds Max, its normals are modified just like I've explained to you before, so that it blends nicely with the ground underneath it, and is then instantiated via this editor script as a prefab. Very nice looking grass, very efficient. I think all of the grass right here in the whole level amounts to just 2000 of polygons, which is very nice. You can also draw bushes really quickly by pressing B. As you can see, it's gonna draw a bush according to my script, and I'm gonna place it here. Of course I have to press B in order to be able to stop drawing bushes, otherwise as I'm rotating my camera I'm gonna be sticking new ones all around. The way I'm doing this is if I have something pressed, like draw with the red channel, if I'm right clicking and dragging my mouse, it's gonna paint the filter texture. And if I'm careless and I'm gonna forget about that I'm painting in red channel and move my camera, you can see that I screw up my filter texture because I've modified red channel on those pixels of the filter texture. But that's fine. As long as I'm careful, I can speed up my working process so much because I can paint filter texture straight away in here and modify it without needing to go to Photoshop, adjust it, come back here and see how it looks on the terrain. This is something that fascinated me a lot. Hopefully we'll be able to learn it later on.
This has been a very long lesson, guys, and granted that it might be the end of our journey due to my very busy schedule, I would like to give you one final task. If you test your player movement script, you'll see that your monk moves through the obstacles. This is because we dropped using the rigid body approach, and now he can walk through stuff and walls, so he does not collide with objects within your world. Your task is to figure out how to do it and how to achieve this without using the rigid body. If you do use rigid body, you'll notice that as you collide into objects, you are pushed backwards with vigorous force, creating a very irritating and nasty movement back and forth, as if your character is trying to jam through the obstacle. No matter how hard you try to interpolate, do the continuous or dynamic tracking of movement, it will still look unnatural. For the first-person character, this is something that you should not be doing. Only for some world objects that's acceptable. That's why drop using rigid body and figure out for your homework how you can create a script which restricts movement of the player through the walls, basically does not let him to walk through them, but does not create a jagged movement and does not result in a low-quality pushback. I found one way of doing this, and I'm pretty sure there is at least a dozen ways of achieving this. So, pause the video, quit it actually, experiment, and then come back later on to find out the answer. It will follow in 5 seconds. What I found out is that if you have your player character, he is a game object. He has the player movement script, which propels him forwards and backwards, leftwards and rightwards, with the help of the input class, which inspects your WASD keys and the value that is coming from them. In our script, we made use of 2 translate functions, to make him move leftwards and rightwards, and the second one along the forward axis. If you attach 4 game objects, which are empty, one at the front, one at the back, one on his left and one on the right, and let's call those game objects trigger zones. They are simple and plain, empty game objects. They don't contain anything except for one thing, a box collider. This collider has to be a trigger. It's a trigger zone. We've been talking about triggers when we were making a burning ball of cloth. On each one of those game objects, you have to attach a copy of your personal MonoBehavior script. In there, you'll make use of the onTriggerEnter function and also onTriggerExit, and one single variable of type Boolean. Once something enters it, that is, some sort of collider, onTriggerEnter will ensure that the variable is set to true. And by the way, the variable has to be public. As something leaves the collider, onTriggerExit function will make sure that the variable became false. And this is the case for all your classes on all 4 trigger zones. Now, from the player movement script, it's just a case of establishing pointer variables during the start function, which will be referencing 4 scripts on 4 of trigger zones of your main character. Don't establish the link to the Boolean variable, because you won't establish a link. You'll simply copy by value. Instead, point towards the script on all of the trigger zones, and then during the update function, before moving your character, if something, for example, is inside of the trigger zone on the right of your character, don't allow the creature to move towards right. Similarly, if the Boolean variable for your back trigger zone is true, that means something is inside of this trigger zone, some collider, restrict the player's movement backwards. Still allow it forwards, but don't allow it to move back. Of course, as your character turns, the zones should turn around it, which will mean that the right zone is always to the right locally, the left one is to the left, and so on. You can make use of this approach further on to restrict player jumping, standing up while crouching, for example if something is on top of his head, if he's hiding, for example, underneath the table, and so on. Congratulations on completing this tutorial, and let's draw a conclusion. If you look back at what we have done so far, it has been 8 parts of intense content. And if you have been watching and following me since the very beginning of those series, I do thank you a lot. It's people like you who provided me support, who enjoyed my videos, and kept me interested in making them, providing valuable content to the community. Once again, I wanted to create a huge library of content ever needed by a game developer, to throw a bridge over this huge abyss between someone who has a passion for games and being actually able to fulfill it. Today, 7 hours of hardcore content, in my opinion, is quite special. Trust me, poor Camtasia program was choking and stuttering when I tried to compile all of that. Keep in mind the words that I said at the beginning. I might come back, and I'll do my best to release part 9. However, right now, it's very important that I finish university, get good grades, and set up my future. I will always love games, and this is the industry that I'm gonna be working in. Right now, hardcore studying and work, and after that I'll see how it goes. If you stay subscribed, bring friends. When I come back, you'll be able to find my videos and watch part 9. Of course, you can always find me on internet. There is only one single Igor Aherne in the world so far. But please, no spam. However, I do like making new friends, and if you want to share your ideas or thank me, you can find me on LinkedIn, VK, and Facebook. So, stay tuned, and I hope we'll meet again. А тебе, Игорь, я могу сказать одно. Была проделана отличная работа, 8 частей отличнейшего контента, и я счастлив, что ты выбрал этот путь. Компьютерные игры — это то, что ты любишь, и когда ты вырастешь, ты посмотришь это видео и увидишь, каким ты был в 2014. Удачи, дружище, у тебя все получится.